Hi everyone, welcome to the ultimate shortcut into the machine learning world. Whether you are a complete beginner or have experience or you would like to brush your skills, this video will give you a concise and intuitive breakdown of our full YouTube playlist backed into with the numerical example, hands-on Python code, and step-by-step explanations that make complex concept feel simple. So let's dive. So as you can see here, we start from zero. What even is machine learning? And how does it differ from the traditional programming? And you will learn three pillars of supervised learning, supervised, unsupervised, and reinforcement learning. So real-world application from predicting house price to spam email detection and object detection, tracking, and everything. So and you will learn how to set up your environment using Python, Jupyter Notebook, and how to install essential libraries like NumPy, Pandas, Skyline, and OpenCV. So it's perfect for beginners who want to build a strong foundation without drawing into the theory. So next up is the regression models. You will master uh, one of the most fundamental techniques in machine learning is linear regression, and this also is the foundation of a deep learning. So in this section it is step-by-step weight calculation, hands-on implementation using pure Python and gradient descent, and you will learn also multiple linear regression, polynomial regression, and how to evaluate your model using root mean square error, and also R square score. So tackle also overfitting with L1 and L2 regularization, and it will show you what is the difference between this and L1 and L2, and when to use L1 and when to use L2. So all explained with simple numerical examples and real Python code. So it's now time to classify. In this section, we explore powerful models like logistic regression, decision trees, Naïve Bayes, support vector machine, KNN, key nearest neighbor, and you will learn how to evaluate clustering using confusion matrix, precision recall, and F1 score, ROC Curve, and AOC. Plug so, plus this, it will give you with a full project spam email detection and multi-class classification. And for the next example, for the unsupervised learning, what let's see what if you don't have a label data. So in the classification you have to have a label data, but what if you don't have a label data? No problem, we cover unsupervised learning with where the algorithm finds a pattern and insight from its own. So it's including key means clustering with optimal key selection, because key means that you have to identify the key, but I also provide you how to select the optimal key. Also hierarchical clustering, and then principal component analysis for dimensionality reduction. I have made it really easy with the super examples. And for a big, or let's say a large scale data set, normal principal component analysis won't be work, because it you have to load the data into the memory. But if you have a big data, there is a solution. We introduce here incremental PCA, which is a memory efficient and perfect for big data processing. So evaluate also clustering with like C-load score and interior. For the to level up with the ensampling learning, combining multiple models in to achieve high accuracy, we explore uh, random forest, AdaBoost, gradient boosting, and XGBoost, one of the most powerful tool in machine learning competitions. But we go beyond just the training and so I have also here, I forgot just to mention that in these projects here, you will learn how to structure your code base like professional, use inheritance and abstract classes, and also to create reusable components, design a clean interfaces for consistent API behavior, implement polymorphism, let's say, behavior. So your pipeline can handle text, images, and or maybe numbers seamlessly without rewriting the code logic. So what you have just if you have this implementation will help you to uh, to make it, let's say, for any project. Just you need to minimally changes to make it work on any project. So please have a look on this video, and you will see, you will understand what I'm meaning here. So these are the techniques used to let's see, top used by top data science and engineering to maintain scalable and production systems. And now let me back to the model optimization. So once you have you built your model, so you need to know how do you know if it's good or not. So in this section, there's a cross-validation technique to test your model through to test your model, and you will understand also what is the overfitting and underfitting, and how to remove, or let's say overcome this stuff. And you will learn how to improve generalization. So go beyond just building a model, learn how to build better models. And for the now, we enter the exciting world of deep learning. So you will learn neural network basic layers, activation functions, and weights, implement forward back propagation, and understand also back propagation with really example. You can also do it with your hand, and use PyTorch to build your first neural network, loss function, and the accuracy metrics explained. Think of this as a launch into AI, computer vision, NLP, and more. So for the convolution neural network, I just focus on this because I'm a computer vision engineer, and let's say I'm working with most of my time with CNN, with images and videos. So images are also a data. So the CNN can be a tool for image recognition. So in this section, you understand the convolutional layers in a very more details, and also with examples, and sometimes also with animations, and also polling layers feature, and you will also know how to extract features from the from the models, pre-trained model. And also explore advanced technique like transfer learning, which is useful if you have a small data set, or if you have no, let's say, computational resource, and you would like to use a pre-trained model and to make it usable in your cases. And also building a model using if VGG16 and ResNet. So these two lessons here, in the beginning I have explained how to calculate the parameters, how to calculate the features map size, how is working, and explain more let's say more complex concept in the VGG. And no so most of, let's say, the I have also seen YouTube videos on this. So in the before I'm explaining stuff, I'm just trying to see how they deliver it. So I found some let's say high percent that they miss some concept in this VGG or resonate. So I have tried to make it simple. And also you will learn about batch normalization and layer normalization, which is critical for stabilizing and accelerating the deep learning training, which is yeah. So this batch normalization it's mainly used for in CNN, and layer normalization is used for NLP. But I give you a introduction to this stuff. So now the best way to learn is do it yourself. In this final section, you will apply everything to real problems. So house prediction using XGBoost, email spam detection with logistic regression. Not sorry, it's not logistic regression. It was with XGBoost. And also you will see a customer segmentation with clustering, k-means and DBS scan and Gaussian mixture model. You will see the comparison between all of these stuff. And yes, even you show how to deploy some of these models using Streamlit, so you can see how to share that. So you can share it with even with the world. And that was just the task of what a machine learning course, intuitive understanding with the numerical and Python example has offered. So every video comes with clear and free explanation, numerical example to reinforcement, and for some algorithms you can also do with the calculation with your hand. So I have made it very really simple, and practical example to build your profit. And whether you are preparing for interview, working, or let's say personal project, or starting to career in a data science or AI, this course is your roadmap to success. So if you found this summary helpful, please subscribe into my channel and hit the bell icon so you will never miss any lesson. So also please see the playlist, visit the playlist. I will just show you the playlist. So you can see this is my, oh no, sorry. So this is the playlist. You can see, I will just, you can see it's here about, I don't know how many, yeah, 58 video. And visit this and see. I will just recommend you to start from the beginning. Some concept already explained in let's say early videos. And if you are, for instance, interesting only in this stuff here, some concept might be already explained in the previous videos. So I just recommend you to go from the beginning. And if you have, of course, any question, just drop it down in the comment below. I will try to answer it. And that's it for today, and thanks for watching, and see you next time. Hi everyone, welcome back to my channel, to our comprehensive course on machine learning with numerical examples and also Python. So in today's video, it will be a little bit, let's say, theory, and up the next lesson, it will, of course, it will be more practical. And just because to give an introduction to machine learning, we have to go through some steps. Okay, and imagine, I mean, indeed, we need to know what is the machine learning, right? So imagine teaching a child to recognize, let's say, animals like cats. So instead of giving them strict rules like the cat has four legs, and also it has a pointy ears, and maybe it has a tail. So you show them, instead of that, you just show them some many pictures of cats, and over time they learn how to recognize cats in any position and also in any colors. That's exactly how machine learning works. So as you can see here, this is the machine learning, the traditional programming and also machine learning. So sorry, I have yeah, sorry for that. I have post. Okay, we in the traditional programming. Yeah. So unlike traditional programming, where you have to write explicit rules, so machine learning allows computer to learn from the examples and improve with experience. It's like training a system rather than program it. So you can see here in the traditional programming we have a program with data and we have an output. Let's just consider it as a role-based system. For instance, if else, just keep it as simple as you can. And in machine learning, you have a data and you have outputs. For instance, if it's in case of classification, and this will give you a model. It's like a program. It's like if we consider a decision tree, it's like if else, for instance. And for the testing, you have data and using this program or the trained model to give you the output. So this is the difference between traditional programming and also machine learning. So as you can see here, the machine learning is a subset of the artificial intelligence. So hopefully you can see this image. Oops. Okay. So you can see this is the artificial intelligence. This is the outer circle, and this is the machine learning. So it's a subset of the artificial intelligence, and it's also you can see the deep learning. It's part of the neural network and also part of the machine learning. It's a subset of machine learning and also all of these subset of the artificial intelligence. So as you can see here, the main key, let's say, of the machine learning is that you have a data, it's learning data, it's learning from data, and the idea is to find some patterns, and that makes, let's see, some decision. It's if we again if we consider as a decision tree, it's like taking a decision. If the value is greater than specific threshold, just keep, for example, go to this direction or go to left or right. So you can see here, this is the data, and this is the machine learning, training the machine learning. And why we see this is, just let me just go back. What is the I mean, we see the difference between traditional program and machine learning. And as you can see, machine learning, to generate this model or program, it's go through several iterations. It's not only one iteration, for instance. So to make this model, it's try to learn from data and extract the insights from data to build this model. And you can see here, for instance, training, and this is the model, build model, and this build model will be used for the tradition, for the prediction. And I mean, don't worry, because this is somehow more theoretical part. But from the next letter, I'm promising we will go through several examples, and also with mathematical, I mean, with numerical examples. Okay, and if you see here the machine learning, it has different types. The different types, the first one is we have supervised learning. Think of it as learning with a teacher. So the algorithm learns from labeled examples, like a student learning from the solved problem. Or let me give you another. So I have, oh, how to move this. Yeah, right. So the supervised learning, it's like it's working only if you have a labeled data. So if you have for instance image classification, you have the input image for instance for cat, and you have also the class label. So this telling the model that try to learn this extract some features from this image, and try to memorize it or try to generalize it, that This features of this of the image, it's a cat, and it's try to, for instance, in the beginning it will be classified as a dog, and we have, for instance, a loss function, and it will try to calculate the loss function, and we'll see, it will tell the model that no, this is not a dog, it's a cat, and it will try to update the algorithm, the weights, until getting the final, let's see, the most correct answers. So this is the supervised learning. It has labeled data, and and also the data itself. And in the, or for instance, another example is for spam email detection. The system learns, for instance, you have sometimes you face emails move to your spam folder. Why it's moving to the? So because the algorithm is learn that if the model, for instance, contains some specific information or a touch image, I don't know what kind of images, or let's say someone asking for money, this will be classified as a spam, and it will be moved directly to your spam folder. And for the supervised learning, we have two categories: classification. Classification, and also regression. What is the difference between this and this? The classification, the class label is a specific category. Let's see, categorical. So you have it's countable. For instance, I have cat, dog, and maybe some animals. So as you can see, the animals, it will be countable. But for the regression, the class label or the prediction, the predictor or the target is a continuous value, continuous. For instance, price, house price prediction. As you can see, you give the information of the, for instance, the area, the number of rooms, the number of where's the location of this house, and the prediction will be a price. So the price is not category; it's a continuous value. And let's move to the unsupervised learning. Unsupervised learning, you see, we don't have any class label. So the idea here is to find a hidden patterns from this data and try to categorize or group all similar stuff in the same group. For instance, let's assume that you have a set of fruits. Let's say apple, orange, carrot, and I don't know some others. So, but here, let's say you don't have any label for this specific fruit. So the unsupervised learning, it will try to group all of these similar, let's say in a sheep, similar stuff in one group. For instance, it will assign apple and orange in one group, and also let's say the carrot and banana in one group because they have different sheep. And this is the unsupervised learning. And in supervised learning, the algorithm try to find the patterns from data without any label. So you don't have any label. Imagine, let's see, sorting a basket, as I said, of this fruit, and you have no label. I mean, or let's say it's not needed. Let me give you a real example. So sometimes you need to detect the defects in images in the product line, let's say. But unfortunately, sometimes the class label, it's not, let's say, the defect samples are not easy to get. Assume that you are in a computer, let's say computer chip uh, manufacturing or product line. So to get this defect examples, you have to make a defect manually, which is maybe it's more expensive for the customer. So the solution here is to use unsupervised learning. Try to learn the model with OK images that that's set manually by the customer, by the customer, let's say. And the system will try to learn, or let's say generalized information or extracting hidden pattern from these images, OK images, and compare it. For instance, in the inference time is compared with the other images, and compare the features if there any difference between the defect and non-defect. And the final one is we have the reinforcement learning. Let's say think of it as learning through trial and error. It's like teaching a dog a new trick through, for instance, through treat. Reinforcement learning algorithm learn optimal actions through reward and potential. Or for instance, uh, regarding the gaming, sometimes you just try this, for instance, open this door and or go to this direction. You have the result and you will learn from this result. No, this, for instance, if I go to this direction, it will be for instance a big mistake. And this is only a reinforcement, let's see, example of reinforcement learning. So what are the application of machine learning? I mean, of course no one so as you can see, machine learning is now used in I will see in all applications. For instance, in business, it's used for fraud detection and customer behavior prediction and also market analysis. And for instance, your smartphone uses, for instance, face recognition and also voice assistance. So it's try to so let's say in generally machine learning is used in all of the in our life in any application. As you can see here is automatic language translation, of course, with this revolution with the chat GPTs and the DeepSeek and everything. It's it's using heavily machine learning. Also medical diagnosis. If you have some images, for instance, you would like to classify or detect the tumor or any disease in images, it's also used in a stock market and many applications. And also self-driving cars, which is you can see one example is as a Tesla or Chinese cars. And yeah, okay, and let me just close this session. It's of course theoretical, but I am promising you from next lesson I will try to start from scratch. Let's see, begin with installing the Visual Studio Code. Maybe it's maybe not. Maybe just preparing the environment, Python environment, so we can start directly to program. So I will start from this basic. Maybe it's not relevant for someone of you, but I will just try to keep it one complete course. Okay, so thanks for watching. If you like this video or and looking for any for other tutorials, please subscribe and hit like button. And if you have any question, of course, just drop it down in the below comments, so I will answer it when I have time. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. So in today's video, we will try to make some, let's see, starting the practical part. So by set up the Python environment. So we will try to see how to configure the Python Jupyter notebooks and also what are the essential libraries. So let me just shift to the Visual Studio Code. So I hope you already installed the Visual Studio Code because it's super easy to install it, and you can just try to see how to install the Visual Studio Code. And I'm assuming that you already opened the Visual Studio Code. And there are also other IDEs like PyCharm, and you also can write it in a plain text. But I'm preferring to use Visual Studio Code because you can use it also in under Windows or Linux, and maybe in OS Apple. So before diving to this, let me just show you a brief comparison between Anaconda and Butri. So Anaconda and Butri is it's like environment management systems. So as you can see here, you can also use Anaconda or Butri. It's almost the same. I mean, if we follow the next letters, let's say next video applying, for instance, Python, writing Python code in for linear regression or any algorithm, it should be the same, but you just need to just choose one of these. Because most of my work, let's say I'm using P3, so I will stick with P3. But it's just to give you a brief introduction, or let's say comparison between these two. As you can see, I will just focus on only on the X, course X, and you can see here Python Fusion Management. It's not supported, but it's rely on a system or PyEnv. So in Akunda, you can see create Python, create environment with this Python version. But here you need to download, also install the PyEnv. And let me just now go to this. It's only supporting Python. It's not like R or CUDA and others. And let me just say this. Work well with Py, Py, Py. So this is designed for this stuff, and uh, it's up to you if you would like to use Okunda. If you are, let's see, a data science, machine learning, scientific computation, and I'm also data science and machine learning engineer. I'm using Beauty, but just to give you a brief introduction. And here you see if if you need both Python and non-Python dependencies, you can use this. If you use only Python code, it's better to use PO3. And one important uh, one important step before downloading, let's see, installing the Python, packages. And if I have here attach a file of a YouTube file, YouTube link. Let me just see if it's okay. Let me just click on this. This is how to install the Python, the Beauty, and also the dependencies and the PyInf. It's a free explained video and easy to follow. And if you have any question how to download this, just let me just write down a comment below, and I will reply. So just to save, let's say, time, and also not to replicate the stuff already uploaded. So as you can see here, install Beauty with PyInf. It's super easy and super, easy to explain and also to follow. Sorry. And before this, before this, you have to download this Visual Studio code. Visual Studio tools in 2017 and 2019, maybe 22. Yes. Why we need to download C++? Because some packages, let's just give as example, uh, Skyline, let's see. And this Python, you have to download it, and some code, let's see, it's written in a C++, and it has to be compiled and from the source. So you need to download C++ installer. And I will attach this as also in the video, in the video description, and you have to download this. And you can see, if I just see, let's see this one here, 17. Just try to modify. And you can just give you what are the important components. And of course, you need to select this Python, C++, and you might also need to select the relevant one. Just try, if you have space, try to select all of these options. And in this one here, 22, let me just modify. Mhm. Also, you need to select C++, not selected by me because it's already in the other pages. And let me just see this. And here you need to download Windows 11 SDK, and in the other one is Windows 10 SDK. That's the difference. Otherwise, you will have some difficulties to install packages. It's using even Anaconda or Biotree. It's almost the same. And for the Biotree, after installation, after following this link video, you will try. After that, you will have the Python. toml file, which is identify, for instance, what is the version, the name, the version, the description, the author, and also here's the Python, which Python version you would like to use for this project, for instance. And this is the packages you would like to use, right? And the other one, as I mentioned, is Jupyter Notebook. Most of you, let's say, is familiar with Jupyter Notebook, but also you can install it here. You just go to the extensions and type note, type here, notebook. You can see here Jupyter Notebook from Microsoft. Just click to install, and after installation, you can create files, for instance, like this here. The extension IPy in notebook NB. So here you can see, for instance, if you'd like to have Markdown to explain the code. So let's see, install packages. So and here you see I need a code, for instance, import numpy as NB. The and you have to select the kernel, of course. But with following this video here, it will this one here, it will show you how to do these steps. And from the next lesson, I'm assuming that you're already familiar with installing the Beauty or even any other packaging environment. For instance, you can use PyInf, or you can use Anaconda and any others. So from the next lessons, it's not, let's see, this lesson is not related to it's not mandatory to do it, but if you would like to follow exactly what I'm doing, you just need to download this. Okay, I will now, as I said, I will attach this file and for the video, and yeah. Okay, then thanks for watching. If you see this video, let's see, helpful, or try to subscribe and like. And if you have any question, of course, write it down below, and I will answer it. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. In today's video, as I promised, I will try to show you or explain the linear regression step by step with real example. So this, if you understand this lesson, it means you understand the deep learning, I would say the deep learning principle. So because the linear regression is the component, let's say, of each layer. So as I said, I will. This is the example here. I will explain it from the beginning. Let me just, sorry. And here is the real example as well. It is explained in very details. So just you need just to go through this video, and if you don't understand, let's say, or you need time, try to pause the video and try to calculate yourself. So this indeed, this video or preparation, it took much time. So please, if you like it, try to like it and subscribe. And of course, if you have any question, just drop it in the comment below. I will try to reply on your question. So let me just see what is the real linear regression. The linear regression is a kind of, let's say, type of supervised learning, but the idea is to predict the target, let's say the target, but as a continuous value. So before diving into this stuff, let me just let you know what is the linear regression. So this assume that you have 2 points, let's say x and y. This is we have learned this from the school. So you have here the value of x, and here you have the value of y. Now, if you would like to write a equation for this, it's like this here, beta x plus beta 0, right? Or it should be like this, for instance, 2x minus 1. So as you can see here, for example, this is the value of x, and the value of y is here. The value of x is here, the value of y, for instance, is here. is here. And this example, for instance, this is the zero axis. Just try to focus here. For example, if the x value is 2, the value of y is almost 2.5. Okay. Now there's the y, it's like dependent variable. It means it depends on the x variable, right? In the x-axis. And y and x is independent variable. It's called independent variable in linear regression because it's not dependent on any variables. For instance, you have x, I need to find y. So y, it depends on x. Now, what is the slope and y-intercept? The slope, it's the if you move, for instance, in x direction, how much y-axis will be jumped or moved? It might be negative or positive. And as you can see here, for instance, if you have 4, the value of y is 8. If you have 2, the value of y is 4, for instance here. Now, as you can see from this, it's if you just ignore this -1, you can see y it's equal to multiply y 2x. It means 1 unit in x, its move the slope. I mean the movement, or let's say the jump in y, or the value in y is 2. It's 2 times. So that's why we see the slope is 2. Now, what's the intercept? The intercept is the value of y when x is 0. So for instance, for just for this simple equation, x is 0. If x is 0, then y is equal -1. So this is why this is intercept is -1 here. Okay, so this is only let's see overview of the linear equation. So now let's just go step by step into the linear regression. So let me start with one example. I mean the house example. This example, just move it here. And it has, let's see, the house size and also the price. So if the size house is the 1000 feet, or I don't know, square meter, but it's square meter, it's too much. Let's save it. And the price is 200,000 euro or dollars. And as you can see, the way, oh sorry, yeah, should be the price. Sorry, the price, but it's just because the next example is weight, as well as this one here. I will change it, sorry for this, price, just to make it everything is clear. Now I would if I would like to draw this, and to draw let's say a line for this data here, and for example next time when I have the size, I will try to predict what should be the price, right? And as you can see, this formula here, the price is equal b beta 0 plus beta 1 multiplied by size. Now I would like to find b0, beta 0 and beta 1 that will be fit exactly to this data. And next time when I have, as I said, a new sample, or let's say a new house, and I know the size of this house, I will try to predict the house, the price. So let me just, for instance, in the first iteration, you will try to initialize beta 0 and beta 1 with, let's say, random values, right? And after that, as you can see here, I have, for example, the prediction, the beta 0 and beta 1 is randomly initialized. We will explain this in more details, don't worry. And the idea, or let's say the goal, is to minimize the distance between this red line here and each of these points. And in the first iteration, I initialize this, and I see, I calculate the distance, for instance, from this red line to this, it's almost okay. From here to here, it's not that okay. And from this red line to this, it's far away. So I need to minimize these distances. So I will try to update this beta 0 and beta 1 with the new values. We will see it in the next session. I mean, the next few minutes. and assume that in the next iteration I have updated based on the cost, or let's say loss function. And here you see I try to minimize the distance between these points to the line. And also after the third iteration, I have this, for instance, is much closer to the point. It's try to fit, let's say, to draw a line. The best line, the best, let's say, linear regression. It should move through these points. And as you can see here, for instance, after some iterations, I see the size. I mean the beta 0 is 0 and beta 1 is 200. And now, if assume that you have a new size, right? Let's see, it's 500. So it will be 500, for instance, here. No, sorry, 500 will be here. Now the price should be 2. So 2 multiply 500, and it should give you y. And if you see, for instance, 1300, it might be here. And if we go, for instance, here, it should be multiplied by 2. Okay. Now this is, let's see, with one independent variable, which is size, and one dependent variable, which is y. But in case in real time or in real projects, we have many attributes. For instance, you have the size, the location, this some many, let's see, factors that will affect the price. So we need somehow real linear regression. It's not only for two x and y. It might be thousands of hundreds of attributes or independent variables. So I just give you one short example here, because we have. I just make it more, let's say, simple. So I have here the data set with, let's see, two variables here. The person one, it's just as index, just you need to ignore it. And here I have height and age, and the predicted or the optimal, let's see, weight is 120. This is for the first person here, and this is for the second one, the third one, and the fourth one. And why we can't see, if I have only three variables here, for instance, two independent variables and one dependent variable, I need to, if I want to visualize it, I need 3D linear regression. And if I have 5, 4, 10, and 1,000, it would be much difficult to draw it. But this example will try to explain everything in more details, so you can apply this concept, the same concept, even if you have thousands of independent variables. So now we need to find the weight, right? And the weight is equal beta 0, beta 1 multiplied by height plus beta 2 multiplied by size. When I change it to, I mean, the age. When I change this to age, I don't know, it's converted to greater or equal. I have no idea why, but that's why I just move it, change it to year. Let's see. Now, as you see, beta 0, it's the intercept. We know already what is the intercept. And the beta 1 and beta 2 is the coefficient of height and age. Now, this is, for instance, as a graph, let's see, because as I said in the beginning, this will be the introducing to the neural network. If you understand this concept, it's 100% guarantee that you will understand everything in neural network. So as you can see here, I try to convert it to a graph. So I have here the independent variables and height and age, and each one has a parameter. And I have the weight. The output should be the weight from this. This is, let's see, the class label or the predictable. We need to predict. The class label is categorical, and this is the bias or called intercept. Now this is, for instance, in the training. This is the forward. Now let's just make it much easier. Instead of weight, we need to find, let's see, y hat. And this height, it should be, let's see, x1, and this one, it should be x2, just to make it less text. Now, I would like to initialize, for instance, I will use this, use this to predict the weight of each person. And in the beginning, I will try to assume beta 0, beta 1, and beta 2 are zeros. Now, if I see here 0 plus 0 multiply x1, with x1 is 65, plus 0 multiplied by 20, and this one will be, the result will be 0, right? And you can see the y, this is the weight, the y is 100, but the predicted value was is 0. Now, this is wrong, right? So we need an optimal beta's values that will try to predict the exact or close to the weight. Now, the next step is to define, let's say, a cost function. So, for instance, here I have theta y hat is 0. Now I need to move to update this to get the real, let's say, the real values. So that's why we need to calculate cost function. The cost function, it will try, after calculating the cost function, we will update beta 1, beta 2, and beta 0. Only beta 1 and beta 2 and beta 0. So please keep in mind the data, it will be fixed. So you don't need to update any data. For instance, this data here will be exactly the same in each iteration. We need only to change only these variables: beta 0, beta 1, and beta 2. x1 and x2 has to be the same, and we try to find y hat. So this is the, let's see, the formula of how, because as you can see in this graph here, I have the y hat, it depends on 3 variables, right? That's why I have here g, so for instance, beta 0, beta 1, and beta 2. And because, as I said, y hat, it depends on these variables. And this is the formula, let's see how to calculate the cost function. It's 1 divided by 2 multiplied by m. M, it's number of samples in your case. For instance, I have in my case is 5. And this is a summation from 1 to 5, and y0 minus y hat. It means y0 is this one, for instance, minus 0, right? And this is the case how to calculate it. But as you can see here, this y hat, what is y hat? Y hat, if you see only here, just y hat, I just replace it. I mean, I need to replace it with this formula here. So that's why I need to add a t to update the weights of each parameter. And it's the same of this function, or let's say formula, but I just replace y hat with this one here. And you can see here, for instance, beta 1 multiplied by x1 I. It means the first element in the table. And I have here summation to go through all the examples. Now, as you can see here, m it's 5. Y, it's the actual value, or the actual value of the class label of the weight of the person, for instance, I person, and this one is the predicted weight of each, I mean, y hat, or let's see, this y hat, or this one here. Now, as you can see here, we need to find the gradient. This is using the gradient descent. And the gradient descent, let me just go here. Gradient descent. Let's just assume this is, let me just explain it in a simple way. So assume this is you are in the mountain, and you would like to find the the down of this mountain. You would like to get up from here. Now you will try to walk through your legs and try to step down. And sometimes you will find uh, this is not the right, let's say, the right jump. I have to go back, or no, I have to go left, or I have to go right. So this is because you are familiar with. I mean, you can see with your eyes with the shortest path, let's see. But as an algorithm, it's not having the short path. So the jump size, it's considered as a linear, as a learning rate. But before this, let me just go to that. So this is the formula of calculating the loss function. Now I need now to find the gradient of each variable. So as you can see here, this is the formula. It's the same here. I'll just move down. And I would like to find the derivative of this formula here with respect with beta 0. So I'll give here one example here. Let's just consider as f of x is equal x2. And the derivative of the first derivative of this, you will have to move this 2 to here, 2 for instance, and x will be 2 minus 1, so 2x. This is the derivative of x2 x squared. It's the same as here. You can try to ignore this. Let me just focus on this part here. Now we need to find the derivative of this formula here with respect to b0, but because we have 2 here, I will try to move this 2 to here, right? And this will be the same as x, for instance, and this minus 1, it will be the derivative of 1. And this will be the same in all the derivatives. So in the next derivative, I will, let's say I have this, and the derivative, then the next let me just copy let me just copy this. Hopefully it will be clear for you. Yeah, I have to copy the whole. It's not that easy to modify the formula, but no, I will have to copy, and let's see, paste. It's not showing the formula. Anyway, and let's see, you will have this from here. I mean, after the first derivative, I mean, not the first, after the moving the 2 to here, you will have only yi minus beta 0. And now what is this formula here? What is the derivative with respect of beta 0? So this will be minus 1, and the constant will be 0. Any constant, it will be 0. And this will be 1. So that's why we have minus 1. And because we have here 2, it will be removed with this. And it will be 1 divided by m. And I have the minus here because we have the minus of the beta 0. And it's almost the same for the beta 1. You can see beta 0, it will be 0. And beta 1, I have only x1i. And beta 0, it will be 0. I mean, beta 2, it will be 0. The derivative of constant, it will be 0. And that's why I have here multiplied, because here I have minus, it will be multiplied by minus xi. And the second one, I mean the third one is beta 2. Consider this as, this will be as constant 0 minus 0 plus, but because it will be here minus, I mean minus 0 minus x2. That's why we have multiplied by x2, right? I mean, if you haven't understand this, please write it down in the comment. I will try to update to find, let's see, a way how to explain in a much easier way. Now, as I said in the beginning, we have now calculated the gradient of each variable. What is the gradient? So the gradient is considered as what is the participation of this, let's say, variable to solve the issue. Okay, and consider beta 0 and beta 1 and beta 2 as steps, as not as steps, but as a parameter to reduce the error. Okay, now after calculating the gradient, I will try to update the beta 0, beta 1, and beta 2, right? So beta 0, it will be the beta 0, the old one, the old value, what was 0 in the beginning, but we will see it, minus the derivative of the gradient with respect of 0. I mean this value, this formula here. We will try to find this, and it's my beta 0 minus alpha. Alpha is the learning rate. Let's see the jump, how the step size. Let's see. For instance, if you are in the mountain, let's see, just in the mountain, and you have, let's see, did a big jump, for instance, in this direction, a big jump, but you will find afterwards, no, this is a wrong direction. I have to go to the, let's say, for the left. Now, to avoid this error, we need to make small steps. So try to make for small steps. And if you, let's say, move in the wrong direction, it's easy for you to go back instead of if you made a big jump. Now it's almost the same as beta. I mean, this is the update, and this is really, I mean, the same for the all parameters. Now let me just, since in the beginning we have said in the beginning 0, beta 0, and beta 1, and beta's values are 0. So y, it will be 0, right? Now we need to update the values with, sorry, the values with respect with to these equations. Now, as you can see, I need to find the gradient of beta 0. Just use this formula here. It will be y0 minus the original y minus the y hat. And in this example, y hat is 0, right? It will be uh, this with the formula here. It will be minus 1 divided by m, where m is 5 in our case, 5 examples. Now open the brackets, this as this one here. 100, this is y, 100 minus 0, plus 150 minus 0, plus 160 minus, and etc. And the gradient of this will be 100 minus 164. Yeah, 46. And this is for the beta 0, right? And for the beta 1, you will do the same. It's, you can see here, I mean y, it's 120 minus 0 multiplied by x1, which x1 is, if you go back, x1 is 65, and the x2 is 20. But here we need only x1. And if you can see here, 120 multiplied by x1, which is 65. Then 150, I mean, plus 150 multiplied by 70, which is x1 as well. So this is 70. And the next one will be multiplied by 72, 86, and and etc. This is for the beta 1. Because beta 1 is, as you can see, beta 1 is related to x1. You can see here, beta 1 is related to x1. So I will just use x1 here. And beta 2 is related, oh, sorry, to x2. Hopefully this is also here. Oh, okay. Sorry for this mistake. It's really big mistake. But here in all equations, it's the same. I mean, it's right. Okay. Now let's go to beta 2. As you can see here, it will be 100, I mean, y 120, for instance, for the first example, 120 minus 0 multiplied by x2, which x2 in the first example in x2 will be 20. As I said, because beta 2 is related to x2, so I will ignore this x1. I will just use x2. And this now I will find the gradient, right? Now I would like to calculate the weight. So it will be the weight of beta 0. It will be, from the next example, from the next iteration will be beta 0, it was 0 in the beginning, minus the learning rate was 0.01, and multiply by this value we have seen here with the gradient. So this is, for instance, B0, and from the next iteration, from the next update, it will be B0, it will be 1.64, beta 1 will be 102, and etc. Now, from the next iteration, I will try to use the same as, I mean, the same formula. So you can see I have updated the formula here just to make sure that you uh, uh, just I mean my goal is to make you 100% understand everything I'm saying. No, as you can see now, the y hat, it will be beta 0, which will be this value, plus this value, and plus this value. It was only a beta 0, beta 1, beta 2, just replacing the values of this. Now, if you see, I will try to calculate y0, I mean y hat 1. So in the first example, you can see it was almost 0, right? And here we have now big values, because this values here, it's not that, let's see, good enough. But this for each sample, it will calculate the y hat. And again, we will try to calculate the residual x minus y hat, y minus y hat, and start and do the same stuff related to this. And I was trying and hoping that you understand this. And as I said in the beginning, this is the very basic of the deep learning. If you understand these concepts, I'm quite sure you will understand the stuff. And I have also write the same example here for the Python in a Python code. And of course, I will attach this with the video description, of course. As you can see here, this is for example, the prediction of 0, 0. In the beginning was beta 0, 0, 0. And the residual was, the prediction was 0, 0, 0, 0. And the residual, this is for instance, 100 y and y minus y hat. This is called residual, or the difference between the target, or let's say the real target, minus the predicted. And now we have the gradient of each beta, and we have the beta as well here. It's updated. You might see somehow there's some differences between the values we have extracted here. But of course, you know, the Python code, it's let's see, it's not that it's accurate. Of course, it's the same example, but sometimes it's used some other decimals. For instance, here you see it's 39 and point 2. Here it's different, but after many iterations, it will try to find the most relevant, let's see, values. And let me just see if I have 50 iteration. No, this is 20. 50 iterations, and let me just see here. Clay, oops, Python, and let me just copy the path of this file and right. So I have 50 iterations, and you can see. Let me just show you this. This is almost interesting. So from the beginning, as you can see, the residual was 100 in the first iteration. In the second iteration was too much. And the third iteration is also too much. And as you can see from each step to another one, it will be less. And you can see the residual is minus 2. It was here one. What was the value here? It was 2 million or 22 million. I don't know. And with every step, you will try to find the relative. I mean the good example, the good value of beta 0, beta 1, beta 2. And if you see here, I have now the value, the where I haven't printed the alpha and no, here's the alpha and beta. So this is, let's say, that the final beta parameters. And of course it's almost, you have the residual, it's still there. But if you would like to solve it in the beginning, you see, I have only 5 examples, so that's why it gave me somehow random data. But in your case, if you would like to have uh, of course you will have a big data, right? That's why we need to make it I will attach this code, and you can try it yourself and try to replace this with your data. Try to load it from file or from somewhere else. So try to find the beta and as you see, here I have two parameters, no, two values, and that's why I have only three values, three beta. If you have five, let's see, five variables, you will have six betas. If you have 10 variables, you will have 11 betas. So all of these will try to participate in finding the best fit to your data. Okay, and that's it for today. And if you like, if you like this video and it helps you, please subscribe and like. And of course, if you have any question, write it down below. I will answer it, of course. Thanks for watching and see you time. Hi everyone, welcome back to my channel. And in the last video, I showed you how the linear regression is working, and I provide step-by-step example with a numerical example, as you can see here. So if you haven't seen the previous video, please try to watch the previous video, and if you are not familiar with linear regression, and then come back to this lesson. So let's say after calculating in this video, we will try to dive in the performance matrices for linear regression. So whether you are building a model to predict house, let's say house prices, sales, or even someone weights. So if you are predicting continuous values, as you can see here, continuous values as numeric values. So you need to somehow evaluate the model. So in this case, we have three, let's say, key matrices. Is RMS, MAR, and R square score. So we will go through if one by one. So first, RMSA, which stands to root mean square error, as you can see here. So RMSA measure the average magnitude of the error between the predicted and actual values. So it's great to penalizing large error because it's squaring the residual before averaging them. So as you can see here is in this formula here. So we use this formula for the root mean square error. So let's say after the first iteration, right? So please, if you are not familiar, let's say with this stuff, watch the previous video. And let's say I have this weight. This is, let's say, a target, or it's called also a dependent variable, which means it depends on all of these variables here. So in this case, we have two. Let's see, and this is the actual value. And if we try to predict, for instance, let's say we have these two values here, and using the previous formula, let's just have a look here. For instance, this one here, and we get y hat. And now I have the actual values of y, which is here, and the predicted values of the y hat, which is extracted, or let's say calculated using this formula here, because only we have two variables. Now you can see that it's super easy. It's just y, for instance, 120 minus 125 plus the second one, 120 minus 155, and taking the average, for because here we have five values here, 1 2 3 4 5, y divided by 5, then calculating the plus, divide by 5, and then take the mean square root error, the let's see, the mean square of this 25. Okay, now let's see. Let's go to the next one. Next about MEA, which means mean absolute error. So in this one here, we can see we have the square, and also square root of the values of the difference. But here we have only taking the absolute value between the actual value and the predicted value. You can see 120, which is this one, minus this, and we have no square, no square root. So when we use, I mean, we will see it. So this I mean the mean absolute error, it's used when you want to treat all errors equaling, and here it's try to penalize the error before averaging. And let's go to the R square. So the R square, it's also called as coefficient of determination. So the R square measure how will the model explain the variance in the target values. So, and for this, it's ranging from 0 to 1, where 1 it means a perfect fit, sorry, and 0 means the model perform as well as the mean of the target values. And if it's less than 0, it's perform worse than the mean. So, and here you have the formula here is summation of y minus y hat square, then divided by y minus mean of y. So as you can see here, I have, for instance, the actual values and the predicted values here. So this one here, it's the mean of actual values. So you have to sum of this up and divide by number of these values. For instance, in our case, it's five values. As you can see here, just it's easy to find the mean of this of y. Now this is the formula. As you can see, it's just apply just use this numbers, and you can see r square it's 0.92, which means it's somehow, let's see, as assumption, it's a perfect fit. But one one hint here, because we have only using random data, let's say it's a view data, so we can't see the model is perfect or not. So it's just an example to show you how the performance matrices is working, and also the linear regression is working. And also here you can see root mean square is sensitive to outliers and give more weight to large errors. And the mean absolute error, it's robust to outliers and provide linear score. And also R square, it's explain how model capture the variance in the data. So for this, I have, for this matrices, you can use skyline matrices. So as I can show you here one example of this. All of these files will be attached in the Git, and I will give you the link below in the description. And you can see just, for instance, mean square error. You can use import it from this map from this lib, and just use it as it is. So you don't need to program from each matrices by your hand. So it just already exists. So now you might be wondering, when should I use each matrices? So as I mentioned in the brief in the slides, or let's see in the document. So mean square error, when you want to penalize large error model heavily, so you can use this mean square error. When you want to treat all errors equally, you can use mean absolute error. And when you would like to evaluate how well your model explains variance in the target values, you can use this R square. So each matrix has, let's say, strength and weakness, but it depends on your, let's say, needs or target, what you would like to. But usually, just try to use this mean square error, and I think that's it. And please, I spend more time just to prepare this tutorial and make it for easy for you to understand everything. And if you like this video, please subscribe and like this video. And if you have any also question, please write it down in the comment below. I will answer it. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. So in today's video, we'll try to dive into polynomial regression with gradient descent. And of course, I will provide example with a step by step with numerical examples, small numerical example. So in the last videos, we see how the linear regression is working. But as you can see here, for instance, you can see this diagram here. Uh, the data, let's say, is distributed with this way here, and it's not, let's say, easy to find the best fit with linear regression line. So the linear regression line is, for instance, for this equation here. But I already explained this in a very detailed way, so you can have a look in the previous video. And as I said, the data, you can't, let's say, draw a line that can cross for maybe cross the all data here with a line. So the next solution for this is we can use polynomial regression. So the polynomial regression, it's for instance can pass through this data here. And as you can see with this information here, we have, for instance, B0, beta 0 side and beta 1 plus x, multiplied by x1. And this is the square. We will add this to the equation, so to the data set. We will have example and it will show everything here. So when we would like to use a polynomial, so when your data, it's not, it's, let's say, complex and hard to find the line that cross the all data here. And sometimes the interaction between features could also make the prediction or the model is perfect. So we can use the polynomial. For instance, if you see, I have x1 here, and instead just of x1, I just add the x1 mal x1. And you can also combine many different features. For instance, x1 multiplied by x2. And this x1 and x2 are features from your dataset. We will go through this example, and don't worry. And when we need to use also when our data, it's not non-linear. So as you see it here in this example here, the data is distributed in a different ways, so it's hard to find a line. So in this example here, I will try to make it, let's say, short, because everything here is already explained. Only the periodic quadratic polynomial equation. So I will use the same data set here. As you can see here, this the weight, the age, and I mean height, weight, age, and weight. We would we try to find the best value or predict the right value for the weight once we have, let's see, height and age. But in this example here, I try to, let's see, to remove this, but it's not needed to remove any parameters here, any attribute. It's just as an example here. So instead of age, I just add x1 multiplied by x1, the same stuff. It means uh, height mal height. And this is only one example. It could be also possible to see y is equal beta 0 plus beta 1 multiplied by x plus beta 2 multiplied by x1 and x2, for instance, height and age, and plus blah blah blah. And this is only an example, so don't worry. And let's say just we need to define this is the problem, and we try this is the y, it's the weight that we would like to have. So as you can see here, I have this is the same data set here, but adding another column here, which is the square, the quadratic polynomial. And it's the same as I said in the beginning of the last video of the linear regression. We try to initialize this to 0. I mean, these parameters, all parameters are initialized to 0. Then we have this equation here, the cost equation. We're using here mean square error. We also covered this in the previous video as well. And this is the gradient descent update. So this is a beta 1, this is beta 0, beta 2. And this is only to calculate the gradient. And to update the weights, we use these equations here. So as I said in the beginning, if if you need to be familiar with this stuff, you please go to the previous or let's see linear regression video. I will try to add it in the description. And this is, for instance, and the iterations 2. So after having the calculating, for instance, the b0 and b1 and b2, the new values of these attributes, we need to add, for instance, it's really simple example here. But as I said, just go back to see the video, and we have to iterate this until we, let's say, reach the best fit to our data set. And let me just there are some advantages and disadvantages of using polynomial. So the polynomial, I mean, flexibility, it can be used for a wide range of relationships. So to relationship between the features. For instance, here it could be between height and age, height and some other parameters. Let's see. And yeah, and what is the disadvantage of this? Sometimes it could be somehow overfitting. As you can see, for instance, if we use a linear regression, for instance, this one here, right? And you can see it's cross. I mean, the data, it's not, let's see, fit because it's not, let's see, a linear distributed. And if you increase the degree of polynomial, it's for instance 3, you can see 3, it means, for instance, in this case I use 2 square. And 3, and you can see 3, it's somehow 3, the red one, it's better than the linear one. And when you go down and I mean increasing the linear polynomials degree, for instance 9, it will try to fit to pass through this data here. But now this is called overfitting. it will try to memorize all the data set in the training set. But once you have a test set, for instance, assume that we will have a point here. So it will be not predicted well because it's far away from the the line. And this is another one. As you can see here, if you use the linear regression, most of the data is far away from the line, this line here. And here, if we use linear polynomial degree 4, you can see somehow it's better. But if we use degree 20, it will be overfitting. And overfitting, it means the data set, the BOM model is working perfectly with the training data set. But for the validation or testing, it's working worse. So it's not working well. So, I mean, we come to the end of this lesson. So as you can see, I spent much time to prepare this document. So I will also try to share it in the in the in the description and give you a link to this. And also for the Python code, it's also doing the same as this file explained. So if you would like, also you can run use this code to run one to run the explanation. So it's the same as I have explained here. So it will help you also to debug if you would like to debug and see what are the values of each variable and what are the yeah, and also this will be attached also in the video in the description. And if you like this, please subscribe and hit the bell button and also like the video. And if, of course, if you have any question, just write it down in the comment below. I will answer it. Thanks for watching and see you next time. Everyone, welcome back to my channel. In today's video, we will go dive into logistic regression. So before diving into logistic regression equations and with examples, as you can see here, so what is the linear logistic regression and what is the difference between linear regression and logistic regression? So both algorithms are supervised learning, but linear regression is a regression. So with the class label is with the target or class label is a continuous value, but with the logistic regression, the class label or the target variable uh, is categorical. So logistic regression now is a supervised learning, but a classification, which is used to classify binary classification. So let's say, for instance, for the linear regression, we have to, let's say, draw a line that fit our data. This is the blue line here. And it's only, let's say, it's a straight line. And in logistic regression, we will try to make a class for each table, let's say. And with the to make this shape here, we have to use sigmoid function. We will go for one example in the in the next. So assume this is let's say this is your data here, and you would like to draw a linear regression. You will try to draw, for instance, line from here, a straight line from here, and split this data, right? This could work, but in our case, we need a classification. So for the classification, we need to use a logistic regression. And as you can see here, the logistic regression is trying to draw this line because we use the sigmoid function. So through this lecture, we will see what is how to, let's say, calculate the weights, how to use the data, how to calculate the weights, how to drive, make the derivative, and this is also example, easy example with numeric stuff, and also I have also a Python. Let me just prepare it. Yeah, and this is the Python code that reflects the same example that I'm using in this document. So let's get started. So assume that, I mean, this I just try to make it as a graph, so it will be easy for you to follow. So for instance, let me just see, we have this data set here. which has two variables: hours studied and previous exam score. So for instance, if the student studied 2 hours and he get in the exam 60 and he will not pass, so this is the class level, as I said. It's categorized. It's not, let's say, a values between. It's not, let's say, predicting the score. If we would like to predict the score, so the score will be here. So we will use linear regression. If we need only one value, yeah or yes or no, or for instance pass or not, we will use this linear logistic regression. So assume that we have only these two variables, and I just replace it with x1 and x2, and each, this is with the gradient descent, and each variable will be connected to the weight 1 for instance, and this is weight 2. Sorry, I just, this is the copy paste. Sometimes it's not okay, see, and this is weight 1 and weight 2, and this is weight 0. So now to get the prediction, we will try to use this formula here. Let me just zoom in, and this is the 0 1 plus 0 w1 multiplied by the x1 and etc. Now after getting this result, we will try to use the sigmoid function, and after calculating the sigmoid function, we will try to calculate the cost, the cost, yeah, function. So we will say why we need this cost. So for instance, assume that you have predicted here 1, but this is not 1. It's the actual label is 0. So we have to update the weight. So until we get the let's see the right value of the loss of the target. Now let's see. The goal is to build a logistic regression model that predict whether the student will pass or fail. So as you can see, the logistic regression is using this formula, this one here, which is called a sigmoid function, and this is the z. We have seen it here in the diagram. And in the beginning, we will try to initialize the weight in all of these are zeros. So if you see, if we have 0 here and 0 here and 0 here, z will be 0 value. I mean 0, right? And after that, we will try to use this sigmoid function. It will be 1, and this z, it will be minus 0. So all this formula here, it will be 0.5. So let's have a look. I will just go back to come back to this, the derivative. But let's have one example. Let's see. For instance, the student 1. It's 0, 0, 0. It will be, for instance, 0. This is 0 multiply 2, which is studied hours. You can see here. Let me just maybe copy this and put it down so we can see. So it's 2 multiply 0 and 60 multiply 0. It will be 0. And the sigmoid function will output 0.5. And we will do it for the second student. This one here, 3 and 75. It will be also 0. Because all these parameters are zeros, it will be the sigmoid function will be 0.5. And in here we need to calculate the gradient descent. So what the gradient descent is used to calculate. The idea here is to update the weights that we can get perfect let's see result. So for instance, we need to predict here 1 or 0, 1 or 0, and etc. And this is the functions that have been used for the gradient calculation. So by the way, this already explained in more details in the linear regression. So please do have a look in the video before. I will also attach it in the video description. So also, by the way, this talk much time to prepare this. So please make sure to subscribe and like this video. And this is the derivative, let's see, partial derivative of this equation here with respect to W0, and this is with respect W1 and W2. So by the end of this lecture, I will show you how the derivative was working. Let's see if you are interested. So just let me now continue with this, and we need to update, let's say, the weight for example for 0, and we will go here. This is the W0. It will be 1 divided by 4 because we have 4 students. And easy, let's see, equation. This is 0.5 minus 0. And you can see 0.5 minus 0 plus 0.5 minus 1. And let me just see this formula here. If our label, let's see, the actual label is 0, this one here, so this one will be, let's see, adding penalty to the weight. And if it's 1, this one will be 0, and this will be adding the penalty to the weights. So that's why we have used for this is for the class 0, and this is for the class 1. And calculating the gradient. This is for the 0, this is for 1, and for 2. Now we need to update. Updating the parameters, we will use this formula here. So the old weight minus alpha, which alpha is learning rate, and this is the derivative with respect to, let's see, W0, and W1 and W2. And we will update this weights. Let's see, this is the first weight is 0, this is 0.05, 0.625, and we will try now to repeat what we have done in the previous steps, say for instance here, and until we have, let's see, satisfied that our result is perfect. So as I said in the beginning, this already explained in the linear regression, so please have a look in there. So regarding the derivative here, so we have this, for instance, loss function, and we have this is the partial derivative with respect to W0, W1, and W2. How did we get this result? So if you are interested, let me just show you this. It's a step by step, hopefully. Let me just see, yes. So this is the loss function, right? And as you can see, this is the graph. So this is our loss function. The input to our loss function was a hypothesis, let's see, the sigmoid function, and the output is y. And here, the input is z, and the output, let's see, is is a sigmoid function. And this is the input is weights and input, and the output is z. So now we need to update this weights W1, W2, and W0. And please make sure that only we update the weights. The data here are fixed, so we don't need to update. It's not allowed to update the data. We only need to update the variables, the coefficient. Now we will start. If we would like to update this W1, we need to see where this W1 is used. Let's see, just for simplicity. So if you see, this W1 is used here, and because the result this used here, it will be also used here, right? Because it is also participate in the result, and also it will be used in the classification. Okay, and for the cost function. So now to get this weight, W1, that's the same mistake here. It should be W2. Not working. Sorry for this. Okay. Now, if we need to update this one, let's say, for instance, this is the with respect to W1. So if you see in this formula here, we have a roll chain derivative. So because W1, as I said, it's plus bit on all of these, we have to get the derivative of each previous step until getting to this one here. So we have to take the derivative of sigmoid function with respect to g, then z with respect to h0 or sigmoid function, then z w1 with respect to z, and etc. This is the z. So as you can see here, the derivative of g, or let's say of course function, with respect to w1, we will start from here. The cost function with respect to theta 0, or let's say sigmoid function, multiplied by the sigmoid function with respect to z, and here z with respect to w1. Okay, so let's just start with the first term here. Cost function, I mean g with respect to h0, sigmoid function. So as you can see here, for instance, this is the g, and this is the formula, cost function, right? Now we need to derive this, or derivative this, with respect to h, or sigmoid function. So where did we find h? It will be here, right? And one note, for instance, this is if you have a log, the derivative of log, it will be 1 divided by what is inside the log. It will be, this is for instance the log, and this is the derivative. And it's the same here, we have to see y multiplied, I mean y divided by what is the inside x, right? Is a sigmoid function, let's see. And we have removed this I because it's only, this is the general one, and after we have a summation, we will use the I. Then plus, we will have this 1 minus y. This is the log, the derivative of log, it's 1 divided 1 minus h. This is for the respect with h. Now we need to derive the h0 with respect to z. So for instance, we have, this is the formula here. What is the derivative of this? The derivative of this, I mean, you can derive by yourself, or so this is the derivative of the sigmoid function. Oops, no. This is the sigmoid function, and this is the derivative of the sigmoid function. And as you can see here, h of x, it's equal this one here. And if we try to get the exponential to z, we will get this one here. It's only a simple multiplication. Multiply this by this, and 1 is equal, this for instance is equal 1, and you can see take the h outside, the exponential outside, and you can see, you can get this. So it's hard, let's say, to explain this in a slide. It's need handwriting. If you are not, let's say, understanding this, please let me know, and I will try to write it. I mean, with handwriting, and of course step by step. And now, if we subtitle, for instance, this is easy. If we just replace this with this right hand, so it will be this one here, 1 minus h, and blah blah blah. And solving this equation, it will output this one here. So that's why we have the output is this one here. Now, regarding the z, so now we need the cost function, let's see, with respect to z. And with respect to z, it's this, we need this and this one, right? And this is the output. If you see, we multiplied this by this, and this one here, it's this is the result of this term, and this is the result of this term here. If we multiply it, we will have h of x minus y. Now we will go to the x0, I mean to w1. W1, it will have this term here. It's the cost with respect to to h, then h with respect to z, and then z with respect to w1, and we will have this formula here. It's the output of the previous one, and z. So if you see, this is the formula we need to drive with respect to w1. It will be only x1, and these terms, for instance, w0 and w2 are constant. It will be 0. So we will have only x1. So it will be x1, and we have this. It will be x1 half h of x 1 multiplied by 1 minus half x. So that's why we have formulas here. Where is this? Yeah, here. So I hope this is what will be clear to understand. And if you like this video, please subscribe and like this button. And if you have any question, just drop it in the comment below. I will answer it. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. So as I have promised, I will go through this list, or let's say syllabus, one by one. So currently I'm now on the decision tree. So the lesson of today is a decision tree. So let's just jump to the decision tree. So the decision tree is a supervised learning algorithm used for classification, and also it's used for a regression task. But in this example, I'm focusing on classification. So how the decision tree is work? As you can see here, it is splitting the data set into smaller subsets based on some features, and also continuous splitting until stopping, let's say, condition is met, or let's say after finishing the data set. So if you have, let's say, a data set like this, for instance, this here, our data set, the attributes are weather, time, and hungry. Let's see if the weather is sun and the time is greater than 30 minutes, let's see, and hungry, yes. So decision, he will take a bus, for instance. And if it's sun and less than 30 minutes and hungry, no, he will try to walk. And this data set, we will try to build the model that we will, let's say, reflect the decision tree, like, for instance, this one here. So what is the real, let's say, application of the decision tree? So the decision tree could be applied for, let's see, many applications, like loan approval in banking. If you would like to apply for, let's say, credit, so based on your, let's see, income and some other parameters, it will approve, it will give you yes or no. And for instance, this is diagnosis. So for one project I have done with MRI classification. So I have some images, extracting some features from these images, and the final decision is to see if the this build or MRI has a disease or not. Let's see, tumor or not, and many other functions. So why we need to let's say, to use a decision tree? It's easy to understand and interpret. I will give you also example and step by step how to construct the decision tree, and also it requires a little data processing, and also handling both numerical and categorical. So let me just go dive into the decision trees. For example, this is a decision tree. So how this is, for instance, we select the weather, and it also depends on your data. So how did you, let's say, select this weather? Why not time, or why not hungry? This, for instance, as you can see, this is a rectangle with blue is the parameter, the attributes. As you can see here, this is 1, 2, 3, and this is the decision, or let's say class label. And these values here, the last one here, is the class label. And these, for instance, these values here are the values of this, for instance, attribute. For instance, whether if it's sun, and if it's cloud, or if it's rain. So how to select this? Let's see how to choose the root node. So there's two methods. Let's see. It's information gain or Gini index. So this example also focusing on information gain. So let's say, for instance, in the beginning we need to calculate the entropy of the whole data set, of the entire data set. And as you can see here, it's summation of bi log to the base 2 bi, and bi is the portion of the ith class in the dataset, And the information gain is also measure the reduction in entropy after splitting the dataset based on the attribute. And you can see calculating the attribute of the variable for the subset of the dataset and try to let's see, reduce it from the entropy of the whole dataset. So let me just go into the example. It will be very easy for you. So first, let's say calculating the entropy of the entire data set. So this is our data set. It's just for simplicity. So it depends on your data set. But let's say here I have decisions. I mean, this is the class label. I have bus, 4 instances, 1, 2, 3, 4, and the walk is 2. And calculating the entropy of this data set, it will be minus this B is proportional, as I said, is not the probability, but the proportional of this class to the this data set. For instance, here I have 4 of 6, so it will be 4 divided by 6 log 2, and this is also the same, plus now I have for the second class it will be 2 of 6 let's see, walk. And this is the entropy class of this entire dataset. And if you have any other class, let's see, for instance, I have only here two classes. And in your case, if you have 3, 4, 5 classes, you will add it plus until getting the calculating the entropy for every class. Now let's see, after calculating the entropy, now I would like to select what is the best feature, let's see, to be in the root. As you can see, for instance, like this here. What is the features? This or this or this in our case. Now this is, we need to calculate the entropy for each attribute. So for instance, I will start with weather. And as you can see, weather, it has 2 sun. And one sun is bus and one sun is walk. So I will try also to calculate the entropy of this, of the sun. It's one of the 2 instances are bus, and one of the instances of the 2, let's see, as is a walk, and this is the entropy of, let's see, of the sun. And now we will go to the cloud. Cloud we have 2 as well. It's cloud, bus, and walk. It will be also the same. And now for the rain, it has 2 instances, but all of these 2 instances, let's see, belong to the bus class. So you can see the entropy will be 0. Now we need to multiply all and sum all of these and see the entropy of the weather itself. So this is the 2 divided by 6, because we have here the first entropy, the first let's see, instance of the walk. It's 2, and here 2, and here 2. And this is multiplied by the entropy. For instance, here is entropy 0, and here is 1, and here is 1. And this is, let's see, the entropy, the entropy of this data set with respect to this feature. Let's see weather. And the information gain, we will try to reduce, subtract the information, the entropy of the weather attribute from the old, let's say, the general, or the entropy of the whole of the classes, as you can calculate it here. Now we will do it for the time. It's exactly the same. So for instance, greater than 30, there are three instances, 1, 2, and 3. And all of these, let's see if you can see, the decision is taken to take a bus. And you can see the entropy is 0. And less than 30, it's also 3, but maybe walk and bus. And also the same as the entropy, the previous one. And if it's not, let's see, if I'm fast, you can just pause the video and try to calculate it yourself. And be sure this is already calculated exactly the same, correctly 100%, hopefully. And now we will go to the hungry class, the hungry attribute. Calculating the same, yes, as you can see here, yes. So yes, it's belong all the yes instances the class label is bus. For instance, yes is bus, 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 and calculating the entropy and also information gain. So now, as you can see here, after selecting how to select the attribute now, based on the information gain. For instance, here we have the information. The weather is 0.2, 0.4, and 0.54. And as you can see, all of these are the same. So you have the possibility to choose which one is the should choose. So by for instance. Now I will try to select, let's say, the time. And from the time you can see, as we have seen, the time greater than 30, all the instances have the bus. So you don't need to split the dataset again. So just take this 30, greater than 30, and it will take the bus, for instance. Now is we have two options in time, greater than 30 and less than 30. And if you have many others, it will be. So now, with respect to this one here, as you can see, time with time less than 30, less than 30, I will take this. It's walk and bus. For this, I can't see it. For instance, I just put the class label here as the bus, because as you can see here, greater than 30 bus, greater than 30 bus, greater than 30 then bus. So there's no other options. So I will just assign the bus class to this. So, and for this class less than 30, I have to split the dataset and just take this only the less than 30 data, 30 less than 30. As you can see here, I remove all the others that are relevant for me, and I just take the less than 30. Now I will try to go through this steps as from the beginning, calculating the entropy, calculating the information for each attribute, and etc. As you can see, it's almost the same, and you can see calculating the information gain for this, and you will also try to see what is the maximum, let's say, information gain. And you can select, for instance, less than 30, then you will you have to select one of these attributes, and etc. So this is let's see, a simple explanation. Continue until finishing the dataset. So now, what is the advantage of? Did I miss something here? No. The advantage of the decision tree is easy to interpret, handle categorical and numerical data, and can capture nonlinear relationship. But what is the disadvantage? It's somehow it's prone to overfitting. What is the overfitting? So the overfitting, our model is working on the training data set perfectly. Let's see with no, let's see perfect. And when I try to test the model, it's working worse. So this is called an overfitting, and overfitting could be let's say removed or over, reduced by regularization. So I have uploaded also some videos on the regularization for regarding the linear regression, and it's almost the same here. And if there's any changes in a small data set, in the data set, it will, you have to, the tree will be changed. And also it depends on the features in the data set. So I have also implemented the decision tree. Let me just share my code here. So this example here, I have seen an error here, huh? Okay. The item feature. And for this Python code, I have implemented without any, let's see, any packages. It's a pure Python. As you can see, entropy function, calculating the information gain, and finding the best features is only the feature. And here's a building the trees. Now, as you can also see, some, if you go to, no, this is a decision tree. Sorry, decision tree. So if you see that this is the implementation, pure implementation, just to show you how the everything is working. And also you can run this and debug if you see what are the values, and to make it, let's see, clear that you understand everything. It might be, let's see, if you are a student in the uni, they might give you a small data set to calculate, let's say, to construct a tree. So this will help you. And for the, let's see, if you have a big data set, you will try to load the data set here. This is with Skyline. You will try to load your data set. We will see in the coming videos how to load data and how to pre-processing the data in the real project. Let's see. And here you can see I have imported decision tree classifier, and you see everything is already implemented in this. Here is splitting the data. This is the decision tree classifier, and here you see fit, predict, and you can calculate the accuracy. And yeah, that's it for today. And I think I have covered everything for regarding the decision tree. And as you can see here, this indeed took a lot of time for me to prepare this tutorial. And so if you like it, please subscribe and like this video. And if, of course, if you have any question, drop it down in the comment below. I will go back and I will answer it. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. So in today's video, as I promised, I will go through the Naïve Bayes algorithm, how it's working, and I will provide you with, explain it with a simple example, and along with the Python code, with the pure Python, and also with the Skyline. And if you, let's go to this document here. Now you can see this is the prepared document with example, and I try to make it very easy for you to go through, or let's say to understand the basic, or the goal behind Naïve Bayes. So as you can see, it took a lot of time for me to prepare this. If you like this video, please subscribe and like the button, and hit the button. And if you have, of course, any question, just write it down in the comment below. Okay, so here you can see the Naïve Bayes. It's a classification. It's a supervised learning algorithm used to classify the data. And as you can see here, for instance, I have these shapes, and I will try to calculate. I will try to classify all these shapes into a different groups. Let's see, different classes here, as you can see, based on the probabilities. And you can see Naïve Bayes is a probabilistic machine learning algorithm based on Bayes' theorem. It's assume all the features are independent given in the class label. So the main, let's say, assumption, or for the Naïve Bayes is they said all the features are independent from each other, which sometimes it's not the case. So for example, time series, each parameter, it depends on the other. And what is the this equation here? So it's like the what is the probability of x to be in y? Let's see. And this is called posterior probability. This is the likelihood. What is the probability of x? Let's say the likelihood of x to be in y. And this is the prior probability of the class label here by y. And this is the evidence. And everything will be clear with the example. Don't worry. So you can see here, this is the equation, and the pi y of x, it's the probability of y given features x, and this is the probability of x occurring in y. What is the probability of, let's say, of x? That should be in y, and the probability of class y in the data set, this one here, and this is the probability of x across all the classes. So yeah, sometimes the text is not clear, but with the example you will understand it 100%. So types of Naïve Bayes are classified. It's Gaussian Naïve Bayes for numerical, and this is for text classification, multinomial Bayes, and spam detection, and also for binary classification. So let me just see. I have this data set here, right? And this is, you can see, if it's sunny and the temperature is hot, high, I mean, the humidity is high, the wind is weak, so Platon is no. So this is, let's say, a small data set. So it's not like, let's say, a decision tree, for instance, or let's say any other algorithm, for instance, linear regression. For in a linear regression, we try to find the best fit, or let's say the best parameter that can fit the data into a line with minimal distance. Oh, by the way, you can refer to the this lecture as well. And for this here, we will not, let's make it a simple. We will not build a model. So for instance, in a decision tree, we try to construct the tree. And once we have the a test example, it will just go through the tree. But here we will it's not like this. It will just as you can see here, this is my text data set, and I would like to classify, for instance, this text this column here. So for instance, its outlook is sunny, cold, high, strong, and what is the best, let's see, or the right class label or play tennis? Is it yes or no? So we need to calculate this. So based on this, as you can see in the beginning, we have to calculate the prior probability of classes, yes or no. For example, we have here two classes, yes or no. So total number of classes are 14. In instances where play tennis is yes 9 and no is 5. And you can see calculate the probability 9 divided by 14. This is the probability, and for the no class is 5 divided by 14. So this 14, as you see, this is number of instances, all of these instances, 14 sample. Now we need to calculate the likelihood for each feature. So the likelihood is this one here. Let's see for the features. I have seen the feature is outlook, temperature, humidity, and wind. For the for the let's see outlook, the class 1, 2, 3, 4, three classes, three yes and one is no. As you can see here, for instance, if we go to only out for the sunny, let's say go to the sunny, it is I mean outlook, number of outlook, it's 9. Sunny with sunny, for instance, 1, 2, 3, 4, 5, 5. Okay, I think I have made a mistake. Oh, no, everything is fine here. Okay, so let me just show you this. So you can see for the outlook, I will start with sunny. So you can see this sunny, this one here. Okay, this sunny here. It has yes, no. For instance, I have only yes, 1, and also this one here, 2. So that's, you can see, 2 divide by 9, number of yes is 2 divided by 9. And for the overcast, so overcast is 4 is yes. You can see 1, let's start from here, 1, 2, 3, 4. And all of these 4 are 4 cases. I mean, yes. So it will be 4 divided by 9. And raining, it will be 3 to divide by 9. And let's see to sunny. I mean, as you can see, rain and overcast, it's 9. And let's see, go to sunny. For the sunny, it's no. With the sunny is 1, 2, and 3. So 3 divided by 5, number of no classes, let's say instances. And for this, you'll try to see sunny is yes, cool yes, high yes, strong yes, and also the probability of yes. So then for the sunny, yes. I mean this is for the first example. Let's see, sunny yes. Not for the first example. Sorry, for this one here. For this example, let me just move it down. And you can see for the sunny. For the sunny, I have 2 of the sunny are yes, divided by 9 number of classes, and multiplied by cool. Cool it equal yes. You can see, for instance, cool for the other parameters 1, 2, and 3 cool, and etc. for the other classes, for the other, let's see, attributes, and the probability. Sorry, this for yes, and the probability of yes, it's 9 instances over of 14, and the probability of yes, it will be this one here. Now we will try to calculate the probability of no. It will be for the sunny no, how many instances? It will be 30 divided by 5. If you go to the data set, the sunny is no, belong to no class is 3. For instance, 1, let me just go to this, 1, 2, 2, and it should be 3. 1, 2, and 3. Yeah, 3 instances of the sunny is no. 3 divided by 5, 5 number of classes, and also multiplied by all of this. This is the probability of y of no class. This is 5 divided by 14, and this is the probability. Now we need to compare the classes, the probability. You can see which one is the greater, the maximum. So for instance, this is the maximum one here. So we will assign this class. So assign the play tennis to no class. So this is in the beginning we have said we need to classify this table, let's see, or for data. And as you can see here in the Naïve Bayes, we don't calculate, let's see, we don't construct, let's see, a model. It's just calculating on fly. And let's see, what is the advantage of Naïve Bayes? It's, as you can see, it's nothing. It's just super fast, efficient, and work also for a big data, for large data set. It's not like KNN. You need to compare all the instances and all the features of the training and calculating the distance through the whole data set. And also this is, you can read it, and the disadvantage of this is strong independent assumption. They said this features here, for instance, all these features are independent. This is let's see, the assumption, which is not right for the whole data set. And for the implementation, I have added here Naïve Bayes. So I have in the beginning I have implemented with pure Python, and what if you run this, you will get the same data as in the document, and plus the Skyline. So for the Skyline, let's say for the big data set, if you would like to use it in your projects, or I recommend you to use this part here, not the above one. So this one here is only for you to let's say to understand step by step and debug. And let's say this is not optimized as the Skyline. This is, I will say, this is my feeling. And yeah, so also this will be attached in the document, in the Git repo, so you can see it's already here, Naïve Bayes, and you can see this is the document. Yeah. And as you can see, this preparing this lecture, it took a lot, it took time for me. So if you like it, please subscribe and hit like button. And if you have, of course, any question, just drop it down in the comment below. Thanks for watching and see you next time. Hey everyone, welcome back to my channel. So in today's video, I will try to go dive with you with the support vector machine. I will try to make it very simple, and almost all the videos in YouTube, they just give you the equations, and sometimes it's not even clear. They just explain it as a theory. In this lecture or this lesson or video, I will try to make it very simple, and I'm quite sure that you will understand every step in this support vector machine. And of course, because I provide you with a small example, let's see, real time, not real example, but it's, as you can see, it's with everything and it's calculated, and I'm quite sure that you will understand everything here. So let's start with what is the support vector machine. By the way, this preparing this document, it took a lot of time for me from me. So if you like this, please subscribe and like the video, and also if you have any question, just drop it down in the comment below. So what is the support vector machine? So yeah, with the support vector machine, I will try to use a gradient descent, and this example also will be. If you understand everything here, you will understand the, let's say, the deep learning concept, I would say. So what is the support vector machine? Support vector machine, in the beginning, it's supervised learning algorithm, and it's used for classification and also used for the regression. And the idea or the goal behind this is to find the optimal hyperplane that maximize the separates different classes in a data set. So let's assume this in the previous video we have seen how to how the linear regression is working, and of course I give you an example. So the basic of the goal of the linear regression is just to split the data set into not splitting the data, sorry, it's drawing the line that fit all the data. And it's the same here. We need to draw a line, but the line is the idea is to split the data set. I mean, split to these classes. And if you see here, if I split this data, the line, if I draw a line, so by the way, we only need one line that generalized for the whole data set. So assume that I have this line here. And for the next time I have created this line here. For the third time, maybe I choose this line here. So what do you think, which one is the best? I will see none of these are okay. So why? So if you see, we need a hyperplane, like for instance, starting from here and splitting the data. This is, I mean, all these lines are splitting the data, right? But the problem is here that the distance between these and hyperplane is less, and the distance from this point are too much. So we need to make it, let's say, optimal hyperplane. So this is the hyperplane, and the goal behind this, or the difference between linear regression and this here, is we need to maximize the support, the margin. So what is the margin? As you can see, if I draw a line here, and any point from this class, let's say, I will try to draw a line parallel to this and cross this, for instance, the close point, this point, for instance, and the same for the other class, and the idea is to maximize this distance here between these two margins, margins, plus d and plus minus t. And now, if I have a point in the testing data set, it will go through. It will be here. I will classify it as as a circle. If it's not, if it's here, I will classify it as a as a rectangle or square. And if you go here, and this won't be able to classify, let's say, splitting the data set into two different classes. So let me just go back and go through the example. So I will try to, where's the data set? Okay, let me just copy this data because it's might be just for simplicity. Okay, so assume that I will apply for the classification for spam detection. Assume that you have receiving some emails, right? And sometimes the Yahoo or Gmail, they will move some emails to the spam folder. Why it is moving this? They are using the classifier. I don't know which one. Maybe support for commercial, any other classes, any classifier. But let's say this is the idea. So this is I have one email 1, 2, 3, 4, and I have free word frequency. For example, if you have a free, how many frequency of word occur in this email, and how many when word occur in this email. So, for example, 3 and 2, it will be classified as spam, and it will be moved to the spam folder. So let's start understanding the support for automation. As I said in the beginning, we have to try to create the hyperplane, which is similar, exactly the same as support vector machine. Sorry, the linear regression, and where the W's are the weight, or let's say the coefficient, and X1 and X2 are the features. So here just simplicity. I have used two features, 1, 2, and for you could use many features as you want. And this one here is a bias, and in the linear regression is called y-intercept. And for the classification, as you can see, y plus 1 if it's spam, and minus 1 if it's not spam. Plus 1 and minus 1. So let's say, I mean, for this, it's working as exactly the same as the linear regression. We will try to initialize the weight and b, and try to calculate, let's say, the cost or the loss, and we will try to update these parameters until we get the best, let's say, fit, or let's say the best accuracy. Now let me just maybe uh, see something about this gradient descent. The gradient descent is already described in the previous videos, but there are two steps for the not two steps, two algorithms, let's say, or approach to updating the gradient descent is stochastic gradient descent, which is update the weight and be after each training example. So with each example, for instance, after this one here, for the example, I will up I will update the weight, and the new weight will be used for this one here. And after this, I will update the weight, and the new weight will be used for this, and etc. This is called stochastic. And the batch gradient descent, it's updating the weight after, let's say, processing all training examples, or maybe a subset of the examples if you have a big data set. For this simplicity, I will try to use stochastic. It's gradient. It's hard to pronounce, but yeah. So as you can see, this is our loss function, and this term here is try to minimize the error, and this try to maximize the margin. As we see here, is trying to maximize the margin. So for instance, in the beginning, this is the margin, and the second one is this one. It's not that, let's say, optimal. I will try to make it bigger until we're getting this, let's say, the optimal one. Let me just go here, and you can see the W are the weights. You can already see this, and regularization parameter. This is the regularization parameter, so I will have it as 1. It's also already described in the regularization L1 and L2. So please have a look. And the Y is the class label. Let's say, for instance, in the beginning, I will assume the weight and B are zeros, and the learning, let's say, rate are 0.01. For this, I will use this example here, calculating Y hat. So for the example 1, let me just zoom out. For the example, when I will try to calculate b hat, y hat, it's w multiply w times x1 plus b. So it's not x1, it's x indeed. So it will be 0, the y 0 multiplied by the first the xy for instance here, plus 0 multiply times 2, plus the beta is 0, it will be 0. Now there are several steps for calculating for example for the first one. I calculating the prediction, then calculating the loss, and calculating compute the gradient, and also update the parameters. So now I will calculate the loss. So here is 0. I will apply this formula here, taking the maximum of 0 and 1 minus y and y hat. Y in my case is 1 and y hat is 0. So it will be 0, 1 minus 0. Let's see. The maximum of this, it will be 1. Calculating the gradient. And the gradient, it's like this. Take with respect to W1, I will try to use this if y is 1. I mean, the loss is 1. Or just use W as it is. Otherwise, let's see if it's 0. And with respect to B, it will be minus the regularization term C multiplied by the class label if it's 0, if it's greater than 0 or 1. So in my case here, as you can see, the loss function as is 1. So I will use this formula here for the W, and this is for B. So I will see the W minus the W in my case is 0, 0 minus C it's 1, Y is 1, and the X is 3 and 2. So this minus this, it will be minus 2 and minus 3. And for the B, I will use also this because the loss function is 1. It will be minus C multiplied by 1. Multiplied by 1, yeah. It will be minus 1. Now we need to update the parameters. The update parameters, it's the same as the linear regression. The new one is equal minus 1. The old one minus the learning rate and times this term here we have added here. So it will be the sum, I mean the weight, minus learning rate times the weight, let's say the gradient, this one here. It will be this one, right? So this is the new weight, W1 and W2. And the B, it will be 0.01. And I will do it for the next example. For the next example, it's 1 and 5, and the class label is minus 1. So what should I use for the weight? The weight should be used, I will use the new one here. That's why it's called stochastic gradient descent. It's like updating the weight after each example. This is the concept. And for this example 2, I will try to use the new weight, which is this, and this is the B. And do the same stuff here and updating the weight. And for this, I will have these two values here, the weight, and 0 for the B. And I will apply, I mean, I will do this for each example until finishing the dataset. Let's see. And this could be, for instance, after all processing steps, I will have the weight like this, for instance. Now this should be repeated several times until coverage, let's say, until getting the best result, or let's say minimum loss and maximize the margin. And this will be repeated several times. Let's say after 100 epoch, it will be this 0.5 and minus 0.2. This regarding the parameters. So for that, I also have a Python code for this. Was support for machine. Let's see. So you can see here I created a class, and the class parameters are learning rate, C, and number of ebooks, and also the weight and the bias, let's see, term. But now it's none in the beginning, and for the for the fit, or let's say for the training, it's for each ebook. Let's see for each example here, I will try to calculate compute the prediction, computing the hang loss, updating the gradient, and updating the weight and bias. Then for the second example, and for the until finishing the whole data set, I will update the weight and bias after each example. Now this will try to this for the first ebook, and I will try to run this several ebooks until getting, let's say, the best result. So you can see this is, if you run this, it's let's say very easy, let's see, to follow and also to debug it. So feel free to use this and debug it, and also use it in your examples. And yeah, as you can see, I have prepared these documents and it took a lot of time. So I have already covered this concept, let's see, of support vector machine in a super easy way. And yeah, if you like this video, please subscribe into my channel and like the video. And if you have, of course, any question, just drop it down below. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In the last video, I showed you how the support vector machine is working with really step-by-step example, numerical example. But as you might know, the support vector machine is only designed for binary classification. So what we can do if we have, let's say, multiple classes. So if you have multiple classes, we can have the solution like this. Let me just share the second document. So, as you can see here, yeah, as you can see here, let's see in this graph we have, let's see, three different classes. And as I said, this is the support vector machine is designed to for binary classification. So there are two or maybe more than two methods or strategies. Let's see, it's one versus rest, or let's say one versus all. So in the beginning, let's say I have three classes. I will just select the first one and as a positive, let's say, and the other classes as a negative, and try to classify, build the classifier here. And then take the second class, and all the other classes will be considered as a negative class. So it's like for each class we will train a binary classifier, and during the prediction, this is interesting. A class with highest confidence, it will be selected. So for instance, let's assume this, we have this. I'll just make it better zooming here. And assume that we have these three different classes here. This image is taken from Medium. And I would like to apply this one versus all. So it means I will try to split this. So for instance, snake and cat, it will be as one, considered as one class, and the dog will be considered as one class. As you can see here, this is one class and this is the other class. And for the next classifier, I will consider this, for instance, cat as a one and as a positive class, and this one as a negative class or another class. And the third classifier, I have this uh, snake as one class and the other objects, or let's say classes, as one class. So in total, we have three different classifiers. And for the production, if I have a new image, I will try to classify it with this classifier, this one here, and also with this one and this one. And once I have the, let's say, the probability, or maybe the confidence value, and based on the confidence value of these three different classifiers, I will select the highest one. So, for instance, if I have a dog, let's say a black dog, and I will try to classify with this, classify it with this one, and classify it with this classifier. And based on the high probability, I will try to select the class label of this black, let's say, dog. For instance, if this one here is the highest one, it will be considered as a dog. If not, it will be considered as maybe cat or maybe a snake. Depends on the data that you have been used. And yeah, and the second, I mean, yeah, during the, as I said, during the prediction, we will select the highest confidence. And the second object, the second strategy or method, it's one versus one. So assume that you have this image here. So this image also is taken from Medium, and you have these three different classes. Let's see. And what you have to do is using this one versus one. In total, we will have 6 different classifiers. So it will be uh, apple uh, against this banana, and banana against apple, and etc. So in total, we will have 6 different classifiers. And for the prediction, new data point will be classified with. So I have just copied with all, just copy, because copy paste is not that. And we'll classify with each classifier and select the highest, let's see, using the foot. And I think this is the let's see, the general, or let's say the short the introduction about this, or let's say multi-class classes. So because sometimes you just use the subnet vector machine with many different classes, let's say 2, 3, 4, 5, but you didn't know that the support vector machine is only designed for support for the binary classification, and how this is working. So as you can see here, this is the Python code. You have, for instance, to just uh, import the SVM from the Skyline, and here you have the decision function. And let's just jump to this. Hopefully, I can go to this. And we need to see what is the default value for this. Let's see the decision. Yeah. See, the decision is one versus all or rest. So it's the default one. It's used by, so in case you don't have, let's see, add this, for instance, if this is removed, it will even apply for multi-classes, but it will be used one versus rest. So that's why we have see the default one is this. And if you need to change it, for instance, you can just change one versus. You can see the parameters here. The parameter, the values, the expected values, it will be one versus one, on, or one versus rest, or one versus all. Yeah, and I think that's it for today, and thanks for watching, and see you next time. If you like, please, if you like the video, please subscribe and like the video, and like the button. And also, if you have any question, please write it down in the comment below. Thanks. Hi everyone, welcome back to my channel. So as I promised, I'm continuing now with the ML course with a simple numerical example of each algorithm. So I'm trying to simplify the concept and equations with a simple with numerical examples. So in today's video, I will try to dive into KNN, how it's working, or K nearest neighbor. So as you can see, all of this already covered, and plus the Python linear regression and others. So let me jump to the document. KNN. What is the KNN? So KNN is supervised learning that used to classify for the classification of, or even for the regression. It's try to find, let's say you have a point, you have a test example, and you would like to see what is the nearest class, or what is the nearest point to this points to this, let's say to this points. So I think this graph should be easy to follow. Let's see. So I have taken this from this website. So assume that you have, this is what the blue and red circles are the training data set. And for the test data set, let's say you have this data set, this table, let's say example, and you would like to see what is the closest or the nearest point to this point here. So as from this example, you can see this is the red point here. And if you have this, when we say the key is 1, the key, it means the closed number 1. And here you see you have key equal 3. And what is the closed 3? We can see this and this and this. But now we will see using the float, which class label should be used. For instance, here you have red and 2 blue. Then the class label should be blue, based on the majority. And if it's 4, you see 1, 2, 3, 4. But now this won't, let's see, be defined. So the one recommendation to use KNN, try to use an odd number, 3, 5, 9, and etc. So, and by the way, this KNN is called lazy linear because it's not building a model during the training. It's just storing the data set, and for the prediction, you have to calculate the distance from this point from the new point to the whole data set. It's called lazy linear. So it's not like, let's say, suppose vector machine or decision tree. In the training we have a build a model, and for the testing we just use this model. But here it's not using the model, creating, let's say, a model. And how is this working? So let's see. It just you need to choose number of closed. So don't if you didn't understand this theory, I will try to explain it here with equations and examples. So don't worry. So how it works? So as I said, we have to select number of key values as we have done it here. So you have to select, let's see, the close 3, 5, and points, and we use 3. It called the let's see, the key is the 3 close point, and we need to select the matrices, the metrics. So usually we use Euclidean distance and maybe Manhattan distance or many quiz key. Quiz key, it's Euclidean distance. I think it's a subset, or let's see, from the minus key, because it's used this square root, and minus key maybe it could be 3, 4, 5, 6. And let's see, here we have an example here. The goal, as I said in the beginning, KNN is not building a model. It's just calculating the distance from the point against the whole data set. Let's say we have this data set here, and we would like to classify this new fruit. Let's say here we have fruit, and we have weight in grams and sweetness, and this is a class label. Sorry, I have flow. And we need, let's see, to classify the new fruit which has these parameters here, let's say these attributes, and which class label should be used. So would we like to classify it as apple or orange? We will see. So let's consider key is equal 3. This is the primary, let's see, primary parameter, let's say, for the KNN. So, and this is the Euclidean distance. I will see x1 minus x2 plus y1 minus y2. So what is x1 and y2? And so x1 and y1, so you can see 1 is relevant to the point that we would like to classify. For instance, in this one here, this is x and this is y. And x2 and x2 and y2 are the coordinate of the training data set. Let's say we have this and this, x, y, and if you have many parameters, it's x2, y2, y3, y, and etc. So let's say I have, as I said, this is my point. I would like to find the class label that is relevant to this point. So it means the weight of this fruit is 165 and the sweetness is 7. So I will calculate the distance from this point to against all the training data set, which is indeed it takes much time if you have a big data set. So I recommend you not to use KNN. So I will calculate the distance. As you can see here, this is my x1 minus x2 plus y1 minus y2, and the distance will be 15. And calculate the distance with the same way against all members, or let's say all tables or all rows. And after calculating the distance from the whole the whole training data set, now you need to sort all of these distances. Let's say sorting all of these distances here, and select the close the three, or let's say the top closed 3 points. And so we have here 3 points. It's fruit 2, fruit 3, fruit 1. This is the closest point to this to the new point, to the prediction point. Let's see, fruit 2, fruit 3, fruit 1, I think. Yeah. Now, once we have this, we need to make, let's say, perform major, let's say, majority voting. So majority voting, it's like take the maximum class that has the maximum number. Let's say here we have 3 apples. So the maximum class, the maximum number of class, let's say it's apple, it has 3, of course. And you can see here apple is 3 and orange is 0. So we will take the maximum one. So here we have 3. And if it's, let's see if it's, if you have here orange 1 and you have 2, of course you will be able, you will choose apple for this. So it's like selecting the majority. So one question here, how to choose the best key? So there's indeed a problem for choosing the optimal key. So if you select, let's say, key equal 1, it will be highly sensitive to the noise, and maybe leading to overfitting. And if you choose large, let's say large key, it's also lead to underfitting. So the best way to choose it is use cross validation to find the optimal key. And now I have already prepared the Python code for this. Let me jump to the Python. And this example, it reflects exactly the same as the example in the document. So in case you would like to, let's see, make a debugging or to find, do it yourself. So here I have the buoyants. And for in reality, you need to load all of this data from a file, let's see. But this is for a simplicity. And here you have the data buoyants, and you have the Euclidean distance. We have to, we said we need to number of neighbors. It's defined as 3. We need to calculate the distance. Here we have Euclidean distance, and now I will calculate the distance from this point. Where is the point? Query point, this one here, against all the features, all the data sets. And the step 3 or 4, I will try to sort the distance based on the maximum number of distance. And here I will select the top, let's say, 3 distance, which is, key, which is 3. So it's from 0 to 3. And here you select the majority. And this will print the class of the new data. And this also only for the simplicity and for you just to understand how the KNN is working. And by using the sklearn, this is easy implementation. You just have the X and the Y, the class, let's say the data and the class label. And you have the new data buoyants. And you have, for instance, define the key nearest classifier, and the key and NN is 3 dot fit, and you can just predict the new classifier, the new point. So if you run this, you should have the same class label. It should be the same class label. You can see here, pure Python. So this is the pure Python. Its class label is Apple, and Skyline it's Apple as well. So this is I'm trying to make it. I try to make it. Let's see, very simple or simplified this with this examples. So indeed, this took a lot of time for me to prepare this. And if you like this, please subscribe and like the video if you like it. And if you have any question, of course, drop it down in the comment below. I will answer it. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, I will try to explain or show you the classification matrix or binary classification matrix. So let me just add these questions. Have you ever wondered how your email providers know which emails are spams? Sometimes you find in your spam folder some emails that are spam. Or how the doctor used AI to detect the disease like a cancer. Or maybe a bank, how banks identify fraud transaction in real time. So these are the example of binary classification, let's say, problems where a model predict one of the two outcomes: spam, let's say spam or not spam, cancer or not cancer, and fraud or not fraud. So this, let's say, how do we know if this model is doing a good job? So after training your model, so now let's say you move to the prediction before the production. So how do you know that if your model is doing perfect? So what if, let me just add this question, what if your email providers mark an important emails as spam? Or maybe what if a cancer detection model miss a tumor? So for instance, you put the image with a humor, let's say a disease, and the system said no, it's everything is fine, no disease. This is a big problem. And what if the fraud detection system flag, let's say a legitimate transaction? If you sometimes, let's say, some hackers are doing some transaction, online transactions, and the bank system said no, this is perfect, this is okay, while it's not. So here's the problem. So these mistakes can have a serious consequences. That's why we need, let's see, evaluation metrics to measure how well our models are performing. So today we are diving into the most important, let's say, matrices: precision, recall, F1, and the confusion matrix. Sorry. By the end of this video, you will not only understand these matrices, but you also know how to use them and when to use them to build a better model. So let's get started. So as you can see here in this image here, the during the training, let's assume this we are using linear regression or maybe support vector machine. It's just splitting the classes into different classes. I mean, the classes categorized into different classes: spam or not spam. Let's see. And during that prediction, you will use this model to predict, let's see, these messages here, and you will see here's the three okay and two spams. So this is the, let's say, the concept of how to evaluate your model, if your model is doing well or not. So let's say I will start with the confusion matrix. But before going to the confusion matrix, let's assume that our spam is the positive class and ham is the negative class. Why it's false here? Sorry for the mistake. Okay, and please keep in mind, if you have the precision and recall or maybe F1 score, it's only and only for positive class. So F1 and recall precision rock curve only focuses on the positive class and doesn't know, or let's say show how your model does on the negative class. So this is, please keep in your mind. So for instance, in this video, I'm assuming the spam is the positive class. And now I will calculate the precision and recall based on this assumption. And if you assume, if you change the positive class to, let's say, ham, so in this case, you will have a different calculation. So just please keep in mind, maybe this could be a interview question. And let's see, this is the confusion matrix. With this assumption, spam is a positive class. So here you have positive and true positive. It means the model correctly predict spam. So the true positive, the table, let's say the data I have, the email I have, it's spam. And true positive, it's classified as spam. And let's see false positive. Let's see false positive. False positive, the model incorrectly predicts spam. So for instance, the email is not spam, it's ham, but the model classified as spam. And in a false negative, the email itself, the actual email is negative, it's a spam, but it's classified as ham. And for the true negative, the email is ham and also classified as ham. So the confusion matrix, let's say the accuracy, it's just summation of this divided by the whole summation. Let's see the, sorry. Let's have a look in the equations. As you can see here, accuracy is true positive plus true negative divided by all values. True positive, false negative, and true negative, as you can see here. And here the precision and recall and F1. So the precision, this is after assumption. Our assumption as spam is the positive class. So you can see true positive. Now, if we change the positive class to ham, we'll have, as I said, different calculation. So the precision is measure the accuracy of the positive prediction. So and also its answer all of the emails predicted as spam. How many actually are spam? So let's see. Sorry, this is the spam classified, and here we have the spam true positive plus false positive. The ham emails that are classified as spam. And the goal of this, or when to use this, if the false positive, it costs high, let's see. So for instance, let's assume that one email is actually it's spam. No, sorry. Let's see the email, the one email is ham, and by the model is classified as spam, and it will be, let's see, moved to another folder, and it might be ignored or maybe deleted, while maybe it's important. So for this, we need to use a precision if we need to, let's say, reduce the false positive. And for the recall, it's called also sensitivity. It's measure the ability of the model to identify all positive instances, and it answer all the actual spam emails. How many did the model correctly identify? So in this recall, we try to reduce the false negative. What is the false negative again? The false negative, it's, let's say I have a spam email, and this spam email is classified by the model as ham, and it's moved to the, let's say, to the inbox. And when you click, let's see, or open this email, you will have some attack, I don't know. So it depends now when you decide to use precision and recall. And the F1 score, or it's called harmonic mean. You can see harmonic mean. It's a mean of a precision and recall. It's a balance between both metrics. and it's used, let's say, for a class distribution is unbalanced. So what does the unbalance means? Unbalance assume that you have a data set and you have, let's say, two classes, but the one class, positive or negative, is high. Let's say it's for the spam file, for the spam emails, you have 1000, and for the ham emails you have 10 or maybe 100. This is called unbalanced data set. And there's of course a solution how to solve this imbalanced data. So we will cover this in the next videos. And let's just give you an example here. So assume this is the actual label. I have my training, let's say my testing data set. I have the actual label. This is the email 1, 2, 3, 4, 5 till I don't know 20 or so. The first email is spam, and our model is predicted as a spam. So it means now true positive, right? So I will put here 1. Now the next email, its actual email is spam, but the prediction is spam. I mean, not but it means correctly classified. So I will see here 1. So now our email, or the email is ham. Oh, sorry. Our email is ham, but it's classified as spam. So in this case, what we should do? False. It will be false positive. It means the email was false. I mean, not including to the, it's including to the false class, but it's classified as a positive, right? So now we have here to increase the to put the 1 in the false positive. And let's see, spam. Yeah, spam. This one email here, it's called class. I mean, this is the actual email and classified as ham. So in this case, we have true, not true negative. It's a false negative. So this, it's the email is let's say as it should be positive, but it's classified as ham, and that's why we should see it false negative. It means it was true, but it's assigned to true, to false. And here you see accuracy is calculated, just sum up all of these true positive and true negative and false positive and false negative, and you can see accuracy it's 0.6, 0.6, let's say 0.60 or 60%, and the precision and recall is 26, I mean 62 and 67%, and the F score or harmonic mean is 0.6, 64. So now when, let's see, to use this, so I will recommend you to use only one, and at most, let's see, two matrices. Don't use all of this. So if you have a system, try to let's see, stuck with one that will generalize your performance. So for instance, accuracy, I will see accuracy, it's not a solution for all of these cases, as we have seen in the unbalanced data set. I think we have it here. So let's say this is the positive and we have the email. Well, so assume that we have 900 of spam and 100 of ham emails. So the classification, the classifier predict all the emails are as spam, and you can see we have a good accuracy, right? But the 100 spam is classified as I mean the 100 emails of the ham is classified as spam. But in this case, we have a good accuracy. But this is in case of unbalanced data set. So don't use accuracy on the unbalanced data set. So, and the question is now, when to use precision recall or F1? As I said, precision is important when the cost of the false positive is high. And in this case, for instance, you have a ham email, right? And our system, let's say we need a ham it has to be classified as ham. It's not supposed to be moved into a spam folder. So in this case, I will use precision. But in case I need to reduce, let's say, the false negative, to reduce false negative, I will try to use the recall. So the false negative, it means sometimes the spam folder, the spam emails is classified as a ham. And in this case, it might be a huge problem, let's say a big problem, because the spam folder, the spam email will be moved into your inbox. And when you open this, it might be attack or hack to your system. So it depends on this. Let's see. Let's give you an example. For instance, MRI images classifier. So sometimes, let's say, assume you have a system that predict the images as a tumor or not, positive or not positive, or negative. So if so, let's say just assume this. The images that we have is has a tumor. Okay. Now the system is classified as non-tumor. It's normal. So in this case, it's a big problem because the person here will be treated as okay, and after a while, he might be died. He might be died. And let's say go to the another example, the opposite case. If the images of the patient are, let's say, okay images. I mean, no images, no tumor, but the system is classified as a tumor. So in this case, it will be as a tumor, right? But it will be a shock for the patient maybe, but they will try to add to make another test to let's say be quite sure. I mean, manual test, right? And in this case, it's false positive. It might be okay, but false negative, it's a dangerous. And let me just move to the Python code as I promised for every lesson. So you can see here, you can use Sky learn matrices, classification report, and confusion matrix. So assume this is our labels. So we have these labels, and we have the prediction is our model, let's see, predicted these values here. In the next lesson, I will try to show you this real example of the spam and ham classifier, but only to give you a overview how to evaluate your system, how to see my system is working good. And this is a confusion matrix. It's a defined function here. You just input the true positive, the actual labels plus, I mean not plus, and the predicted ones. And you have the report as you can see here, not spam, precision, and recall. As you can see here, precision, recall, F1, and support is calculated two times. One for the one for the ham, and one for spam, as I have seen in the beginning. So we assume that the spam is positive and the ham is negative, and the program, or let's say the library, is calculating in both directions, not only one. So yeah, I think now it's I have finished this, and as you can see, it has take much time for me to prepare this. So please, if you like this, please subscribe, like the video, and of course, if you have any question, drop it in the comment below. I will answer. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. Have you ever wondered how your emails know which messages are spam and which one are, let's say, important, and this goes to the inbox? And have you also know how the Netflix recommend, let's say, the perfect show for you? So that's all about how your model can separate the right choices from the wrong ones. So, and that's where the ROC and AUC come in. So many people think, let's say, accuracy is enough to measure the model performance, but this is not always true, especially when you're dealing with, let's say, fraud detection, medical diagnosis, or spam filtering, and when you have, let's say, imbalancing data set. So in this video, I will try to break it down in a super simple way, as you can see, with real example and visualized. And I'm quite sure that you will never be confused about ROC and AUC again. So because this took much time, so if you like this, please subscribe into my channel and like this video. And of course, if you have any question, please write it down in the comment below. So the ROC, let's start now. The ROC curve and AUC are used for binary classification. So the ROC is called receiver operating characteristic. It's a curve is a graphical representation of the trade-off between true positive rate and false positive rate. And this is AUC, it's under area under the curve. So this is the area under the curve. We can calculate it and see how our model is good enough or not. And as you can see here, the AUC, if the AUC that we will calculate it in the section below. If it's 1, our model is perfect. If it's 0.5, it's randomly guessing, let's see. It is less than 0.5, it's not anymore. So it depends on AUC. If your model, let's say, greater than 0.5, I will say it should be, I mean, not okay, but you have to, let's say, improve the model, and 1S should be perfect. So let's assume that we have a positive, email spam email classification that I have also used for the previous video for the recall precision and accuracy and F1 score. So I'm assuming this positive class is a spam email and negative class are not spam, or let's say ham emails. And please keep in mind that F1 and recall and precision also focus only on one on the positive class and doesn't show how well your model does on the negative class. So if we are focusing now on the spam, and we see the spam is the positive class, so now the ROC, it will only show us the performance of our algorithm only on this class, and the ham, let's say, class, it won't be showed here. And you can also assign, let's say, change the positive class to ham and see what is the performance. So this it depends on you. And also this already covered in the last video. And let's say this is, let's see our emails here, email 1 and email 2 and email 3, and our class, sorry, our class for the first email is spam, and for the second email it's not spam or ham, and email 3 is spam, and etc. Now this is our predicted score. So how to get this predicted score? If we remember in logistic regression, our model is predicting a probability. This is, let's see, greater than 0.5, it should be 1, and less than 0.5, it should be 0, or let's see the other class. So now we have this, our, let's see, our model is predicting scores before the classification is predicting the scores. I will show you also in the code. And this, please keep in mind, this is not randomly generated. So this is predicted by the model. And as you also remember in the logistic regression, we said if the model is, if the prediction is greater than 0.5, we see this is, let's see, a spam. If it's less than 0.5, we see it's ham. But now we need to see what is the best threshold that can separate our spam and ham perfectly. So in this case, not only 0.5, it could be, let's say, 0.7, or it could be 0.9, or it could be I don't know, 0.4, let's see. And this we will cover in this lecture, how to choose the perfect let's see threshold. So for this calculation, we also need to calculate the true positive, false positive, false negative, and true positive. And also we need to calculate the true positive rate and false negative rate. And true positive rate is called also, by the way, recall or sensitivity. and this is the false positive rate. And as you can see, this is only a copy from this, so it's just to show you the data set. So now let's assume this is our prediction. This is on the validation or the test set. So now assume that our model for the for the first class is predicting 0.9, for the second 0.885, and etc. Now I will try to use these thresholds, all of these thresholds, and see how my model is separating these two classes. So I will start with point 0.9. Let's see here, for instance, point 0.9. And they have email 1, 2, 3, 4, 5 till 6, right? And why it's 1, 0, 1, 0, 1, 0. This is, let's see, spam, ham, spam, ham, spam, ham. And for the prediction, if I see from point 0.9 equal or greater 0.9, it should be spam. And if we see here, we have only this. So this email will classify it as spam. As you can see, spam, and the others is these probabilities less than 0.9. So it will be assigned to 0. Now let's calculate the true positive, false negative, and true negative. So as you can see here, this class was spam, or let's say positive. Now and calculated as positive, I mean predicted as positive, so it will be true positive. It's only one. And for the false negative, false positive, we have no false positive here. What is the false positive? If if the email is ham or not spam and classified as spam. As you can see here, this is 0, but it's predicted as 0, so it's not 1. So it's not, there's no false positive here. For the false negative, we have this spam here, but it's classified as 0. And this one here is classified as 0. So we have two false positive. And the false negative, this one is 0 and predicted as 0. 0 predicted as 0 and 0 predicted as 0. So we have 3. So I just try to simplify this, and we have to do all of this for the same for the all let's say thresholds. So we started with this one, and we have to do the same steps with the second threshold. And I have just prepared this table here. As you can see, yeah, I just forgot to mention this. The true positive rate and true and false positive rate, we can apply this here. So it should be true positive plus, for instance, we have 1 divided by 1 plus 1 plus 2. So it's 1 divided by 3. And it will be like this. True positive, it's recall, as I said, and this is false positive rate. And we have to, as I said, we have to do it for the all probabilities score for the whole data, let's say data we have predicted on. So it might be validation or test, not on the training data set. And now we have to draw this ROC curve. So as you can see, this is, for instance, false positive rate is starting with 0. I mean, not starting, it's 0, but the recall is 0.33. So we have 0, and we'll have, I made point here. And point, let's say, 33 here, and it will be also in 0.3. Now, and etc. And I need, let's say, to calculate this area. It's called an area under the curve. How to calculate this area under the curve? It's using the function called I can't pronounce it, but trapezoidal. Yeah, sorry for this rule. And it's like the false positive rate, the next false positive rate minus the previous one, and multiply by the true positive rate, the next true positive rate minus the previous one. So it's like starting from here. This minus this, multiply this minus this, divide by 2. Next, this minus this, multiply by this minus this, divide by 2. And this is just calculate the summation. And in our case, in our example, the the prediction, let's say the area under the curve, it's 67, which is not a perfect, but it's just because of this example here. So as I said here, for the function, you can use num by I to calculate the traps function. Let's see the area under the curve. But of course, there is also in a Python. I will show you in a moment. And let's see, an important question is when and when not to use the under the curve. So if you have unbalanced data set, don't use ROC because it will misleading the it will give you let's see a misleading result or performance. And if you have a balanced data set, you can use it. If you have imbalanced data set, try to use recall or precision. And yeah, you can see read it, all of this. If you have a model, some models are not predicting, let's say, a probability, so you can't use ROC. And for the fraud detection and medical tests, sometimes we have, let's say, a rare positive, which means, let's say, if you have MRI images, and for the MRI images, we are trying to classify if the MRI has a tumor or not, let's say, a disease. And for many cases, we have only rare positives, which it means rare, let's say, patients having the disease. And let me just move to the Python code. I'm not, let's say, I will not present the whole code for this, but to just show you what is how to calculate the ROC curve. And you can see here, I have the Y test. This is the class label, the actual class label of my test data. And this is the score that generated, or let's say, the result of the prediction. And here I have a positive class as a spam. And it depends on your case, as I said in the beginning of this video, you can choose whatever important label for you. And as you can see here, for instance, predict probability. The model can predict the probability, and for instance, for the support factor machine is uh, a decision function is used. But this I will cover the whole code in the next lesson. That's it for today, and if you like it, as I said, please subscribe into my channel and like the video. And if you have any question, drop it down in the comment below. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, I will try to make, let's say, a really project which is contains, let's say, a spam detection or let's say handling the text data or numerical data. And this I will show you step by step. But before going to the implementation, I have just in my mind. So, for instance, when you deal with machine learning, this is, or let's say the pipeline, the normal pipeline, and let's say assume that I have a data. Now I will pre-process the data, do the training, prediction, and the evaluation, right? And this is when I have only one, let's say, one data set or maybe one algorithm. So now if I am assuming that I'm using a support factor machine for spam email detection. So next, what I would like to, let's say, to apply the decision tree on the same data set. What will I have to do? I will just have to change the training algorithm, right? And for the beginner, let's see, he will duplicate. Let me just. He will duplicate this implementation, which is, let's say, it could, for instance, it could work. I mean, it should work, but the problem now here is duplicating the code. It's not easy. Let's say after a while, it's not easy to maintain. It's not easy to extend it. And assume that you will use, for instance, logistic regression.
you will duplicate the same code. So now the idea here, I'm just showing you real project plus the right structure for your code. So as I said, this is let's say the normal pipeline. But before this, I have, for instance, I need a data, right? And the data could be text, numerical, images, any other data, let's say, type. And the pre-processing, each data type, it's need a pre-processing, its own pre-processing. For instance, for numerical data, you need to take the mean, median, max, I don't know. And for the text, you need to convert the text to vectorization and do this processing. And regarding the algorithm, some algorithm has several, let's say, parameters and different, let's say, prediction. So this has to be, let's see, taken into account before the implementation. So let me just show you this diagram. This has to be deleted. Okay, let me just remove this. Now, as you can see, this is the pipeline. So load the data, pre-process, split the data into train and test, training the model, make the prediction and evaluation. This is the normal pipeline. This we have seen in the beginning. So now for the data, as I said, for the data, it could be I have different data sets. I mean different type of data sets, text, images, numerical, and etc. And also pre-processing. So now for the data pre-processing, you have to create abstract class. So abstract class has two, several functions. It depends on your needs. So for instance, what I have here, load data set from file from, let's see, in this, I'm just trying to have it from file, but in your case, maybe in the future, I will try to update it to have a data from TCP protocol, or maybe from directly from a camera, or it depends, or maybe from the any endpoint. So let's say I have this data base data handler. This is only, let's say, the base class of the data. And for the data here, I have a spam data and resign data set. So it's only just to show you the text and the numerical data set. So this both data sets have downloaded from the Kaggle. And this data, this spam class will be inherited from this, and it will try to use load, pre-processing, and the extract features and label will be, let's say, will be private. So plus public, and private minus is, let's say, private. And this, for instance, it has pre-processing, which is plus if it's transform. Sorry. And regarding this is, for example, from step 1 to 2, load and pre-process. Now this step it will be in the main, because try to split as much as you can. So don't try to put all of this code in one file. So indeed, if you would like to change, if I would like to change the data, let's say the pre-processing for this data, so I will just change only this part here, and the other bus will be as the same. Only this file here will be changed. And assume I'm trying to add, let's say, another matrices. I will just add it here directly without any changing of all of these components. So this is the advantage of a well structured. So in this case, I can reuse this code. It's support reusability, modularity. So this, for instance, is one modular, this one modular, and this one, etc. And as extensibility. So you can extend it to whatever you want. For instance, in this case, I will add here, for instance, image data handler. And if I have image data handler, I will load the images, let's say pre-processing the images, and after that, I will just put the data as a training and label, for instance. This is for classification. So let me jump to the code, and as you can see here, this is a base class. The base class has uh, two different, let's say, two or three, let's say four steps. Let me just zoom in and zoom out. So why I have, let's say, created a base class. The base class or using interfaces is like a contract. So it will make, let's say, your code very consistency. So if you use a training, if you use, let's say, decision tree, support vector machine, any other algorithm, they will have the same functions: train, evaluate, predict, and etc. And if you have, let's say, in case you need more other functions, you can make it as a private or maybe public in the child class or the derived class. So here I have the base class. So as you can see here, I have train, evaluate, and predict. And if I need to add another function, I will just add it easy here. And for the other function, it will be used directly. So I'm not quite sure if I need to explain this, but let me just do it. The video maybe will be a little bit long, but this is the training. This is the I'm using, by the way, the Skyline functions. But let me just close this, and let me just see. This is the base class train and predict. And by the way, this could be also more, let's say, organized. But this is, let's say, not the best, but it's good to have it. So now let me just go to the decision tree. So in the decision tree, there is a decision tree class file, which is already implemented in Skyline. And for the decision tree class, I have this. This is created by me. And in the decision tree, it's inherited from the base classifier. So what does that mean, inherited? So if it's inherited, it will have the train, evaluate, and predict, and these other functions. So I can use it with this function. And you can see here I have initialized the super class. Let's say the parent class with this super, and I have it has the type and the argument if you have arguments. And here I'm initializing the model here, and the model it's initialized by Skyline with this parameters. And this model here, as you can see, it's used in a base class. With sometimes you see where's this defined, for instance, with the model, and you see where this is defined. As you can see, it's not defined anywhere here. So it's just defined in this function, in this class, sorry, and it will be used. This module will try to use this train and fit and etc. And let me jump to the main, just to make it clear. So here I have created a classifier, and the parameters, I have no parameters for this classifier. As you can see, I defined it here. And the decision tree will go to the classifier, this one here, and create a decision tree classifier which is defined in Skyline. And with the classifier is used, so because I have used several classifiers here, so the classifier, as you can see, I can use train function, which is used in a base classifier. I can use the predict, which is also defined, all of these. And all of these functions, as you can see here, let me just, if I just see this one here, just to remove it to make it clear. So I have defined a classifier, which is initialized from this class, and now I can train, predict, and evaluate of this classifier here. And it's the same for the rest. If you see it, for the example, for the support vector machine, support, yeah, it's inherited from base classifier. so I can use the predict and evaluate. And it also the same as the decision tree. Now let's go to the data class. As you can see, I have a data class as a let's say interface class. I have I have seen this load data, which is for instance reading the data from CSV file, and extract the file, extract the functions. As you can see here, it's defined as a private, and it this function here, extract function, it depends on the data set itself. So I will not have any implementation for this, so it means I have AdaBoost. For the pre-processing as well, I have no processing specific processing for this. What I have done here, anything is common between all of these data, it will be, let's see, written here. If any data, if the data it has different pre-processing or different post-processing or different functionalities, just you need to add the functions, add pass, and this functions will be redefined, or let's say overwritten in the derived class. Let's let's have example. For instance, I have spam data handler based it, which is inherited from this, inherit all of these functions. And now, as you can see here, extract function, it will be written, overwritten, and I will have my implementation, let's see here, for the features. And for the pre-processing, I will have this. And for this data set, it's a numerical data set. I will just extract these features, and the pre-processing, it's just standard scalar. And yeah, so now if you see, I have in the main, I have defined this spam data. I'm using this now. Let's see. And if I run this, I will have, let me just base classes, base classifier. Let me just comment this out because it will show the plot and stop. Let's see at a certain point. Let me just run, and you can see this. It will start with the decision tree, I think. If we go to main, we can see which one is the first decision tree, the first one. And you can see here, for example, the decision tree, I have the confusion matrix classification report, and this is for the data. Oops. This is for the same data set. As you can see here, I'm using the spam data set. And now you can see which let's see classifier is the best. Try to compare the confusion matrix if your data is balanced. If the data is not balanced, try to use precision or recall or F1 score. And you can see here the AUC is, for instance, for support function machine is 1, which is perfect. That is, let's say our classifier or the support function machine is perfectly split these two classes perfectly. And let me just see, you would like to add it to use the resin dataset. For instance, I have the dataset here. I just need to copy this. And instead of this, I will just try to use this one here. Now it should work directly without any issues. I hope so. Because each data has the loading, I mean pre-processing. Okay, where's the? Okay, sorry, I have just add data. I have to remove one data directory. And you can see all the components, other components, I haven't touched anymore. So because it has to stay
the same. Okay, and you can see here it's none. This I will have a look why it's none. Yeah, this is I think one real project for the spam email detection. Okay, sorry, I haven't shown you the emails, right? Let me just go to the emails and see the dataset. As I said, the dataset is downloaded from the Kaggle, and you can see this is the spam. Let me just see. Um, Not spam. Let me just see where's the other class. Or each one message it has the class label. Let me just go here. So text spam subject. Okay, why it's not showing? Yeah, anyway, this is the dataset. Let's say extracted, downloaded from the Kaggle, and every email it has a class label. And if you go to classes, I mean data class, and you can see in the data handler, I have I have used this. This is the data, the text dot value, which is, and now it will be replace a spam with one or maybe a zero if it's ham or spam. And for the pre-processing, you need to count vectorize, which is, let's say, creating a bag of words for the whole data set. It will make it, because if you see in the text, every email or every has a different length. So to make it equal length, we need to use a bag of words. Let's see. And let me just run this and see what is in X and in Y. And I think this is, let's see, an overview. I have shown you a real example spam email detection plus the good structure for your data set. So I think this should be enough for today. And so you can see I have 5,000, almost 5,000, 6,000 message. You can see this is the Y, it's the class label. You can see spam, and also 6,000 messages. Sorry. Yeah. Okay, I think this is enough for today. And if you like it, please subscribe into my channel and like the video. And if you have, of course, any question, write it down below. I also upload this code to the Git, so you can have a look. I think it's already uploaded to the Git. Let me just check. Not yet. So I will just upload it right now. Okay, thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, I will show you how the multi-class classification works. I mean, of course, with example. And as you can see from this pipeline, it's the same as the binary classification. So you have a data, pre-process, training, and evaluation. This is the same for every step. And I also showed you in the previous video how to structure, let's say, your code. I mean, it might be, let's say in the beginning it might be hard, or let's say take time, but it will save you a much time in the future. So as you can see here, what I have done, I have added only a new data set. So the new data set, it's like, for instance, predictive maintenance.
So the predictive maintenance is in a key kaggle, as you can see, and it's supposed to, let's say, to detect the class of the device. But I think this is not a real data set because it's hard to find some data. But you can see here it's a synthetic data set, and it has the temperature of the device. There you can see here, for instance, I have downloaded this to my PC. And you can see this is the attributes that will try to classify, for instance, this product as a failure or non-failure or no failure. So, and of course you can download it from here. And what I have done, it's only adding a new class. I will show you in the code a new class of this data set, how to read it and how to pass this. And these other components I haven't touched because it's let's say well designed, so nothing need to be changed, only the data set here. And I will show you now. You can see this is the data class. This are the other classes we have tested last video, and this is the predictive maintenance. So it's nothing to change, but I have defined the function, which is you can define the function. You can even define it as a private if you want, but just let's keep it like this. And I have here encode. I dropped this index because it's not needed. It's only an index for these tables. And these, as you can see, features or let's see columns are categorical and are not let's see numerical values. So we need to encode these values with this, for instance, code. I have the categorical columns, type and product ID, and go through this and try to transform it to the numerical values. Now from in the main, I have, as you can see here, data class import. I have imported this predictive, but as you can see, I have changed this. It was, for instance, spam dataset, and this is, I will see, it's not a good solution to change it every time in this main. While main, I mean, I will say main, it's not, let's say, related to the core implementation. Main, you can change whatever you want in the main. It's not, let's say, related to the algorithms, the to the main core. So, for instance, the classifier won't be changed, the data, the decision tree, this won't be changed. But if you want, you can change only the main. But anyway, this implementation also it's still not optimal. We will in the next video I will try to optimize and add. And this, oops, sorry. So instead of having, let's see, for instance, I'm using now predictive maintenance. Next time I need to use the spam data. I have to change it here, which is, I will see, it's tedious work. So I will add the factory class for this, and it should work. And I will also add uh, a config file, and I will show you how to read the config file and assign the parameters and etc. Also, I will try to add log files. So yeah, let me just, I have read the data, as you can see, reading the data, and this won't be changed. So when I run this, I will have the result as expected. Yeah, okay. So let's start with the decision tree. As you can see, this is the confusion matrix of decision tree, and this is the precision and recall for each class. And now, based on your needs, as I said in the video of precision and recall and even ROC, the the precision and recall, it's only let's say calculated only for one class and ignore the other classes. So in case, for instance, it should, as you can see here, it showed you the position for each class. And now which one is important for you, you can try to focus on this. For instance, for me, it's the power failure. It's the most, let's say, dangerous one. So I will try to focus on this. Find, for instance, position and recall. And this is for the logistic regression support factor machine. And maybe, for instance, from the accuracy, all the All the classifiers have, let's say, divided, class except the decision tree, which is 99. It's almost one. But yeah, this is only how to show you in a, let's say, a diagonal overview. By the way, this code will be also, of course, uploaded to the Git as usual. Maybe I can show you where to find the Git. It's usually uh, it will be added in the video description, so no worries. So here you can find it, and you can see, for instance, supervised learning, and here you have the projects, yeah, classification projects. You can see it also here. Yeah, then I think we are at the end. So please, if you find this helpful, please subscribe to my channel and like the video. And if it means a lot to me. And of course, if you have any question, write it down in the comment below. I will answer it. Thanks for watching and see you next time.
Hey everyone, welcome back to my channel. In today's video, we will try to dive into key means clustering. And here's the objective of this lesson. Let's see, I will try to simplify this key means so you understand it 100%. So I will give you also numerical example step by step and plus the Python code. And I will try to select, let's say, not choose, let's say a real world, let's say example. So dive into key means. So key means clustering, it's unsupervised learning. So it's not like, let's say, support vector machine or any, let's say, decision tree or naive Bayes. So this key means it has, you have your data, but you don't have any class label. So your idea is here, it's to group all of these, let's say, data together. So it's, as I said, it's unsupervised learning, and this means it's work with unlabeled data. So key means help you to find, let's say, patterns. It groups similar data points together, and these groups are called clusters. For instance, here we have this called cluster. And it helps, let's say for the real example, it helps the customer segmentation. It's divided the customer into different groups. And based on these groups, let's say you can add your discounts, you can give some offers, and etc. So it's also using for the image comparison, because it's somehow cluster the similar data, and just you don't need to repeat all of these data. And for the anomaly, of course, for the anomaly detection, assume that you have some images, and let's see, OK images, or maybe MRI images, and you would like now to cluster the similar images together. And if you have a defected image, then this image will be assigned, let's say, to another cluster. Okay, then let's just dive into the how it's working. So it's simple algorithm indeed. So first, we choose the select number of clusters. Let me zoom in. We need to select the key number of clusters. So this we have to do it manually, unfortunately. But there's by end of this video, I will try to show you how to choose the optimal key. Yeah, maybe as a note, because this talk, preparing this tutorial, it took much time. So please subscribe to my channel if you are not subscribed, and like this video. And also, if you have, of course, any question, drop it in the comment below. So as I said, starting with selecting the number of clusters, then the second step is initialize centroid randomly to the to the clusters, and assign point, now the assigned point to the nearest centroid based on the distance, and recalculate this is iterative indeed. In the beginning, we have assigned two different, let's see, point into different to the clusters. Now we will calculate the distance to these clusters, or called centroid, and based on the distance, we will we assign the points to the clusters. Now we will also recalculate the centroids, and also do the assignment again. And If there's no changes, let's see, we can stop. And this is the final, let's see, result. If not, we will assign, not assign, we will recalculate the centroid and assign that again. And this is, I said, iterative way. So you can also stop when it's covered. I mean, no changes in the cluster assignment, or maybe you have number of iterations. Let's see, 100 iterations, or it depends on your needs. So let's have this example here. Assume that we have 6 customers here, and the annual income for this customer is 10,000, let's see, euros or dollars, and he is spending 30,000. Let's see, 30, spending a score out of 100. 30. This is the spending score. Now we would like to group all of these, let's see, these points into different clusters. So we have, let's see, 2 clusters here. So the idea is to cluster these customers into 2 different clusters. So in the beginning, as I said, we have randomly picked 2 initial centroid. Let's say, for instance, the first point here will be assigned to the first cluster, and the second point, not the second point, but this one here, 50 and 80, will be assigned to the cluster 2. So this called centroid. And if we have, let's see, many other data here, let's see, columns, this will be also, for instance, 10, 30, and 50, and 90, and depends on how many points how many features or columns do you have. So this will be extended, of course. Now, let's see, after assigning this, let's see, selecting the centroid of each cluster, now we will try to calculate the distance from each point here to this, to each centroid, and we will see which one is the least distance. So, for instance, I will calculate the distance even from the point to the same point. I mean, for the same centroid, because this one at the beginning it's selected as a centroid. So you can see the distance from here to here, it's 0 0.0. You can use Euclidean distance here. So it means 10 minus 10, so 10 the first point, minus 10 the centroid, the first point in the centroid. It's 0 plus 30 minus 30, it will be also 0. So that's why we have here 0. And the distance, this point, the distance to the second cluster, it will be 10 minus 50 square plus 30 minus 80 square. So, and you can select the root, square root. So this will be, let's say, 64. And now we will select the minimum distance here. The minimum distance is C1. So this, in the beginning it was assigned to cluster 1, but after calculating, this will be assigned to cluster 1. This, for instance, the cluster 2 and 1, and these are the 2 to the cluster 2. So we have this, for instance, the first assignment. Now we will calculate the mean of these points. So for instance, the mean of each points, let's see, find the new centroid by calculating the mean of these points. So for instance, in C1, cluster 1, I will try to calculate the mean of A and B. For instance, only A point and B points are assigned to cluster 1. So it means this point here, A and B. And sorry. And this is calculating the first point, the first point, the mean of the first point, and the mean of the second point. And now we have here the new centroid of the cluster 1. And here it's the C. Calculating this, the C. Let me just maybe copy this data here. And we can have maybe better understanding. So we have C, D, E, F points from here. So we'll calculate this. You will calculate this, the mean of these points from 30 to 55, and again you will calculate the mean from 60 to 85. So that's why we have here the new centroid of the cluster 1. As I said, if we have many columns here, it will be the number of points here, or let's say the number of is centroid. I mean, not centroid number. So here we have 2 points because we have only two columns. And again, we will use this centroid, the new centroid, and calculate again the distance for the whole data set. So again, we will calculate the distance from this point to the new centroid and this point to the new centroid, and we will see there's no changes in the let's say assignment. So in this case, we can stop because it's already covered convergence. So and this one way to stop after, let's say, no changes in the assignment, or maybe, as I said, after a certain time, a certain point of iteration. So this was, let's see, customer segmentation. So in this example, as you can see, for instance, cluster one, it's low income and low spending score. So it will be, let's say, called budget customers. And this one here, it's because we have it's a real, let's see, data set. This will be taken by the technical the stakeholder, let's say the name. And the cluster two, it's high income, high spending. So they are premium customers. So based on this, you can try to give some discount, or maybe let's see a top deal, let's see, for the customers. Depends on the customers. And for instance, for this customer, you can give better, let's see, deals. And for this, you can make some discounts. So we are talking now if it's, let's see, a website, or maybe even a customer in their banks. So now the good question here, or let's say the important question is how to select the right key in key means. So because if you have a data and you don't need to try, let's see, randomly number of clusters. I mean, sometimes when you have your data, you can expect, or let's see, you have, let's see, insight how many keys you would like to cluster this data. But if you are not able to do this, there's an one method is called elbow method, which is most popular. There are many different methods, but this is the only one. Not the only one. This is the most popular. So I have only used this when I have some when I use the clustering. So what is this? It's like calculating the mean for each. Let me just calculating the mean, the this the cluster, for instance, for with the one cluster, let's see, and you will calculate this called within cluster sum of square, and this is the data point, and this is the centroid of the cluster, and this is number of clusters. And you can see here it's like selecting the elbow. So the optimal key, let's see, it's when there's no significant let's see, improvement. As you can see, from this point to this, there was a big drop, let's see. And from these points, the change is not, let's say, reduced, it's not significant. So we will see, we will choose this for number of cluster 4. As you can see here, this is called elbow. And yeah, so k-means is a clustering that group the data based on the similarity. And by the way, you can use whatever you want for regarding the distance calculation. You can use cosine similarity. You can use Manhattan distance and others, and many others distance. And choosing the key, as we said, we have this is the best, let's say, uh, way to select the clusters. And let me just jump to the implementation. Okay, here's the mean. So I have written this let's see with pure Python, only with random and math, and this is with Skyline. So this one here is just for you, let's see, to make a debug and see how this is working. And if you would like just to use it and you don't need to understand any stuff here, you can just use the Skyline because this is more optimized. And if you have real, let's see, real data, don't use this implementation. It's you have to use this because this is the more optimized and also it's well known. Let's see, package in Python. Okay, and that's it for today. Yeah, by the way, maybe you will have a different result if you implement this and this because due to the randomness and yeah, because in the beginning, as you can see here, we see it select with the select random point cluster means yeah, you can see it's selecting random data to the clusters as a centroid. That's why we have, let's see, different result here. But this is the main concept, and I'm quite sure that you will understand it, let's see, with this, with the numerical example and plus the Python implementation here. Okay, so if you like it, please subscribe into my channel, and that means a lot to me, and also make me keep me motivated. And if you have any questions, just drop it down in the comment below. Thanks for watching, and see you next time. Everyone, welcome back to my channel. In today's video, we will dive into hierarchical clustering. And let me introduce this. Have you ever wondered how machine automatically group similar things together? Like how Netflix, let's say, recommend similar movies, or how Google Photos group people based on their face. So the secret behind all of these is the clustering. And today we are diving into the most powerful clustering method, which is hierarchical clustering, step by step with an easy to follow example. So by end of this video, you will not only understand how hierarchical clustering works, but also how to implement it in Python. And if you like this video, please subscribe to my channel and like this video. And if you have any question, of course, drop a comment below. I will answer it. So the clustering, let's see, what is the clustering? And also is already described in the key means clustering technique. Clustering is all about grouping similar data points together. So unlike classification, in the classification we have predefined labels, but clustering helps us to uncover hidden patterns in data. So in many, let's see, I will say real real time, let's say real projects. So most of the time you don't have the classes, so you need to, let's say, group these data together. And today I will see, as you can see here, we will try to dive into the hierarchical clustering. And what is there are two different types, let's just say main types of hierarchical clustering. And you can see here, for instance, we have these data here, and the main goal is to group similar let's say data into a similar cluster. Let's say, for instance, A and B will be grouped in one cluster, and then A and B will be grouped with C and D in one cluster. Let's say here, and until getting the the whole data will be in one cluster. So in the beginning, it assumed that every data it will be in one cluster. But here's the two main types of the hierarchical clustering. Agglomerative, it's a bottom up. So it's starting with this from here until getting the cluster into merge all the clusters into one cluster. So it start with each data point as in its own cluster, and iteratively merge the closest clusters. And top down is starting from, for instance, from here, and try to split the cluster to the individual clusters. But we will dive now into this bottom-up clustering technique. So as let's see how it's working just in a few words. So in the beginning, it will calculate the distance between points, then merge the similar close point together, and repeat until everything is in one cluster. So and after that, you will create this dendrogram. This called here dendrogram. Yeah. So let me just say I have this data here. I have a points from A to E, and I would like to cluster the similar points. And let's say building this hierarchical cluster. So in the beginning, I have this data set, and first I will compute the matrix, or let's see the distance matrix. So this distance matrix will have x x1 minus x2, or it's the same as if you see x2 minus x1, because here we have square, plus y2 minus y1 square. Now, because we have here only two features, let's see x and y, we have only this, the formula, the Claudian distance, only this. If you have many features, let's see, in your data you have different columns. So in this case, you will have many terms here. So the distance, let's see, I will calculate the distance from each point, from this point E against all the other points. As you can see here, for example, from A to E is 0. From A to B, the distance using this Euclidean distance will be 0.71. And as you can see here, this is the diagonal here. And the other one is the similar to this is a symmetric, let's see. And as you can see here, this A to B and B to E, it's the C, because it's a distance. And for instance, the other one, A to C, and you can see C to E, it's the same distance. So we will focus, let's see, only on this up diagonal. Now, after calculating the distance, we will try to see what is the minimum, let's see, distance. And from this table here, we see the minimum distance, it's A to B. And we will select this as this, because then A and B will be in the same cluster. As you can see here, we will merge A and B into one cluster. So we have here clusters A and B. Yeah, by the way, in the beginning we said each point should be in one cluster. Now after the first iteration, we have A and B one cluster, C, D, E, and this is the point belong to this cluster. Now we need to update the distance matrix. So because here we will ignore the first data set, let's say, not ignoring, but here we will calculate E and B to the C and also to D and E with the same matrix, of course. So for example, distance between E and B and C, we will start to calculate the distance from this point to C. And because we have A and B in one cluster, we will try to calculate the distance from A to C and E and B to C. And we will select the minimum, let's see, distance. It's, for instance, cluster B and C. Now we will calculate the E and B to the D and etc. It's the same as previous one. And you can see here, I have the distance, the minimum distance is 1 between D and E, and also you can see here E and D, it should be also 1. So I will now merge D and E in one cluster, and we will repeat this process until we have building the dendrogram. Also, let's see here we have A and B to C, and I mean A and B in one cluster, C in its cluster, and D and E. And we also calculate the same distance using this. For instance, A and B to D and E. So we calculate the distance from A to D, A to E, and B E, and see the minimum distance, and see, for instance, here we have that C should be, for instance, merged with, let's see, grouped with the DE cluster. And etc. As you can see here, this is the final, because here we have, it's not the same data. I will show you in the Python code. And finally, we will have the all data points in one cluster. And here we can see what is the real world application for this hierarchical clustering. Is biology, classifying spaces into a taxonomy group based on genetic similarity. Social media, market segmentation is grouping customers based on purchase behavior. So the customer they buying, let's see, buying BCs, they will be in one group. Also, the document clusters. Sometimes it's hard if you have a big data set, if you have a big documents. It's hard to, let's say, to classify this, because you need to label every point, every document. But with the clustering, it will try to group the similar documents into a topic or categories. And also in image segmentation, grouping the pixels in in an image based on the similarity. And what is the limitation of this? So it's, as you can see, it's computationally extensive. The complexity is big O, and in trouble, and it's sensitive to noise, and also invertible mesh. So if you already mesh C and with DE, it's not able. It's not let's see. Possible to refit the measures. It's already done. And sometimes, let's say, I just give you this as a hint. Sometimes you will have the distance will be somehow similar to each other. For instance, you will have, just as an example, let me just go to this. For instance, the distance from A to B, it will be 0.71. And as an example, the distance from A to C will be of as well 0, 0 0.71. So you can just select randomly, or let's say the first occurrence as the merging. For instance, A and B will be in one cluster. But of course, you can see if they are the same distance, you can select A and B or A and C. But I think they just choose the first occurrence. And as you can see here, what is the advantage and disadvantage of I mean, what's comparing to a key means? In the key means, we need to identify how many clusters do we need. But here you can see it's trying to merging the data points into one cluster. But indeed, you also need, for instance, to stop these clusters. In this case, you will also need to identify the number of clusters, and or maybe the distance, the threshold distance. If the distance, for instance, let's say, for instance, the minimum distance here is 2.92, and you can see if the distance greater than 1.9, don't merge. So in this case, it will be stopped at certain point, for instance, here. Then let me show you the code. It's super easy. I mean, I use the SciPy package, and it has also dendrogram and everything. I also have the same example here, you can see. And if I just run this, you will see the points, the dendrogram as a figure or plot. You can see, for example, start from A and B, then C and D, and merging C and other into one cluster. So at the top, you will have all the data points belong to one cluster. Yeah, so now we have already done with this, and if you have any question, please drop it down in the comment below. And if you are not subscribed to my channel, please subscribe to my channel, and see you next time.
Hi everyone, welcome back to my channel. Imagine you are working with massive data set, let's say customer preferences or maybe social media or even satellite images or object detection or any of these algorithms, and you want to group, let's say, similar data points together. and to uncover hidden patterns. But how do you know if the clusters or the groups you already created are meaningful? And are they well separated, or let's say grouped? And are the points in each cluster are similar to each other? So a clustering algorithm, let's say like key means or hierarchical clustering. Let me just jump to the, let's say key mean or hierarchy clustering can help us to partition our data, but they don't guarantee a perfect result. So misplaced points or maybe poor defined clusters can lead to misleading insights. To avoid this, we need a way to evaluate the quality of our clusters. So, and this is what we will cover in this lesson. Let's see the clustering, the Silhouette score. This used to evaluate are your clustering algorithm is working well or not. So let me just jump to this document, and there are many. Let's see the three algorithms that can be used to or maybe to evaluate your cluster. Silhouette score, interior calculation, and also the clustering evaluation methods, some other methods. But today I'm trying to focus only on the first one. So how's the Silhouette score working? Is try to measure the similarity between the points in the same cluster, in one cluster, and also the inter-cluster similarity between different clusters. So in this case, we will assure that our clusters are, let's see, working well. So let's assume this, we have this data set here, small data set. I'm just giving it to make it more simple. And here you see, let's say we applied key means or hierarchical clustering, that we into to group these points into two clusters, and finally we have these two clusters. For example, cluster one contains point 1, point 2, point 3, and the other cluster point 4, point 4, 5, point 6. Now, the Silhouette, it's somehow sometimes it's hard to pronounce this. Silhouette score, it's measure how similar a data point in its own cluster compared to other clusters. So the value of the output of this algorithm, it's between 0 and between -1 and 1. So 1 indicate that point in is well clustered. So if you assign point to one cluster, for instance, this one here, and if it's 1, there's Silhouette score, so means this point is well clustered. And if it's 0, indicate the point is boundary in between two clusters. And if it's -1, it's randomly, it's wrong clustered. So let's see for each point in the data set. Let's see, for example, we have 6 data sets, and this data in this for each point we need to calculate the bi and b and a, and divide by max a and b. What is a and b? A is the average distance of point A I to all other points in the same cluster. Let's say, for instance, as we said, this our cluster one. So the A, it's the distance of from from B1 to B2 and B3, and the B, it's from the point in cluster one, for instance B1, to this 3 points in the cluster 2. So this is A and this is B. And let's say just go to the example here. For in the beginning, we need to calculate the A for each point in this in each cluster indeed. So let's see, we take the first cluster. Sorry. So as you can see, first cluster is B1, B2, B3. I will calculate the average distance from B1 to B3. So this is first calculate the distance from B1 to the B2 and B1 to the B3. You will have this result. Now we'll take the average. Because we have 2 points, we will divide by 2. And similarly, we need to also to calculate it for the B2 and B3. with the same steps here. So the distance from B2 to B1, B2 to B3. And for the B3, we will calculate B3 to B1 and B3 to B2. And taking also the average, we will get this result. Now we will do it for the cluster 2. And if you have many clusters, you will have repeat this several times. This is with this steps we calculate the A1, let's say average distance of point I. Now we will calculate B. So B, it means calculate the point to the other clusters, the distance to the other clusters. For instance, we have, let me just move this here, these two, just to see the points. So compute B, we will, for each point, we will start with B1 in the cluster 1 and calculate the distance against the all points in the second cluster. So B1 against distance from B1 to B4, B1 to B5, B1 to B6. And after that, we will take the average because we have 3 points. It's divided by 3. And similarly, we will do it for B2, B3, B4, and B5, B6, of course. So this is, for instance, for the first cluster, and this is for the second cluster. Yeah, this should be moved here. Sorry. Let's see here. So this is the first cluster, and this is the second cluster. And now we will compute the S. The S is the similar, the score. We will divide, I mean, this minus B minus E. So we have here, for instance, for the first point, we have 2 multiplied by square 2, the square root of the 2, and this 7 multiplied by square root of 2. And you can see this is A and this is B. Then B minus this divided by the maximum value, it will be 5 divided by 7. And we will also do it for the other points in all clusters. Let's say we have 2 clusters. We'll see B2, B3, B2, B5. Now we will calculate the solute score by taking the average of all of these scores. It will start with the first point till the 6 points and divide by 2. And this is let's see the average value of the score. And taking the average, it will be 0.7. So now this score is close to 1. So it's indicate it's a point is points, let's say, are well clustered. This is, let's say, the let's say numerical example of how it's working. And if you can also, if you see now the Python code, so you can import, I'm just using the key means for clustering, and here you can see you can import the data, you can import the algorithm to calculate the performance from here, from metrics. And for instance, you can see we cluster the data, and here we calculate the score. And you can see if we just run this, you can see we have a 0.488, which is, I would say, it's not a good performance, but because we have only a few data. So that's it for today. And please, if you like this video, please subscribe to my channel, like this video, and of course, if you have any question, please drop it down in the comment below. I will answer it, of course. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. Today we are diving into one of the most powerful tools in data science and machine learning, which is principal component analysis. So before jumping to into the code and math and let's say the numerical example, let me ask you some questions. Have you ever worked with a data set that has too many features? Or maybe have you dealing with hundreds or tons of variables and that
you ask your question, let's see yourself question, how do I apply machine learning for this big data set? So in this case, we have, let's see, principal component analysis. The principal component analysis it's let's see, is classified, or let's see, categorized as unsupervised learning. So if you see this course I'm doing right now, it's supervised learning, this one here, and it's as unsupervised learning. You can see, yeah, principal component analysis, or PCA. For the, so what is the main, let's see, goal behind the principal component analysis? It's try to minimize, let's say, to shrink number of features, or maybe extract features reduction, dimensionality reduction. So what are the steps of the principal components, or what are the keys in the principal component analysis? So the first one is variance. The variance is measure how spread our data belong to a particular, let's say, axis, or let's say, principal component. So in the principal component, we try to maximize the variance along new axis, new principal component. And the next one is covariance matrix. We try to measure the relationship between variables in the data set. And the eigenfactor and the eigen values. The eigenfactor represent the eigenvalues represent the amount of variance captured by each principal component, and the eigenfactor define the direction of the principal component. For instance, this principal component is in this direction, and this one is in this direction. And if you see here the principal, let's see, or the if you have a principal component in this direction, the other one has to be perpendicular, or to this principal component. So that's why we need to capture all the variance in the data set. And let's now jump a little before this, and the explained variance ratio. So the explained variance ratio, it tell you how much of the total variance is captured by each principal component. This we will see by example. So assume that we have this data set here, feature 1 and feature 2, or x1 and x2. And before this, we need to standardize the data. To standardize the data, we need to calculate the mean and covariance, the mean and variance for standard deviation for the data set. For instance, we have this data here. It's the same as just copy, and we calculate the mean for each feature. Let's say for the feature 1 we have the mean is 6. For the feature 2 we have the mean of the standard deviation. Okay, sorry. This is the mean of the first column, and this is the standard deviation of the first column, of course. For the second feature, we need to calculate the mean and also the standard deviation. And if you see the standard the standard deviation is the value, the features, for instance, 2 minus the mean square plus the second value, for instance, 4 minus the mean, which you call mu, minus 6, and all these divided by number of samples. And we will do it for each features. For instance, because here we have only two features, feature 1 and feature 2, we have only mean 1, mean 2, and standard deviation 1, standard deviation 2. And you can see here, for instance, now we need to standardize the data. We will have, as I explained here, we will have 2 minus 6 divided by the standard deviation. If you can see here, z, we will need to calculate now z for the first features and z for the second feature, the same z. And it's, you can see, 2 for the first value minus the mu, which is the mean of the first column, 6, divided by the standard deviation of the first column. And do it for the all features in your data set. I just keep it simple here. Now we need to calculate the covariance. The covariance, as I said, it's just capture the relationship between two variables. And the covariance you can calculate with this equation here, and the z, the covariance is the variance of the z1 and covariance of z1 and z2, and also this one will be the same, and Z2 and Z1, but it's the same. And the variance will be in diagonal, and the covariance will be in the other values, let's say, or cells. And the covariance, we will calculate covariance, just double the values of in this features here, divided by number of features, or maybe number of features not minus 1, because this number of samples minus 1. But I just keep it like this, 5, and I already did the calculation, so will be hard to change it. And this is for Z1, and you can calculate it for Z2. Now we can calculate the covariance matrix with this formula here, which is Z1 minus mu multiplied by Z1, and this formula here. And after that, we will have the covariance matrix like this. Now, from this covariance matrix, we will calculate the eigenvalue and eigenvectors. With eigenvalue and eigenvectors, for the eigenvalue, we need the determination of the eigen of this matrix. So you can see covariance matrix is this one, 1, 1, 1, 1, minus the lambda multiplied by identify matrix. So identify matrix is this one here, like this. For example, we have two features, it will be like this. If we have many features, all the diagonal will be 1 and the other will be zeros. And the determinant of this, it will be this multiply this minus this multiply this, and it will be like this. This is the equation, and you can see after what is the values makes, for example, this term equals 0. If we see 0, this will be 0. If we have 2, of course this term will be 0. So the eigenvalue will be 2 and 0. For now, we need to calculate the eigenfactor for each value, for each eigenvalues, eigenvalue. So this is the eigenvalue. For the x, for the lambda 1, we have it 2. So we will take this equation here and replace lambda with 2. As you can see here, lambda 1 minus 2, and here's still 1, and here 1, and here 1 minus 2. And this is our, let's see, matrices. We need to multiply this by this, because we have two values, two variables. It will be value 1, value 2. If you have, as I said, if you have many, you will have, of course, many, and of course, the matrix will be big. This is just how to make it simple for you. And if we multiply this row and this column, we will have this equation. Now we will multiply this row and this column, we will have this. And from this equation, if you see, we can say, for instance, V1 is equal V2 in both equations. So that's why we say V1 is equal V2. And for the eigenfactor, we say we just select 1, 1, 1, because V1 is equal V2. You can just do it 2 or 3 or 5, 4. But for let's say simple calculation, we just replace it with 1. For the 2 as well, we will have 1 minus 0. It will be 1, and here 1, 1 and 1 minus 0. And if you multiply this row in this column, and this row in this column, we will have these two equations. And from the calculation, we will see V1 is equal minus V2. And that's why we have 1 and minus 1. For the eigenvalue, we will sort the eigenvalue and eigenvectors. We have 2 and 0, and here 1, 1, and 1 minus 1. So how now we need to calculate? We need to transform the data into the principal component, and to transform the transform data will be standardized data, which is this one here. For instance, we have it in the beginning. This is the normalized data multiplied by the eigenvector, and for the eigenvector in the beginning we have 1, 1. For the first principal component, it will be Z1, this one here, multiplied by 1, and Z2 multiplied by 1. And now we can see the principal component 1, it will be Z1, plus z2. So for instance, this plus this. This way we'll have the principal component here, principal component 1. If we need principal component 2, we will do this 1 and minus 1, this one here. But this is because we only have two variables or two columns, we just to make it, let's see, simple. And I will select only the principal component 1. I just calculate the principal component 1. If you need principal component 2, it will be the same, but you need to replace the eigenvalues. Now, the total variance, as we said in the we mentioned in the beginning, that eigenvalues, it will be the total variance. So if you go here, I don't know where was this mentioned, but I hope it was mentioned here. The eigenvalue represents the amount of variance, yeah, I can say, captured by the principal component. And now here we have the total variance. Now we need to calculate the explained variance ratio for principal component 1. How much this principal component represents the data. So as you can see here, this is the equation, lambda 1 divided by total variance. It will be 2 divided by 2, it's 1. So it will be 100%. The principal component analysis is represented the whole data with 100%. This is not the case because we just have a small data set. But in your case, it will be certain percent, for instance, 90%, and the next one, it will be 2% or 30%. I don't know. And some other principal components will be 0, so we will ignore this. So now, as you can see here, we reduce the total the two-dimensional data set into one principal component, and we said principal component will capture the variance of 100%, and this one will be 0. Now this is our data set, will be used for the training. And you can see this is sample 1. In the beginning was so we will replace this data here. Let me just copy this and put it down. So in the beginning was this was our data set. Now the new data set will be this one here, and this will be used for the training. We'll feed this into the training, no, in the machine learning algorithm. So, and they have already provided a code for this. So you can see this is in this file you can calculate the principal component analysis either manually or using the Skyline package, and you can see the Skyline decomposite value decomposition. It's principal component analysis, and the principal component analysis is it's a subset, I will see, from the single decomposition value, singular decomposition value, and you can see this is calculated by NumPy, and this is calculated by Skyline. Of course, you will have some differences, but yeah, this is sometimes this is the case. And I think I'm getting the end of this video. So if you have any question, please write it down in the comment below. And if you are not subscribed, please subscribe to my channel and like this video, because preparing this document or this tutorial, it was taking much time. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, we will try to go dive into incremental principal component analysis. So imagine you are working with huge data set, let's say millions of records or images or maybe financial transactions. So the traditional PCA, the traditional principal component analysis, helps us, let's say, to reduce the dimensionality. But with this big data set, let's say it's required loading the whole data set into the memory, which is sometimes it's not practical for large data scale or large data application. This is impossible to load all the data set into the memory. Or maybe another example, if you have, let's say, streaming data. So maybe the whole data, it's not, let's say, already ready. So we got, let's see, some other data from social media networks, maybe sensors, and we would like to achieve the principal component analysis. With this stuff, we can use incremental principal component analysis. It's not like a normal or a standard PCE. The incremental PCA is learn from the new data step by step, so adapting without needing to recompute everything from scratch. So why it's important? Why the incremental PCA is important? If you have a big data, you would like to process the big data, so it helps you to process the data in chunks instead of all data in at once, or maybe as real-time data. So as I said, you get real data from the sensors, and for the scalability, it works even with a huge data set, and it's memory efficiency. So in this video, we'll go explore the how incremental PCA works, and I will break it down step by step using a clear numerical example and also including with the Python code. And I will show you how to compute and update the principal component incrementally. By end of this video, you will understand why incremental PCA it's not just a theoretical concept, it's a practical solution for handling real data challenges. So before going dive, if you are not subscribed to my channel, please subscribe to my channel because preparing this tutorial it took a lot of time. Okay, let's start. So as you can see, for example, from this image here, you have a lot of data. Sometimes, in reality, we have big data, let's say, collected every day. So to process this, we need somehow efficient way. So this is why we need incremental principal component analysis. So this example here from the Skyline website. I have also added the reference here. So this is applied for iris dataset with the standard principal component, and this is with the incremental dataset. And you can see there is no difference. So let's go dive into the incremental PCA, or it's also called IC. Let's see, IPCA. It's also called like this. So before this, before processing any data, we need to initialize something. The mean, the set number of, let's say, of the vector principal components, and the number of principal components. For instance, 1, 2, 3, 4. And in the first step, we will try to process the first batch. We have, let's say, a big data, and the first batch, let's say, it contains some rows or some data. We will calculate the mean, center the data uh, to the mean, and perform the first principal component analysis with singular value decomposition. And for the next step, for the next patch, we will try to update the weight and center the data based on the new weight and project the new data to the principal components, the OD calculated from the first patch, and reconstruct the data and calculating the residual, calculating the error of the principal component, then updating the principal component. So I try to write some examples here. It's just a short example. Let's see a simple example, but it will help you to understand the theory behind the principal component. By the way, the standard principal components already loaded, so please have a look because most of the stuff here it's already related to the already explained, let's say, in the standard PCA. So I have, for instance, X and Y. This is batch 1 and batch 2. Let's see, batch 2. And the whole data set is concatenating all of these data. So in the first step, we will calculate the mean of the first data here, the X, Xi, X1, let's see, and we will try to center this. So it's 1, the centering, it means 1, the first point, minus the mean. It will be 1 minus 1.5. And the second one, it will be 2 minus 3.5, and etc. You will do it for the all data, for the all data in the x1, and we will try to calculate the principal the the principal component using SVD, singular value decomposition. So let's say this is the Python code that you can do the singular value decomposition. And let's say assume this, we already got the result of this one here, and we will assume this is our principal component u. And for the second batch, we will calculate the mean. For instance, we have x1, x2. This is our second batch, and the mean of the two, it will be this one here. Let's see, and this is our mean one, and this is x1. Now we need to update the mean, so we make it as a global mean. So we will have this formula here, the number of points in the previous batch multiplied by the mean of the first batch, of course, plus the number of records in the second batch multiplied by the mean, divided by number of records. And you can see here, for instance, in our case, sorry, it's jumping. So if you see the x, we have 1, 2, and the second one is 1, 2, 2 rows. So that's why we have here 2 and 2, and here is the sum of 2, 2 plus 2. So now we will center the data, the mean, to the mean, and project x2, the centered x2, into the current PCA. But with this formula here, multiply the centered x2 multiplied by the already calculated u, or let's say principal component, from the first patch. Now we will try to reconstruct x2. So here we have calculated we projected the x2 to the into the current PCA, and we got this one here. Now we need to reconstruct from this. We would like to construct the x2, the center x2, and see if it's similar, or let's see if it's right, correct. Now we will construct this. Now we need to calculate the residual. So this is our x1, I mean x2 centered. Let's just get from here and minus the reconstructed. And you can see it's 0, 0, and we have this value here. We will try to update so this means it's the third principal component. It has let's say contribute, and we will try to repeat this several times until we get the final principal component. So let me just show you this, or maybe before that, let me just go to the incremental PCA. It's already implemented in this skyline, yeah. And you can see this is the example here. Let's try to load the iris data asset, but I already did it in a, let's see, in a different way. So I will show you how I did that. So let's see, we have loaded the data, and as I said, if we have big data, let's see, it's not let's see, possible to load the data. We will try to use a generator, or maybe loading reading from file, let's see, line by line, or patch by patch. This is only because the iris data, it's small. So the number of components we would like to extract is 2, and batch size is 10. So each time we will process 10 10 rows, let's see. And this is the incremental principal component, and from here fit in batch. So as you can see, the difference here, they directly use the X data, the whole X data, for the principal component. But in our case, it's I just add this batch in a for loop. So every time we'll try to partial fit the batch, and then after that it will transform to the data, the entire data set. And this is the second one, the second implementation. Let's see here is the principal component, the normal principal component or standard principal component. And here we try to visualize the data, to visualize the result of both incremental and the standard. And you can see, I can see any difference. Let's see. So that's why it's the incremental principal component, as it could work as the standard one. Let me just remove this. The breakpoint, yeah, it's already. This is the, sorry, this is the standard one, the standard PCA, and this is the, I can, okay, I can, yes. So you can see I can't have any difference. So this also proves that principal component analysis could work as a standard PCA. So, but the advantage of using incremental PCA, it's when you have a big data or you have a streaming. I think we got to the end of this. So if you like it, so everyone, welcome back to my channel. So far, we have already explored some amazing machine learning algorithms like decision tree and support vector machine regression or classification. But today we are diving into a new, let's say, advanced machine learning algorithm, which is, let's say, a more powerful algorithms that take the simplicity of decision trees and handle a complex problem with easy. So this is a random forest. I'm quite sure maybe you already heard about this. And imagine that you are, let's say, lost on in a forest, and you would like to find your way. So if you ask just one person for the directions, they might he might, let's say, lead to give you a wrong direction. But what about if you ask hundreds of people and take the most popular route? So it chances that you will find the right path. This is exactly how the random forest. And sometimes it's happened for me when I landed in a new city, and I ask for instance someone for the direction, and after a while, just maybe 1 minute, I will ask the second one, where's the direction? And just to be quite sure, because sometimes you will get lost if you didn't ask. And that's why I'm asking, let's say, two, three persons, and if the answers are similar, I will see, yeah, this is the right direction. If there's a conflict, I will just take the most, let's see, the foot, let's say, foot method. So, so now in today's video, I will explain how the random forest is working, and of course with Python code. And I will also upload the video and also the code. So please, if you like the video, please subscribe to my channel, like the video, and if you have, of course, any question, drop it down in the comment below. I will answer it. So this is, let's see, the outlines. So I will this is define the random forest, understanding the decision tree. This is we already covered in the last video. I will put the description in the I mean the link in the description, and how does this work, and step by step numerical example, and of course advantage and disadvantage. And I will also provide the code. And as you can see here, for instance, this is your data. This is taken from this website. You have this data set here, and you will try to build several decision trees, but in random, not on the whole data set, but in random, let's see, data. So this, for instance, tree will work on will be built on different, let's see, features. and rows, and this also will be built in different features or maybe rows. So I would say there's no, let's say, similarity between these data sets that used in each tree. This is the goal, let's see. And why we have, if you just remember from the decision tree, what the one the main disadvantage of decision tree is that we only build one tree for the whole data set, and this will lead to, let's say, overfitting. The overfitting is that the model will start to keep the memorize the data and not make it generalized. But here, if you see, we have different trees and trained on different subset of the data set, and that's why we will try to reduce or remove the overfit. So, and in the random forest, it's of course it's a machine learning and it's supervised learning used for classification or regression. And let's say that we have this data set here, a student, and from 1 to 10, and they have studied our attendance, previous exam score, and we will try to predict if he pass or fail. So based on this, we will try to create, let's see, bootstrap samples. Bootstrap, it's like decision tree. It's called bootstrap. But random forest use, as you can see, random forest use bagging. What is bagging? As I said, bagging, if you have many options in one hand, in your hand, and you will select, let's say, the most accurate one. So this means we will create multiple sub decision trees. For instance, let's see we have three different three decision trees. So as I said, it's called bootstrap. So 1, 2, 3, and as you can see here, for instance, we have this data set, and for instance, the first data set will be trained on this, let's see, rules. For instance, 1, 2, 3, 4, 5, till 10. And sometimes it will also, you will see some rules are repeated, maybe repeated. For instance, they will use 1, 1, 2, 3, 3, 4, 5, 5, and etc. This is because it's random. And for the second decision tree, I will take this one here. You can see it's randomly taken, and also this. And with this example, we'll try to build a decision tree. That's we already covered in the, as I said, in the previous video. And you could also not only randomly selecting the data set, subset of the data set, but also you can select random features, select random features. For instance, for the first tree, I will try to choose this and this, for instance, hours studied and attendance, and this will be ignored. And of course, class label will be used in each tree. And after, let's see, building the decision trees, now we would like, let's see, to predict, to make a prediction on this, for instance, on this data here. So we have our studied attendance, previous example, because I haven't built the each decision tree because it takes much time to build this. But the main idea is just to give you overview how this is working. And now let's see, we have three decision trees, and let's see, all these trees are, let's see, this is a prediction pass fail, and because of this, I will try to aggregate the prediction and select the most, let's see, popular one, or let's see, use majority voting, because here pass is more than fail. I will try to classify this data here as a pass. And yeah, this is, let's say, a key points of to remember. Maybe it will be used in be as a questions, how the decision tree is used to remove or eliminate the overfitting, because it uses many multiple trees, and each tree is trained randomly on a subset of the data or maybe a subset of the features. And the advantage, I mean, advantage is reduce overfitting, handle missing data. So what does that mean, handling missing data? So if you remember, in each data set, there might be missing data, right? And you would like to remove this data by filling this data with any data, any not random data, but maybe me taking the mean or median and replace the missing with these values. But for the random forest, it's not needed here. It will be automatically. For instance, let me just assume this. I have this hour studied, and let's assume this is empty, or let's say missing value for decision tree. It will try to see, will I be able to classify this without this missing value? If I have many missing values in this column here, it might be removed because it's randomly it work with some features. It might be removed, or maybe use the other one with more high important as a root. You can see decision tree taking the it use the select the entropy and the information gain to select the root of the tree. And I think this is enough for the theory. Let's see. And here I have the implementation. The implementation is similar to what I have in the document. So the same data set. It's just make to make it simple for you, and you can let's see, debug and see what is going on. And for the next video, I will show you how to use random forest in a real data set, let's say for spam detection or any other problems statement. And you can see here, this is the data, our data set that used in the document. And here I have the decision tree. Yeah, here's the decision tree. And number of estimators is this number of, let's see, decision trees. And we use this random state just to make the result reproducible every time. So if you run this one time, two, three, 10 times, you will get the same result. But without this, you will get a different result because it's randomly selected. And yeah, I think that is enough for today. Of course, I will push the document, the code, and video. And yeah, if you like this, please subscribe to my channel because preparing this document it took a lot of time. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, we will diving into the exciting, let's say, topic, integrating the random forest algorithm into a classification project. So the previous video I have uploaded was explaining or show you how the random forest is working, and now we need to integrate the code into this, let's say, pipeline. So whether you are, let's say, a beginner or experienced expert, so you need, let's say, somehow we will cover some professional and for code organization and evaluation techniques. So before we jump into this, as you can see this diagram here, sorry. So I have for instance many. Let's see, just zoom in. I have some algorithms, machine learning, for instance, decision tree, random forest, logistic regression and support vector machine. And now I need to add, let's say, a random forest. So because we are already, let's say, organize our code, I will just add one file in the project. So it's called random forest. So I will show you now in a minute. So let's see this. For instance, let me just show you the decision tree, for instance. So this decision tree, it inherit it inherits something from the base classifier, and here we initialize the decision tree classifier from the of the decision tree classifier. So this is already defined as it in the skyline. With the similar way, I will just it was just copy paste indeed. See, I have imported except this one here imported the random forest, which is an assemble algorithms, and here I initialize the random forest, and I just change this name here, random forest. That's it. This is what I have done here. It's just adding one file. So now the question is how to use this one here. So if you go to main file, this main file of the random forest, as you can see, this is only for debugging if you would like. So let me see the main file here. So the main file I have added uh, random forest. I have added this class, for instance, from this file, and imported this random forest. Now I just add this line here. You can see it's random forest called random forest. I just called random forest. Number of trees. This is the parameters you would like to add it here. Random forest is 3 and etc. And in here we need also to add if else. If it's random forest, just use the random forest classifier. Then the rest will stay the same. Let me just show you the changes here I have done. Adding the classifier that I have defined in this folder, in this file. Then adding the classifier as in a dictionary. Let's see, dictionary classifier, and this one here. And let me just show you this. This is because it's new, nothing changed. And indeed it's only two different changes. The one in a me, and they have only created this one here. And if I run this, let me just show you. If I run this, I will get the same. Oh, I close it. No, this mean if I run this code here, I will get the same. I mean, not the same result, but the result of each of these classifiers. They are defined in this classifier dictionary. Let me just run this, and you can see I will have no issues because everything is separated. And if you have any error in the random forest, you will just should focus. I mean, fix this in a random forest and nothing else. Let me just remove the breakpoints. So this is the advantage of well-organized, or let's say object-oriented programming. And you see here, with this here, the random forest classifier. You see. So this is to show you how to integrate any algorithm in this project. And if you would like to add any other algorithm, you just need to add another file here. Call it whatever you want, the algorithm name. Initialize inherited from here, and initialize the from the package. That's it. Okay, that's it for today. And if you like this video, please subscribe to my channel and like the video. And if you have any question, just drop it down. Of course, I will answer it. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. In today's video, I will try to show you how the add a post or adaptive posting algorithm is working. So as you can see here, if every day I upload a new video on this algorithms. So please try to have a look on this. So what is the AdaBoost? AdaBoost is ensemble learning techniques that take multiple weak classifiers that just slightly better than random guessing and combine them to form a strong classifier. It does this by focusing more on mistake of the previous classifiers, adjusting this importance in the learning process. So think of it like a team project. So imagine there's a group of students or maybe employees working on a specific problem. Each student might have different strength and weakness. Some might have some might struggle in let's see one area, while the other is perfect. And if they help each other by learning from past mistake, the team as a whole gets stronger. This is how post adaptive or adaptive posting works. So why it's important? Let's see. It because it turns the weak classifier into a powerful model. It focuses more on hard to classify symbols, refining, and its accuracy. Let's have a look here. For instance, this is how. Assume that you have a data set, and for the data set you will build several classifiers, weak classifiers, and this weak classifiers is let's see a specific special decision tree with only one node. You can see, for instance, here I have only one node, and this will be clear with the example. And they have, for instance, they have this weak classifier. Sorry, and they have the second classifier, and the second classifier will try to improve the data, the result, and etc. So I have here let's see a diagram. I hope it will try to be uh, to make it easier. So here I have initialized the weights and trained the weak classifier, or let's say learner, and he evaluate the error. As the error is high, so we have to increase the misclassified weights. Then try to train the weak learner, let's say, or classifier, and do it again until it's the weak classifier is, let's say, performing well. And if it's not too high, the error is not too high, it will ask you, would you like to add, let's see, another classifier or weak classifier? If yes, then we'll try to start, I mean, return back to this step. And if not, combine all these weak classifiers to make it a strong classifier, and then predict the final classification. So assume that we have, let's see, this data set here. So let me now zoom in so we can see the data set. So assume that we have spam detection. Imagine you want to classify email as a spam or not a spam, and you have these four emails. The word contains free, it should be spam, and no, it hasn't contains free, it will be not spam. And this is, let's say, only a small data set. It's not a data set, but just to make it simple. And imagine that we need to classify if an email contains a word free, they will classify it as a spam. So what they will do, they will take only one feature here, and let's say, for instance, free. They will see how many samples do we have here? We have four emails, and initializing the weights, they will try to make it all the weights are all this the data are having the same weights. So it's important all the emails. Now we will try to build a weak classifier, and which one is has misclassified, we will add a big large weight to this. So in the next time we will try to correctly classify it. So start with the weights, and because here we have four for data, we have four weights. So that train the first, let's say, weak classifier. The first classifier, let's assume that we have contain free. So the contain free, it's predict spam. Now we will see contains free. It will be spam, no, no. This is the, let's see, this is the true label, and this is the 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 prediction. And we see here we have corrected two classified, and here we have missed, let's say, missed two classifiers. And now we will try to calculate the error, then updating the weights. And with updating the weights, it will try to add to update, not to update, to calculate the error with this formula here. And if we get, let's see, error point 4, we will get this formula here. I mean this value. Now this is, let's say, a weak classifier, and for each classifier we will try to take only one, let's say, features, because as I said in the beginning, it's it's only a special decision tree with only one node. Now let's see, we need, after getting this error, we need to update the weights. If, for instance, the new weight, if the is correctly classified, we will add this e to the power alpha. And this, if it's misclassified, we will add this. And after normalizing and misclassified, we will have a higher weight. So for this here, it's not correctly classified. We will add more weight here, so that the classifier will try to make it, let's see, correctly classified. And after let's say training several weak classifiers, so it will try to make many weak classifiers. So let's see, 50, 20. It depends on your stuff. And now the how to build now a strong classifier. So the final decision is made by combining all these weak classifiers, weighted by the alpha. The alpha is all defined in this example here, in this formula. So let's assume that we have uh, 3 or 4 different classifiers. So for instance, if the classifier 1, if free, it should be spam. If discount, it should be spam. If urgent, it should be spam. Let's see, this for instance, free, discount, and urgent are the other attributes. For instance, he and he and he. Yeah, and each classifier contributes with its weight. Now, with this formula here, we will try to find to build a strong classifier. Let's say this is example here. For instance, check free. The weight is zero point 0.2, and the prediction, for instance, is spam. The check discount 0.4. It's not spam, and etc. And now we need to calculate this with the help of this formula. We will try to find the 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 final prediction, and see we have compute the weight, and here we have zero point 0.2 multiplied by 1. So for example, this multiplied by the class label, and this multiplied by the class label, and etc. And the final answer, it's positive 0.1. It's a positive value, so it will be classified as spam. So as a let's say a takeaway, the final decision is based on the weight of majority foods. As you can see here, we add the weight multiplied by the class label, and summation all of this with the help of this formula. A weak classifier with high accuracy have a higher influence, of course, because it has more weight. Let's see. And I think this is regarding the theory stuff. I tried to make it simple with this example here. Hopefully it will you will understand it very well. Now I have the code, the Python code is here, and you can see. Let me just focus on the stuff that we need. So you have see we have a decision tree. The max depth is 1, so it means only one node. And for this is for the weak classifier. Now the AdaBoost is a set of weak classifiers. We see here uh, adaptive boost classifier is imported for school from Scilab, and here we have estimator. The weak classifiers we have using decision tree. The estimator, number of weak classifiers, and the learning rate, and learning is 1, and the random state, I have mentioned in several videos that if you would like to have the same result with every run, you have to add this random state. Otherwise, you will have with each run you have different different result, because the uh, test split, it's randomly splitting. Without this, you will have to, for each time you'll have different X train, Y train, and etc. Now you can see add a boosted fit and add a boosted predict. Finally, we'll have to calculate the accuracy. In the next lesson, I will try to add this as to add it in the classification project. So we will make it is more organized, not just like this. We will use object oriented, and also calculating the accuracy and other matrix. Yeah, and you can see. Yeah, this with this data set, IS data set, we got 100%. So as I said, in the next one we'll add it here in this classification project and make it more organized. Thanks for watching and see you next time. Everyone, welcome back to my channel. In the last video, I walked you through how the AdaBoost work under the hood, and I showed you step-by-step numerical example that help you, let's say, to understand its mechanics. If you haven't seen this video, I highly recommend check this out. So in today's we are going to take a boost to integrate boost into our existing system. If you're already familiar with my previous video, you know what I mean by the integrating to the system. So it's only let's say a classification system that is working with multiple with let's say arbitrary data set and arbitrary number of algorithms. And this system is, I think it's already, let's say, well structured with, I mean, with a professional code design, reusable components, and let's say robust evaluation pipeline. So by end of this video, you will see how AdaBoost fit seamlessly into such system and how it can be used to enhance your, let's say, machine learning workspace. So let me just show you the system I have designed. Of course, it might be, let's see, better than this, but this, let's see, consider it as a starting point. Let's see. So let me just show you this. Yeah, for instance, this is the normal pipeline, and this is the data set, and you can add whatever you need the data set. And here this is the base classifier, or let's say the classification system. It is binary and multi-class label. And here you can see the many algorithms, and you can add as much as you can without affecting or changing the whole system. And this is what we have done in the previous sessions, but now it's just to show you how I add the integrate, let's say, the boost, add a boost adaptive posting into this system. So what I have done is, for instance, this is the project creating a file, call it as you want. I mean, let's see, add a boost, and this is the this is the class that I would like to let's say the code I would like to add to use it in add a boost. So creating a class, call it, let's say, with add a boost, and the parameters of this of the add a boost, it has many parameters, but in the beginning in the beginning it has yeah, I forgot to add this. Let's see, we classifier. Let's see, go to this one here, and you can see what are the parameters. So it was the estimators. So this should be estimator, and the other parameters will be added in the main file. So you can see in the main, I will just show you. Let's see the changes here I have done. So I have added the import, the class that I have done in this file here, and add the parameters, the parameters of this class. For instance, number of estimators, learning rate, and random set state. And here I just add if statement. If the type classifier type is AdaBoost, try to call this, and the other will stay the same. So this is much, let's see, easier than I mean, to integrate it in the working system. So now if we run the system, let's see the classification project, just run by this one, and here you can see, because I have the in the classifiers, I have all stack all the classifiers. So I will have result for each classifier, including of course the AdaBoost, the last one. So, and you can see here the AdaBoost classifier, and this is the confusion matrix, and this is the classification report. Yeah, that's it for today, and of course I will attach the code and all the video of last time. So if you like this, please subscribe into my channel, like the video, and if you have any question, of course, drop it down in the comment below. Thanks for watching, and see you next time. Everyone, welcome back to my channel. So have you ever wondered how machine learning makes, let's say, a great prediction? How does algorithm make a better with each step, and why the gradient boosting is one of the most technical in machine learning? So in today I will try to break down gradient boosting with a simple example, so you will not only understand it perfectly, but you can also you will be able to even to implement it yourself with pure Python. So imagine you are trying, let's say, just give this motivation to this boosting, gradient boosting. So gradient boosting is an ensemble learning technique that build multiple weeks model in a sequence. Each model fixes the error of the previous one, making the predictions, let's say, more accurate step by step. Now let's dive now in action and to see how it's working with a simple data set. So before that, if you are not subscribed to my channel, please do subscribe in my channel and like the video. And if you have any question, drop a comment in a comment. Drop a comment, of course, in a comment below, so I will answer it, because this preparing this takes much time. So as we already defined the gradient boosting, it's in ensemble learning algorithm that build multiple weak models. You can see in this figure is taken from Geeks, Frogs. I mean, it's hard to pronounce this, but this website is famous, and you can have a look on this website, of course. So you can see, for instance, we have a data set here, and start a model with a decision tree with only one split. So it's only one node in the tree, and then you will calculate the error, or called residual, of the model of this model here, and your model will train the to predict these residual. So usually when we have a training, when we have an algorithm, it will try to train and to predict the class label, or let's say the regression value. But here it's try to calculate to predict the residuals that calculated from the previous model, or let's say weak classifier. So this process continuously, iteratively, and keep adding models to reduce the error. As you can see here, final model will try to fit the data, as you can see in this tree. So let's assume that we have this data set, so X and Y target. So what we can do in the first step, we'll start with initialize the prediction. So we will sum up all of these the class labels. Let's see, this example, or this video, it's only for the regression. For the classification, I can do it in the next session. So we start with the initial prediction, and you can see sum up all of these y target values and take the average value. Now this is, let's see, the prediction, the initial prediction of the y. So you can see here, this is x and this is our y. Initial prediction, this is, for instance, 8. All the values will be 8. And now you can calculate the residual or error, this minus this. Now this error here will be let's see, it's not as a class label, but let's see, just for simplicity, it will be as a class label. So we will try now to predict what is the we will try to predict these errors. So now let's say this is our data set here, and instead of y we will replace it with the residual, or let's say the error of the first classifier, weak classifier. Now assume the decision tree is classified as it will be minus 2 if x less than 2.5, or plus 2 if it's greater than 2.5. This is only an example. So after this, you will have a decision tree to classify this, I mean to predict this, and then let's see, this is the prediction. Now we will update the prediction here. So the prediction, we will see, let's assume that the learning rate is 0.5, and with this equation here we can add the initial prediction plus lambda multiplied by R1, which R1 is this one here, the prediction of the decision tree. Let's see, this is a decision tree. And you can see this is a prediction. This is the first tree, which we have calculated from this one here. And now we need to update the y hat, with this formula here. And you can see this will be 7799. And now we will try to calculate, to let's say to predict this target, and we have the update of our updated prediction was 77 from this one here. And you can see now the residual of this predictions is minus, I mean this minus this. And you can see the next classifier will try to predict these residuals. And we see, for instance, this is the second residual, minus 200 plus 2. And we will have, I mean, calculate the final prediction with this equation here, with this y hat. And it's just iteratively until finding the closest, let's say, values to the class label. And you can see, for instance, this is the class label, our class label. Let me just check if it was the class label. Yeah, for instance, this is the class label. And if you see, after 2 iterations, we have somehow close to the class label. So it's 5 and 6, 7, 7, and 9 and 10. And here we have, let's see, minus 1. I mean, after iterative, you will have somehow close result to this. So as I said, this is a regression model. So as a summary, start with the initial guess, which is, in our case, we have done here is a mean, and compute the residual, train a weak classifier, update, repeat, and final model will try. Let's see, it's just sum all of these weak learners. So there are many, let's see, not many, but several gradient boosting algorithms. It's like gradient boosting machine, this one here, and XGBoost, which is, this is the most, let's say, fastest and optimized speed for and the performance. I will also explain it in a more detail with a simple example, as you can see this one, in the next videos. And when to use gradient boosting? So it's suitable for small and medium data set, not for the big data set. So you can use it if you would like to have a high accuracy, and when your data has I mean have no nonlinear relation in the data. I also, as usual, I have added this Python code here, and you can see I have imported gradient boosting regressor from the ensemble. And if you would like to use a classifier, of course, you need to replace this with gradient classifier. And you can see this is only reflecting the data that is used in this document here. And yeah, this is, you need just to import this, and that's it. Of course, you need number of trees, learning rate, and maximum depth. Maximum depth of the tree. It should be 1, let's say 1. And that's it for today. And if you like this video, please subscribe to my channel and like the video. If you have also a question, please drop it down in the comment below. I will answer it. And by the way, next time I will try to integrate. I have first the classification, the gradient posting for classification, how it's working with a simple example, and how to integrate these in a let's see in our project, which is already implemented in this classification project. You can see base classifier here. Okay, then happy learning and see you next time. Hi everyone, welcome back to my channel. In the last video, we explored how gradient boosting regressor was working, which was focusing on predicting a continuous value. In today's video, we'll see how it's working for classification, which is try to predict categorical. For instance, we have here binary classification 0, 1. And from the last video, let me just recap how it's working. So it's working as follows. So you have a data set. It will try to create a weak classifier. Usually, it's a decision tree. Initial predictions. It will be, for instance, taking the mean of the class label. Let's say of the regression values, and but here it's different in classification, and calculates the residual, train the next classifier, update the predictions, and if still needed to improve the accuracy, it will do again, and etc. So this will be repeated, let's say, several times. In the classification, we try to predict the categorical, and we'd like to minimize the log loss, which is called in cross entropy. So in the regression, we use mean square error. So let's say this, we have this data set. The first step we have to do is to make a constant prediction. So in the classification, we will try to get the total number of ions and total number of ones and total number of zeros. And if you see here, we have two zeros and two ones. It will be applying this formula, it will be 0. Now we will try to make the sigmoid function, which is this one here. It will be minus f0, which is 0 here. It will be minus 5. Now we will do the the initial prediction. It will be 0.5 for all uh, of these samples. Let's see, we have four samples here. Now we will try to calculate the gradient, let's say, pseudo residual. It will be this one minus the b0. It will be this minus the value that we got from this formula here, and this will be minus zero point 0.5, minus zero point 0.5, plus zero point 0.5, and plus zero point 0.5. Now we will try to use the next classifier, which is let's say, suppose we use a decision tree to predict this class label here, to predict this residual, not to predict the target. So this is the principle how gradient boosting is working. Now assume that we have, after calculating constructing the decision tree, we will have this, for instance, minus point 5 if x is less than 2.5. For instance, this is x. If it's less than 2.5, it will be minus uh, 0.5, and etc. Now we need to calculate the updating the loss, the loss. Let's see the logit value. It will be this, the f0, which is calculated from the above, and it will be this one here, and 0 minus this is what was 0, 0 minus, and the learning, let's say learning rate is zero point 0.5, and multiply by the first predictions, and it will be like this here, converting this to the probability, and this will be the 3.4 and 0.6 and etc. Now we will repeat this several times. For the classification, we will see any value is greater than zero point 0.5, which will be considered as 1. And you can see, if this is only for example, you can see this is 1 1 0 0. I mean, after the threshold, this will be less than zero point 0.5, it will be 0. Less than zero point 0.5, it will be 0. Greater than zero point 0.5, it will be 1 and 1. And if you see the class label, it will be somehow 0 0 1 1. So because it's only a simple example, it was covered so forth quickly. And what's the difference between the regression and classification? We already know. And in classification, it's try to minimize the cross entropy, And instead of calculating the residual, we're calculating the pseudo residual, which is loss, log loss. And we update the predictions and using the sigmoid function, and update the, I mean, repeat the process several times until we get, let's say, the best performance. As usual, I will try to show you how it's working with Python code with only a simple example that we have used in this document. So as you can see, 11434, and this is the main important one, is to focus on this. How did we import the boosting classifier? And here we add as a parameter, we need three decision trees, let's see, or let's see, weak trainers. And here the learning rate and max depth is 1. For instance, each decision tree is used, it has to be only one node. So for instance, X, either yes or no. And we have the prediction. And so I think this is enough for today. And next video, I will try to integrate this in the our classification project, so we can make, let's say, a complicated or comprehensive classification project that use all of these classification algorithms. If you like this, please subscribe into my channel and like this video. And if you have any question, of course, drop a comment below. I will answer it. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. So on the previous video, we have seen how random forest is, let's say, mastering of footing. And we already also, let me just go to it, and we also explore how AdaBoost, which was the first, let's say, booster. And we also master the gradient boosting that's learned from its own mistakes. But now it's time for the final, let's see, post. I call this post boss. I mean, this algorithm is that's faster, smarter, and also powerful. This the one that, let's say, dominates Kaggle's and power production models at scale, and they have used it in many, let's say, projects. It was performing sometimes better than the deep learning, but this is not the case. But it's really powerful. So in this video, we will take insight how not just how what is the XGBoost, but how it's working, how the log adds initialization, how the gradient and Haitian loss are calculated, and also gain calculation, and also the secret how the gradient boosting is working. And by the end of this lesson, you will understand exactly how XGBoost build its tree, update its predictions, and why it works well. So let's start from the beginning. Okay, so as I mentioned, the XGBoost is belong to ensembling techniques, as you can see here. So there's ensembling methods, and it's belong to boosting algorithms, including, I mean, inside the sampling. And this is all updating for the gradient boosting. If you see the previous video, it's the gradient boosting, and this one is extremely, let's see, optimized, the gradient boosting, and it's used widely in many applications. And let's just compare between XGBoost and gradient before diving into the calculation. So you can see the speed, it's the faster, and via parallelism and also histogram tricks, and handling missing values. For instance, if you have missing values in a gradient boosting, or maybe any other algorithms except random forest. So in this gradient boosting, you need to require manually how to fill this missing data. But in the gradient boosting, it's handling automatically based on see the behavior of each features, let's say. And the scalability, highly optimized for big data set. So I have used this with millions of data, and it will be, let's see, more powerful and efficient if you have a sparse data. Sparse data, it means if you have many zeros and some only ones. So assume that we have, let's start with the example how it's working. Let's assume that we have this data set here with several parameters, and we need to predict the y, the class label here. It means if the student will get the credit or not. So in the beginning, we initialize the step one, initialize the prediction using log odds. The log odds is try to sum up, let's say, taking the average of ones and zeros. So it's how many ones and how many zeros. That's it. And let's see, we have 0.5 because it's 2, 2. And now we need to convert the outlooks into probability. So we will use this function here, and we will get log 0 here. For the log 0, for this output, we will use the sigmoid function to predict the probability. And using this formula here, we will add, we have f0 is 0. So the output of this formula, it will be 0.5. Now we need to compute the gradient and Hessians. The gradient, it tells how wrong the prediction is and in which direction. And the Hessian, it tells you how confident we are about the gradient. So I will show you so let's say, let's just do it now. So what is the Hessian? How did we get this one here? Because this one is a first derivative, and it's easy. For instance, it's just the y hat minus y. The prediction minus the actual value. And this, how do we get this? Let me just show you here step by step. You can ignore it if you are not interested in this. But here, say for instance, this is our log value here, log function, loss function, sorry. And this loss function, it will be also after that, it will use the sigmoid function. And for the sigmoid function, the first derivative will be this, the first derivative of the log function, this one here. Sigmoid function. And the second derivative or Hessian derivative will be y minus, y multiplied y minus y hat. And this is how did we get the Hessian, the second derivative of this function here, of course. And yes, and let's say we have y hat. See, this is the y hat that we calculated from the beginning. So let's see from this here, from this formula here. It will be replaced by all the values. For all values, we'll just put 0.5. Now we need to calculate the gradient. We will calculate the distance not the distance, the difference. 0 minus 0.5, it will be y hat minus y hat minus y, it will be 0.5, and the other will be 0. And here it's the same calculating as Hessian with this formula here, so we will get this 0.205. So now we need to select, let's see, try to split the tree. It's building a tree, indeed. It's only building one tree. And it's not like random forest is split the dataset into several sub datasets and build the trees and using the footing. But here it's only build one tree. And let me see, we try to split the features with age. And if we see the age, let me just copy this. Maybe it will be helpful if we put it here. And you can see this is the age here. And we try to see if the age is less than 30, it should go to the left, and the other values, it should be to the right. So someone will ask why we just select the age. The good question. Let me just show you here how it's working. Starting at a node for each feature, because here we have 1, 2, 3, 4, 5 features. So here we have 5 features, and for each feature we will try to split to all split threshold and compute the gain. And from all of these we will try to select the highest gain. Let me just show you this one here. For instance, we have many features. 1, 2, 3, 4, 5 features, and we will try all of these features. and we will try all the splits. For instance, for the age, we have 1, 2, 3, 4 values. 1, 2, 3, 4. 4 values. And we will start with less than 22, less than 25, less than 20, and etc. And also you can add use the average of these values. For instance, calculate sum up taking the average of these values and make it as a split point, and this could also work. And here it's I'm just trying to do it with age less than 30, and if you see, we have only one less than 30, right? No, two. This one here, because it's not sorted, sorry. So 1 and 2 is less than 30. And if you see the left node, I mean the left node will be less than 30, and the right node will be point. I think I have the no. It's fine. Yeah. So for the left node and for the right node, it's like this one, and I will have less, and this, for instance, less than 30, and this is greater than 30. This is how it's building the tree. Now we will calculate the sum of the gradients and Hessians. So here we have the, let me just remove this because it's not needed anymore. And you can see here, I will add sum up all of this G and H. So the G, it will be 0.5 plus 0.5, it will be 1. And here 0.5 minus 0.5, it will be minus 1, I mean for the right hand. And for the H, it will be 0.20 plus 0.20. I mean, all of this, I mean, regarding the H, left or right will be the same. Only the difference is left, it will be 1, I mean, in a G, and a gradient, and here will be minus 1. And the total, if you sum up all of these, sum this and this, here will be 0, and this on this, it will be 1. So now we will calculate the gain. So calculating the gain, it's with this formula here. So you can see the squaring the GL, the G left was 1 divided by H left plus the regularization function. So this is the advantage of XGBoost against the gradient boosting, because using the generalization, it will try to minimize or remove the overfitting. Now plus the G right, and it's the same, and minus the G total. Let's see here, for instance, 0, and this one is 1. And it will just simple calculation. So we will have, for instance, the split, the gain, it will be 0.66, for instance, for this split, And as I said, we will do it for all of these features and all of these thresholds, let's say, and select the maximum. Gain. And after we get this gain, we will put it in the root. I mean in the root node, and we will try to add. I mean we will ignore this features. Let's see the age, and try with the new values until we get the. Let's see, for instance, we said this is the highest one, and we will try to calculate the leaf width. The leaf width is G, I mean summation of gradient divided by the Hessian plus the regularization function. And you can see the left we have 2, because the summation of this is 0.5 and 0.5 is 1, and divide by 0.5 plus 1. And for the right, we have for the right we have minus 1, this one here. And yeah, this is for the left and this is for right. Now we need to update the row prediction. we're using this learning rate. So you can see this is our left and right. Here is the left and this is the right. No, left, left, right, right. And we will use this to do the next prediction, let's see. And we will have this formula after calculating this, after applying this formula here, we will get these values here. Now, we will convert this to the probability. And you can see this is the sigmoid function, applying the sigmoid function with these results here, which is also this in the same here. We will get these values. And now we'll try to repeat from step 2 to 7. So this is 7. Step 2, it will try to calculate the gradient and Hessian. So for instance, let's just back to 3, I mean to 2. We will do the same here and following to the 7 points, step 7. And until this will stop until number of threshold, or maybe if that is it not changing anymore, and it will be, let's say, stopped. And as I said in the beginning, this is the most powerful, let's say, algorithm that I have used. I mean, without let's say deep learning. This used for small big data set, and it was super fast. So sometimes I compare the random forest and XGBoost, and so random forest for some, let's say, big data set, it's not working. It's need high powerful PC, while the XGBoost was perfectly working. So let me just move to the Python code. Yeah, for the Python code, we need these two packages here because I'm using Beauty and Toml file. What you can do, let me just close this idea. We just need to Beauty add and the package. This is, I mean, if you follow my videos, my previous video, you know how to do it. Now I have these files here. This is reflect exactly the example that I have done in this document, document here. And you can see, select the kernel. We need to select the kernel and it should work. And this is for, reflecting, as I said, the example that I have done. It's calculating the gradient, the boosting, and everything with pure Python. And for the second example here is using the XGBoost. So for instance, I have the data. I don't know why it's not, it's hitting here. Sorry for this. No idea indeed. Why is this collapse? Okay, but here we have a data. Here we have a data set, and in this one here we try to convert the data into XGBoost matrix because we need to convert it to the format of the XGBoost. And here we try to predict did the prediction and etc. Now uh, for this uh, yeah, and what I explained now is the XGBoost in classification. As you can see, I think hopefully I added in the beginning. It was for the classification. Yeah, and for the next lesson, I will try to make it for the how to do it or how it is working for the regression. And that's it. That's how our XGBoost learn from logs as and the trees. If you find this helpful, please hit like, subscribe, and check out the rest of my series. If you maybe you need to refresh how the random forest is working, how gradient posting, how AdaBoost, adaptive posting. Yeah, and drop your question in the comment below. And I always check and keep learning and, of course, keep posting. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. If you remember, or if you're following my series, I already implemented scalable and let's say well-structured project classification project, which is included several data sets, several classifiers, and also several, let's say, matrices, for instance, accuracy and recall, position, and etc. Now I would like to integrate the XGBoost in this code here, but unfortunately it's not, let's say, straightforward. That's why I would like to extend the code by adding another class and make it, let's say, scalable and maintainable for the future, let's say. And what is the problem indeed? The problem here is that XGBoost is only working with encoded data. For instance, if you have model, for instance, to fit, and x and y, let's see, x train and y train have to be encoded. For instance, if I have a class label spam or ham, this has to be encoded, for instance, 0 1. And it's not unlike the decision tree and support for automation and many others. It could work with this categorical data, but for the XGBoost, it give you an error. So what I have done is just have, for instance, in the beginning, in the old implementation, the data handler is trying to load the data and put it in and put it as an input for the classifier. Now, before this doing this, I have added this label transformer. So this label transformer, it will try to transform the class label, let's see, and then make the encoded or decoded classes and use it without any issues. So let me just show you the code. It will be maybe more clear. So in the beginning, I'm just showing you the changes I have done. So as you can see here, this is the class of XGBoost, and it's almost the same as it's the same, not almost, it's the same as support vector machine, as the decision random forest, as a decision tree, or it's the same. I have defined the XGBoost, imported the XGBoost classifier, and I have inherited from base classifier, and this base classifier has the train, predict, and etc. And these are the parameters, and also could be also passed from the main. And now if you see, this is the transformer class. This is the transformer that will try to transform. It's not only a class label, but any data here. So I think this is easy, let's see, to do. By the way, it's if you would like, you can use these two lines instead of the class, but I just make it, maybe, let's see, scalable. Maybe you need to add some other functions into this class, so that's why I have created a class label. So now if you see the main, let me just show you the main, what I have changed here. So I have imported the classifier as usual, importing also the label transformer, and I change it to spam data, because this I just we can use this as well, but because here it was a spam, it has to be spam, not another class. I just make it compatible. And let me just remove these two lines. Now what I have done, loading the data, I will get XY, and now I will try to encode the XY, the Y, so that's why it will be 0, for instance, 1. And I will try to use it here for splitting. Now I have defined the XGBoost here. This is for the classification indeed. And I added these lines. It's similar to all of these above. And here, after the classification, if you see, after the classification, after not after the yeah, after the classification or prediction, I will get this prediction. Now I would like to enforce it into the the original classes. Let's see, categorical classes. It will be spam or ham. For the test classes as well, I will do the encoded classes, and this will be almost the same. And if you run this, you will have all of these algorithms running on the same dataset without any issues. Let's see. And you can see it from the previous run. So and you can see now I have the class label as well in this report, classification report, because I have used inverse transform. Random forces takes much time, but if you can see here, XGBoost is really fast. So I recommend you, if you would like to use, if you have let's say classification or maybe regression project, I will recommend you to use XGBoost because it's really fast and you will get a best accuracy. I mean, we could also use random forest, but this one will also. I mean, I have used this several in several project and it was performed all of these traditional algorithms. Let's see. Okay, and then that's it for today. And if you like this video, please subscribe into my channel, like the video, and if you have, of course, any question, try to drop it down in the comment below. Thanks for watching and see you next time. Welcome back to my channel. If you already watch our video, let's see, in XGBoost for the classification, today we are continuous this journey with XGBoost for regression. So I will try to go step by step with numerical example and full explanation, beginner friendly as always. So before diving into the XGBoost, let's see regression. Let me just quickly remind ourselves what is the regression itself. And in classification, we predict a categorical like spam or not spam, okay or not okay. It's the class label is categorical. It's limited, let's say countable. And in regression, we are predicting numbers like house pricing, temperatures, salaries. So the class label or the predicted or the target column is a continuous value. It's not categorical like in a classification. So if your target variable is numbers, then you are dealing with regression. So as I already explained or tell you in the last video, it's XGBoost is a ensampling and boosting algorithm used to build the decision trees one by one. So and each tree it tries to fix the mistake of the previous one. So let me just say it maybe clearly. So in random forest, it built several trees. In an XGBoost or boosting algorithms is trying to build one tree, and in the beginning, let's see, and is try to improve or let's see fix the mistake of this tree of the previous tree. It's not let's say building several trees and finally it's just using by footing. No, and it's a great, this XGBoost is great for classification and regression. And today I will focusing on regression. By the way, if you have any data set, try to use XGBoost before using deep learning stuff, because it will give you a very accuracy, performance, and also a time. It will take in a second, let's say. And in today's video, I will try also to show you how to use the L1 and L2 regularization. L1, it's let's see, I think it's called uh, ratio. I'm not sure, but L1 and L2. And this L1 is used for the to make the tree sparse. So some leaves will be become zero, and L2 is shrink the value that prevent a huge jumps. So, by the way, L1 and L2 already explained in more detail with real examples. in the in this series. So I can give you about the link in the description. So as I said, now let's just start. And XGBoost, I will try to use gradient descent, also regularization L1 and L2. And let's assume this is our data set here. It has 1, 2, 3, 4, 5, let's see, parameters, plus 1, 2, 3, 4, 5, plus the price. This is our target column. Let's see, we would like to predict this price. So if we have a new data here, let's see the median income, and this is house age, this is the average rooms, this is the average occupancy, occupancy. And if we have, let's see, a new sample without, let's see, price, and we would like, our goal is to predict the price. So let's see how the linear, the XGBoost for the regression is working. It's similar to what we did in the classification, but somehow different steps. Let's see, as always, XGBoost is try to predict constantly the mean of the target values. So if you see here, we have the target values is this one here. They will take the decision, the average of these or mean values of these, and assign it to each row. So let's say, for instance, this is actual price, and this is the initial prediction. The initial prediction is came from the mean, taking the average of this column. And now we will try to calculate the residual. This is called the initial prediction. Now will calculate the residual or error, 300 minus 312, and etc. for all of these. Now we will try to build first tree. The first tree, as I already explained in the classification, it will try, for instance, you have here several columns here, and it will try to all of these columns and plus the threshold or the values in this, and build a tree and try to calculate the information gain and see if this is the good. It will try to split. So as you can see here, for each feature it will try to split all the threshold, then compute the gain, the information gain of each split, and try to split with the highest gain. So if we assume that if the median income is less than or equal 5.5, so it will go to left. If it's greater than 5.5, it will go to right. It's like a tree. Now, if you see here, let's see with the mid income, I will maybe copy this and put it down so we can see it clearly. Oops. So you can see here, this is the median income. It's, as we see here, this is the rule. If it's less than 0.5, so this will be left, and this will be left because it's 4, and this will be to the right branch. Now we will try to sum up all of these. So you can see the residual. We will try to sum all of these. I mean, for the left, we will try to sum all of these up, and for the right also we will sum these up. And you can see here the residual of this and this, it will be minus 45, and the number of samples, it will be 2, and number of samples also will be 2, and this is the summation of the residual will be plus 45. Now we will try to calculate the leaf values without regression. How do we calculate this? This is the weight. It is G divided by H. The G is the summation of residual in the leaf. So for instance, we have left and right. This will sum of the right and for sum of the left. It's OD here. You can see this and this. Now for the number of samples, H will be 2. And you can see this is divided by 2, minus 45 divided by 2. And this is divided by plus divided by 2. And we can see here, this tree, let's see, is predict 22.5 and minus 22.5. So we will now replace this, the initial bit. So we have this initial prediction. Now we will replace this with this new predictions here. But let me add the regularization L1 and L2. L1 is 5 and L2 is 1. This is assumption. This is as a parameter. You can change it whatever you want. So this is with the regularization L2. It's G and just added this lambda here. It's also, and for the L1, it's taking the sign of G, then multiplied by max, the absolute of minus alpha. I think this, taking the maximum of this multiplied alpha, then with 0. And if you see here, this is minus, and 45 multiplied by 5. Let me just check. Maybe I have done some wrong, maybe calculation. Yeah, sorry, I have done some errors. So we you know what is this? So this is the G, the absolute value of G multiplied by alpha. So it will be 270. But now it will be error, but sorry for this mistake. And now I will try to use to update the prediction. So this, let's see, assume this is the update. So this update will be y hat plus uh, uh, alpha multiplied by weight, which this is the weight we have. We have get this and this. So if you see, this is the new prediction. It will be this multiply plus this and this. This is our new prediction. Let's see. And now we will try to repeat step 2 till step 6. So for instance, this is our new prediction. We will try to calculate the residual, and this is a step 2, I think. Calculating the residual, yeah, and try to build a tree and calculate the values of the with regularization and etc. Now, after several steps, you will get, of course, I mean, because this is a small example, but after several steps you will get the exact, not exactly, or close to the class label, the regression label, the target column. So XGBoost build many trees, but each one fix the previous one. So it's not building, as I said, several trees. It's only one, but it's just fixing the previous one. And also linear regularization is shrinking the leaf to avoid, let's say, overfitting. So that's why I recommend you to use XGBoost, because uh, it's avoid overfitting, because using the regularization. And they also have this code here. Let me just maximize it. This is the same example I have as I have done use here, and you can see this is the regressor. It's imported from XGBoost, and you see how I installed this XGBoost in my Beauty. You can have a look in the previous videos. And let's see, yeah, I can just show you. This is the alpha. This is the regression lambda. Alpha and lambda. This is L1 and L2. Let's see. This is the regularization parameters. But I think they have also some default values. So I don't know where is this. But of course they have default values. Yeah, I think this enough for today. And if you find this helpful, please drop a like and subscribe into my channel, and let me know in the comment if you have any question, or maybe you need a notebook for this. I can do it quickly. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. If you are working with machine learning models, like we already covered several machine learning like decision trees, Perfecto machine, XGBoost, AdaBoost, and etc. So you have probably reached a point where you ask yourself some questions, important questions, let's say. So how I know which model is really the best, and more importantly, can I trust the accuracy I'm getting from any model? So well, see, here's the truth indeed. Sorry. Uh, so just checking the accuracy on the training and test split dataset is a misleading, and I already explained also this when to use accuracy and when to use precision and recall. Please have a look in the previous videos. So in today's video, I will try to we are going to fix this. For instance, how to measure, let's see, your performance. So let me just introduce to you the cross validation. So what is the cross validation indeed? The cross validation, so instead of training and testing your algorithm on just random split of the data set, for instance, like this is the data set, split it into two parts, for instance, 70% and 20%. So instead of just split this into two parts, we have to do cross validation. So split data set into multiple times. So I will go through this step by steps. So this way, every data point gets in turns into the test and also in the training, and this will get, let's say, much more reliable performance. Yeah. So this the cross validation, it helps to detect overfitting, compare models fairly, let's say, in a fair way, and make better decision based on on the result. So whether you're choosing, for instance, decision tree, random forest, or XGBoost, so cross validation gives you a confidence that your result will hold in the real, let's see what. So I'm just let me just give you a real example. Assume that you are working with a real project and you have a data set. Now you are split the data set into two parts: training and validation, of course, and testing. And your performance, let's see, was working, your model was working perfect. But in the running time, in the real time, in the real system, you will see the system is not working well because the data is different. Let's see, the distribution of the data might be different, or maybe, of course, there's a drift in the data. But this cross validation is showing you or let you know that your data is, let's say, really right, correctly distributed, okay, or come from the same distribution. So let me now, there's three different ways for the validation. So either hold out, which is like we have done in many ways, let's say in many, let's see a project. We have, for instance, a data set which contains 100 record, so that we will split the data into 70 and 20%. This will get training for 70 records, and this will get 20 records. The advantage of this way is fast and simple, so it's not complicated, let's say. But here you will get high variance and less reliable. So high variance, it's like when you have a high variance, it means, for example, in the testing, in the testing example, you have high variance that your model is already overfitting, so it's not able to perform well on the testing data, let's say. And the second point, let's see, the second approach is key fold. So you will divide your data set into, let's see, a set of fold. For instance, here I have 100 data, 100 record, let's see, and I decided to split this into 20 folds, and each fold contains 20 record. So assume this, you have data set, let's see, you have data set with 100 record, just like for simplicity. Uh, so yeah, it's just I'm just assuming I'm just forgot to add this, but let's do this and okay. It's just as example, and let's see you have uh, 100 records, for instance, 1, 2, 3, 4, 5, your data set, and you try use it from 1 to 20. This called fold 1. From 21 to 40, for instance, or 41, it will be fold 2, and etc. Now, how this will do in the training and testing? So we will assume that for the first fold will be as a testing, and the other, yeah, I have forgot to change this colors. Sorry, my mistake. Or just easy to do it here. So this is the training, and this one here is the testing. So you will use all of these folds in the training, and this one will be in the test. So in this example, for instance, the training will be 80 records, and the fold one or testing will be 20 record. Yeah, why I have this here? It should be 30% indeed. I just remove 10%. Sorry. Yeah, and it is for the same fold. So you will divide your data set into fixed folds, and each run, let's see, each iteration, you will use one fold for the training, for the testing, and the others for the training. And the last one is leave one out cross validation. Assume that you have 100 data set, 100 record, and each time you will take one sample as a testing, and the other samples are the as the training. But this, you see, it's more reliable, less bias, but very slow. It's because you need to if you have a millions of records, you need to do it. You need to have a, let's see, a big PC. But normally we would use key folds to do the cross validation. So let me just show you this example here in the for the cross validation. You can just select it for, I mean, import it from the model selection, which is Skyline, and it's just super easy. Defined, because here I just show you the decision tree and support for automation. And here you can see this is a cross validation. I have the X, Y, and how many cross validations. For instance, I have defined 5. And after this, you will have the scores of each fold. And here you see we're just taking the mean of this and also the standard deviation. And if you see here, yes, for the decision tree, the accuracy is 96 plus minus 0.033. And in this one here, it's the support factor machine is 96. I mean, let's see, 97 plus minus 0.021. So this is how you from now you see my classifier decision tree or support function is working perfectly. And because you see the standard deviation is very less. Let's see, neglectable. It's not that much. If it's much, it means one fold or maybe more than fold. It's far away from the mean. So you can see now which fold or which data it's different, and of course you can study your data why it's different. And I think that's it for today. If you like this video, please subscribe into my channel, like the video, and if you have, of course, any question, just drop it down in the comment below. I will answer. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. In today's video, we are diving into one of the most critical concepts in machine learning. It is overfitting and underfitting. So whether you are a beginner or experienced, let's say data science, mastering this concept is a key to building effective models. So imagine you are running a model to predicting the house prices or recognizing the cats or animals in the photos. So how would you ensure it learns just enough to generalize well? And let's see, for instance, this image here. As you can see, for instance, we have two different classes. This is just a simple, let's say, figure. And you see here, it's for instance, it's try to split. Let's see, is assuming that you are using any, for instance, linear regression. So here you can see it's trying to split these classes, these two different classes. But as you can see, for instance, many orange, let's say, classes or let's say instances are not well classified. So this called underfitting. And this will be explained in more details in the next, let's say, section. And here you can see, this is, for instance, if we draw a line from here, this will be, let's see, the optimal one. Of course, we have some misclassification here, 1, 2, and here's 1 for the other class, but it's somehow generalized. And if you see here, it's try to memorize the data so it won't miss any data. So this will be what we'll call overfitting. And overfitting means it works perfectly on the training data, but if you have a new sample, let's see, it's in this one, in this point here, in this point here. And it will be, let's see, misclassified because it's memorized the data. So let me give you a real, let's see, example, analogical. So for instance, let me just move it so. So imagine that there are three students preparing for an exam. The student A, student B, and let's see, student C. Each H1 represents different type of model, let's see, behavior. So assume this student here, this one for instance, is study barely, and let's say he didn't understand the subject and fail in both practice and real exam. Similarly, this is underfitting model is too simple. It missed the pattern in the data. So if someone is not studying, he will not, let's say, pass the exam and the theoretical and practical exam. So for the overfitting, for instance, this one here, so this student memorized every detail in the practice problems, but panicked during the real test. So this is, let's see, overfitting. He does the same. It's memorized the training data so well, but when but so that it fills on the new unseen data. So if you just only, for instance, for the this student, he memorized everything. But if you change the question slightly different, he won't be able to answer because he just memorized everything. And for the smarter he, it's like a hybrid between this and this. So this student understand the core idea, practice more, and perform well in both exams. So this is a balanced model. So learn the true patterns and generalized effectively. So let me just also give you, assume this is you are training your data, you are training your model on cats detection. So during the training, the model sees clear example of cats. But what happened when it see something new? So the model learns from these clear cats, for instance, this one here. But for the detection, try you see you put these images here, and this one, for instance, it will be somehow easy because you can see the cat in this area here, this one here, and because sometimes it will classify it or detecting only a dog because this is not clear. And will your model will be able to predict the cat is in this area here? This is the head, let's see, and this is the tail. And the most, let's say, difficult one will be, let me just zoom in so you can see this is the cat here. And it's like ability of your model with predicting the unseen data. So now how to detect and fix the overfitting and underfitting. So detecting the overfitting, look for every low training errors but high test example. So when you are training, let's see, assuming that a neural network, and during the training, during each ebook, the training error is let's say close to zero. But when you have on the calculating the error on a validation data, it will be very high. And also the model is in this case is working only on the training data, and with the validation or testing data, it's not working, let's you will. And for the yeah, to fix this, to fix the overfitting, let's say use simplify the model. If you are, let's say, using a neural network and your network has many layers, try to simplify this network. Let's see, make it 2, 3, 4, depends on your data, let's see. And the second one is to use regularization, L1 and L2. This will already explain in a very detailed way. It's already uploaded. I will give you the link. And also to fix the overfitting, you need to add more data, because with less data, the model will try to memorize this data, not make it, and is not able to, let's say, to make it general. And also try to use data from the data and the training and validation have to be, let's see, coming from the same distribution. Because if you train a model on this data, for instance, here, and the validation validate your model on this such data here, it won't work. But if you mix between training and the prediction from these two types, let's see, images, the model will be more generalized and it will be balanced. And also use one solution is to use dropout. Dropout, it's like making this is dropout in a concept in a neural network. It's like deep learning or CNN, and it's like making some neurons zeros, so it will not be calculating, will be participating in the calculating of the weight or cost. And also early stopping, it's, for instance, just try to make several ebooks and stop. Also feature selection, and one of the most algorithms used for let's say sampling methods, it's to fix the overfitting is used random forest. And of course I will not forget the XGBoost is also designed to fix the overfitting. And also the cross validation, it could also fix the overfitting. So I already have uploaded a video on this. Now how to detect the underfitting. if if your training and test error are high, then your model will, even on a new data, on the known data, it might be underfitting. So if you have if you train your model, let's see, let's just go to this example here. If you train your model on these images here, and from the same category, your model is not able to detect the cats, so in this case, it's also underfitting, because even for the training, it's not able to do well. So this is underfitting. Now, how to fix the underfitting? In the overfitting, we said we need to simplify, and here we need, but in underfitting, we need to make a complex model to learn more patterns. Also, training wrong, it's somehow the opposite direction from this one here. And let's see, this is this table. It's, I will see, it will for me, It's explain everything, and I'm quite sure this you will not forget anymore after this, hopefully. So to summarize, as you can see, underfitting has low bias and low variance. So let's see the bias in underfitting and in overfitting. Bias in underfitting is very high. So this is the error of the training is super high in the underfitting. And the error in an overfitting of the training, it's very low. So you can see the training is performing perfectly on your training dataset. And in variance, in the underfitting, it's low. So how could it be low? Because it will try to predict the same value. It's even if you have a different input, it will try to predict, let's say, the same output. For instance, here, it's like predicting output on the old data set with the same different, with the same, even with different data. It will try to predict the the same value. So that's why if you calculate the variance, it will be the same. I mean, very low. And for the overfitting, the variance is, let's say, related to prediction or to the validation. So in your overfitting, your model will do better on the training, but on validation, it will be the variance will be super high. And as you can see, the for the training error and underfitting, it's you for instance it will be high. So get prices wrong even for training, even if you train the model. Assume that you are trying to buy, let's say, a house, and you have no let's see enough information about the prices or the area location of the house. So this will be the error will be high. You will not be able to estimate the price. But if you for instance are doing you know the area, the prices of the areas of your area, and you try you miss, let's say you have enough information, but if you just move a little bit few meters, and you will not able to predict, let's say, the prices, because you just know this just a small area, not the whole area. So this is called overfitting. And I think remember this is, the goal is to create a model that learns just enough to generalize to the new data. So avoid the extreme of underfitting and overfitting, and you will be on your way to build a powerful, let's say, machine learning. So thanks for watching, and if you found this helpful, give it a thumbs up and subscribe for more insight content, and see you next time. Thank you. Hi everyone, welcome back to my channel. Have you ever wondered how your phone lets you recognize your face, or how virtual assistants like Siri or Alexa understand what you are saying? And what if I told you that a digital brain behind all of this? So a system that learns just like we do. It's like when you start learning something new, it's like sometimes you will start with learning some, let's see, something with wrong information, and you it will be updated over time. This is how the neural network working. So what exactly is a neural network? Imagine a computational model inspired by a human brain, just like our brains process information through the millions of interconnected neurons. And neural network mimic this structure to learn from data. But how do they do it? So neural network is just internal parameters, are just internal parameters. As you can see, these are the internal parameters here. I will just show it in the next section. So it's just adjusting these parameters so the output will be as, let's see, as a target, as we need. So as I said, it's called these parameters called weight in the neural network. And to make a prediction or decision, think of it as a digital brain that gets smarter with experience, consistently refining its understanding based on the data it processes. So even if you see how the kids is learning, is just learning by, let's say, comparing some stuff and updating the information and until he is able to do something. So, and as you can see, it's this information, this neural network. It's coming, or let's see, mimic the human brain. But but where the data, this data, the idea came from. So this. It starts with biological. It's like our brain here. You can see here, and they try to mimic this, uh, the processing in our brain, and mimic it as a neural network. And you have an input, so you have some processing unit. Let's say this one here, and you have the output. So what are the main component of the neural network? We have one is it a neuron, which is, for instance, this here called neuron. And it's the basic building block of neural network, and neuron compute the weight sum of its input adding to the bias. This is the bias. And pass the output to the next neuron to the next neuron, and this output from this unit here, it will be considered as an input to the next, let's say, neuron. And the weight is a connection, is strength the connection between the neuron and the bias. The bias is a constant value that will be added to the weight sum. Bias shift the activation function, allowing the neural network to fit the data better. And it's like giving the neuron a little nudge in the right direction. And the activation function introduce non-linearity into the network. So maybe one question in the interview: what is the goal behind the activation function? It's like introducing non-linearity using some activation functions. And the layer, of course, we know the layer. For instance, this is the input layer. Here, for instance, if you have a large, oh, here you can see it. Here, this is the input layer, and this is the output layer, and this is the hidden layer, and this is the output layers. And this input layer, it's not updating anymore. So, for instance, you have a data. I will just explain it in a moment. But the output data, it will be constant in all of these iterations. We will see it in a minute. And let's say, for instance, see this is as a black box. Input layer receive raw data, for instance, text, pixels, numeric values, and etc. And here, hidden layers is learn complex features. And if you see in a deep learning, some systems having many layers, hundreds of layers, thousands of layers, and number of millions of parameters. If you see it in a LLM, and the output layers is producing the prediction. It might be a probability and also a classification if you have a classification, but it mainly produce probabilities. And if the probability is greater than a specific threshold, it should be classified, for instance, to any class. So what are the type of neural networks? Is feed neural network, recurrent neural network, and CNN network. And feed network, it's like this one, for instance, here is called feed forward network. It's like each node, it has to be connected, or let's say called, for instance, fully connected layers. For instance, this one here is fully connected layers. That means each node will be connected to the next node. For instance, you see here, this one here, it's connected to this and this. This is generated by, let's see, the ChatGPT, but it's not like a good example. And let me just show it here. Neural network. For instance, this node here is connected to all of these nodes. That's called fully connected layers. And recurrent neural network is used for sequences like languages, and recurrent neural network and transformer is used for languages, and also transformer latest in the latest time it will use for the also for computer vision, for object detection, object segmentation, and etc. And the CNN is used for video and image analysis, because it's if you imagine image with hundreds of pixels, so and if we try to use the whole pixel, for instance, let's say assume this is the layer, the input layer. So if we have one image with thousand, let's say, pixel, we will add here 1,000 pixel here. So this too much, right? So that's why we need to use a convolutional network. This will be explained in the next videos in a super easy way, and I'm quite sure that you will understand everything, but not in this lesson. This is only a basic. And assume this is a simple network here. So we have x1 and x2, and every input has, let's say, a parameter, and the parameter will be added to the bias and to output the y, let's say the target. And this is the easy this is the equation here. You have y weight 1 multiplied by x plus weight 2 multiplied by x2 plus bias. This is to output y, but we need also, after this calculation, we need activation function, as we have seen in this let's say activation function. This is also needed. As you can see, this is activation function. And this activation function, it will try to output, make the output into a specific, let's say, range. And after this, after y calculated, for instance, let's assume this, I have x1, x2, right? And I have x1, x2, x1, x2. This is, for instance, my data set. This is, let's say, my data set. And I'm trying to get the y. So in the beginning, in the first time, I will add replace x with, for instance, here 1 and 1, and calculate this calculate y with this, with the help of this formula. Then the second input will be 2 0, then and etc. But in neural network, it somehow take all of this in a vectorized method and to make it in one time, let's see. But this is the case. It will take this input and this input and this input to calculate the y. Now the activation function is used to, as we said, it's adding non-linearity to the output, to the output of the neuron. And we have many, let's see, activation functions, but these are the most, let's see, important. Of course, we will have in the next videos, we will see many of these ReLU and what is the best use, and when to use or when not to use it. For instance, like ReLU, it's like a gate that only open for a positive number. For instance, if ReLU it used, if you have a value, for instance, negative, it will be replaced to 0. It's like taking the maximum value between 0 or the output. And as you can see here, the output range is 0 and infinity. And the sigmoid function is used between 0 and 1. This called this used for classification. And you can see here the ReLU function is used for hidden layers. It's not, don't try to use it in the output layers, because the output, it will be from 0 to infinity, and you will not be able to, let's say, classify or detecting the values. And tanish function, it's like a sigmoid function, and the output range is -1 and 2 1. And this is best used cases. To use this one is used for inside in the for the hidden layers, and not for the output layers. And sigmoid function is not used for sigmoid for hidden layers. If you know why, this will be of course explained in the next videos. But for now, sometimes the sigmoid function, after the derivative of sigmoid function, the values will be close to 0. And if we use it inside in the hidden layers, our network will not, let's say, learning best, because sometimes it will be first, because there's no movement in the, because the sigmoid function, the derivative of sigmoid function, it will be zero, it will be close to 0. And tanh is just used for hidden layers, of course, and it could be also used for the output, but it's rarely used in the output layers. And let's see, this is activation function, right? And after calculating the activation function, we need to calculate the loss, measuring the mistake. So you see here, we calculate with example. Okay, here we calculate the example. Let's see the output of y, and now we need to see, is it right? This is expected value, or it might be okay, or it might be far away from the actual value. So we need to measure the mistake and update, measure, for instance, measuring the mistake, and there are several methods indeed. One used, for instance, for regression, and one used for the classification. This mean square error is used for regression, and this cross entropy is used for classification. And now, after calculating the mistake, the measuring the mistake, now we need to update, let's see, fixing this mistake. And fixing this mistake will be try to update the weights. So you can see in this one here, for instance, x1, y1, and we need also to update only this. Let's see the weights and the bias in all the networks. So for instance, here we have only 2 nodes or 2 inputs, but mainly only the weights and bias. These inputs here will stay the same as, I mean, it's constant. It, it won't be updated, let's see. Because if, for instance, the x1 and the xy2, this is the values of x1 and x2. This won't be a change during the training or during the testing or during anything. So the updating will be updating only the weights and bias during the training. So there are several, of course, several optimizer. Let's see, stochastic gradient descent and adaptive gradient descent. So this moment descent, this is, let's see, most used in all, let's say, algorithms. This is because it's super fast and accurate. And I have also tried to for instance, for a small example, let's see, with the same number of creating a similar simple neural network. And as you can see, so in the beginning, I have to import the torch and see how I install it, because I'm using the beauty. What you can do is what you have to do is like this. So this is added now. Let me just to see this. You can see this is the project TUML file. So this have been added. Torch audio, I mean studio and vision. And this, I have used this one here, CUDA. But in case you don't have a CUDA, it will try to download the the CPU version. So because I have in this PC, I have no CUDA. That's why I have only to install the CPU version. And you can see, after importing the torch, I import the neural network, and and also the functionality. So, and here this is a simple class, let's say simple NN. I will initialize it will be inherited indeed from this neural network module, and initializing the parent class because it is inherited, and I have defined 2 layers. let's see the two inputs from layer one, and the layer two, it will I mean the input is two, but the output is also one, only one output. And the forward process, it will try to use the sorry it will try to apply ReRO function for this output here, for this input. And what is the input here? It's a simple linear function. And this linear function, it will try to update this one here. This is the linear function. Each layer will do this one here. And because we have two inputs, it will do both. And finally, we will use a sigmoid function and returning the output of this y. Now, after calculating this, we need to update this is only forward feed. Now we need to update the weight, right? And here we initialize the class, and the loss function we use mean square error, and the optimizer we will use Adam with learning rate 0.01. And here, let's see, I need to run this for 1000 time, and 1000 time it will try to predict the model and calculating the loss as we have to explain it in the document. And here it's optimizer is clearing the gradient of the previous gradient, and now loss back propagating, calculate the loss the gradient and optimize the weights. And this will done for every, let's say, for 100 times, 1000 times. And once everything is okay, this, and let me just run this. It will take, I don't know, because it's I have no GPU. Yeah, by the way, for instance, for regarding the TOML file, project TOML file, you can add the stuff here, and it will be added after when you add Beauty install. It will try to read this. I have follow. And you can see, for instance, in the ebook, the loss was 0.02, and it's reduced. Let's see somehow a bit, and after 900, because here I use after 100 should give output. After 900 ebook, the error was somehow. Let's see if you compare these two, or maybe four. You can see the loss function is fixed, and in this case you can add the earlier stop, or maybe number of iterations, reduce the number of iterations, or maybe taking the best out, the best model with less error. And this we will see it in the coming, let's see, videos. And by the way, for instance, sometimes you will have this ebook. I mean, the loss function will be this 1.668, and for maybe for the next for the next ebooks, you will have 0.017 or 0.019. So it's not like a fix that you will have always decreasing. It might be jumping based on your data, based on your weighting, initialization, based on many factors. This will be covered in the next videos. That's it for today, and if you like this video, please subscribe into my channel, like the video, and of course if you have any question, please write it down in the comment below. I will answer it. Thanks for watching, and see you next time. Everyone, welcome back to my channel. So as you already, let's see we already now covering the part 4, which is deep learning, the most important, let's say, aspect. So I already starting with the neural network basic. We uploaded this file here, the video, and with example. And now which we are now covering, let's say, a back propagation. Let's say the backbone of any algorithm in a machine learning, in a deep learning, which is updating the weights to reduce the error of the algorithm. So because I already covered this in the previous video, as you can see here, it's already covered in this video. It's really explained with example and step by step, and I'm quite sure that you will get the main idea behind this. And as you can see, it's covered every, with of course with example and with the numerical example, step by step how it's working and how gradient is working and how to the updating. And I don't want to, let's say, to repeat this calculation because indeed I have no this file. I already lost this file, so I'm not quite sure if I can do it in a short time. This example. So please have a look, and if you have any question, just drop it down in the comment below. And also, I already attached this file here, backpropagation example, so you can have a look. It's really might be helpful for you to go through this document. And as I said, yeah, I'm quite sure you will understand everything here if you see only this document. And if you have, let's say, some doubts, please refer to this video. I will add this in the comment below. Also, I already attached this link here. You can see document example. And yeah, so if you like my videos, and please subscribe to my channel, like this video, and if you have any question, please drop it down in the comment below. I will answer it, of course. Thanks for watching, and see you next time. Everyone, welcome back to my channel. In today's video, we will diving into some super, let's say, important aspect or important stuff in machine learning, which is loss function in neural network. So think of it as GPS guiding your model in the right direction. So this is how the let's see the loss function. And what is the loss function indeed? So assume that you have a deep learning algorithm is running, right? And you have, let's say, your training data, and you would like to build a model, let's say a high performance model. So now this is your data, and after feeding this data into the model will try to update itself. The parameter, of course. So based on this, the calculating the loss function will let the neural network to update the weights. So in that case, you will have, let's say, a good performance. So what is the loss function itself? It's a quantifies how will a neural network perform, or perform, yes. And it's compare between the your predictions and the actual result. And the best part of it, it's turn these mistake into a numbers, which your model can use to learn and improving over time. So let's say, for instance, in this example here, why it's important. Let's say, for instance, your model is trying to predict the house prices. Now I have added here only one parameter here. Let's see, because for the house pricing you need many variables or attributes. And let's see, just here the input of the size of the house, and here's the actual price, and this is the predicted price. Now the loss function is trying to measure the difference between predicted price and the actual price, and see if it's big, the model needs to be updated. Let's say the parameters needs to be updated. So these parameters already explained in the previous videos. Please have a look. And also in many several algorithms already explained in many several algorithms like XGBoost, support for machine linear regression, also logistic regression. Now let's see, for instance, I have this actual price, and this is a predicted price. Now calculating the error with prediction minus the actual. This is, for instance, 20,000. And with applying the mean square error, we will try to square this error here. So as you can see here, this is a big number, and this let you that that is a huge, let's see, error. But now how the model know how far it was. So, and based on this value, it will try to update the parameters of the network. So this loss, let's see, for the upcoming, let's see, iterations or epochs, this will be somehow close to zero. I mean, the optimal value is to be the optimal error. It should be, let's see, zero. For instance, the actual price is 300,000, and let's say the predicted thousand, the optimal case, it will be 300,000, but it will be plus minus something. And until you have, let's see, agreed with this or satisfied with the model, this is, for instance, enough for the model. Now there are several or important loss functions used for the in the deep learning in the deep learning. The first one is mean square error. It's a great for regression, and but it's it's try to, let's see, if your data is having only let's see, numerical values, like for instance, predicting house, it use only for the for this values that is numerical. And also the mean square error, it's the same as this one here. And binary cross entropy, it's used for classification. For the classification, if you have, for instance, cat or dog, here you need his is only a binary classification, for instance. And the hang loss, it's used, if you remember, it's used for the in support vector machine. This is with the regularization function, and this already explained in a very easy way with a numerical example. So please have a look in the support vector machine. And now let's have a look on type of loss function. I mean, this is only the loss function, but we need to know when to use this and when not. Let's say, for instance, mean square error is used for regression problems. When you have numbers, the target value is number. For instance, house pricing is a numbers. And let's see, forecasting, weather forecasting, it's predicting the degree, the temperature, it's a number. So we need to use mean square error, or maybe mean absolute error. And binary cross entropy, it's used for binary classification. And if you have a spam, email, spam, or ham, only two classes you have. And categorical cross entropy, if you have multi classes. For instance, if you have, as you can see here, for instance, predicting the digits between 0 and 1, or maybe if you have a let's see, ImageNet that has 80, for instance, or maybe then 80 classes for the animals. So in this case, you need to use categorical entropy, cross entropy. And the hang loss is, as you can see, it's support vector machine classification. And let me just see, I have also provided this, and it's somehow this is what we have already explained, but in a PyTorch framework, or let's see, package. And here you have the mean square error. This is how to import the mean square error. The error is, for instance, here, and here's the mean absolute error, and the loss Hooper loss function, and binary cross entropy. For instance, you have the prediction, and you have the truth. So, for instance, 0.9, and here's 1. And the binary cross entropy, this is calculated by this function, or let's see, class. And here you see the it says binary loss except for digits. And here the categorical cross entropy, if you have, let's see, multi classes, as we already said. And the last one is the for the hang loss. It's not, let's say, provided directly in the PyTorch. It's not available, so that's why you have implemented it. Also, this was already implemented in a support vector machine, and you can see it in support vector machine. I don't know where is it, but it should be here. Yeah, that's it for today. And if you like this video, please subscribe into my channel and like this video. And if you have, of course, any question, please drop it down in the comment below. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. Have you ever wondered what makes some neural networks so powerful while others struggle to perform basic tasks? Or why bigger models sometimes fail when they are getting, let's say, more little data? So the answer is this is, let's say, the trainable parameters. But what exactly these parameters? So why do they matter, and how we can calculate them in our model, or let's say neural network? If you are asking these questions, you are coming to the right place. Today I will try to dive into this, understanding how to compute, or let's say count number of parameters in your network. So why should we care about, let's see, these parameters? Why we need to calculate these parameters? So defining these parameters is they define the learning capacity. So more parameters mean the model has more flexibility to learn complex patterns from the data. But there is a disadvantage of getting more parameters. It's risk of overfitting or underfitting. So many parameters might cause overfitting, where the model memorizes the training data but fail on the new inputs. This already explained in the previous videos. On the other hand, too few parameters could lead to underfitting. So this model won't be able to capture enough information from your data even during the training, or maybe the validation or testing. So in a short, getting the parameter count right is a critical to building efficient and effective models. But what are these parameters we need to calculate? Or let's see, count. So it's weight and bias. And the weights are the connection between neurons in the adjacent layers. So each connection has its own weight value that model adjusts during the training. For instance, this is our input values, and as I mentioned in several times, the input data won't be changed. Only these connections here. These connections are the weights, and plus the bias. This H neuron, so for instance, this is a neuron. H neuron in a layer has associated bias, which help to shift, let's say, the activation function or up or down. And together with weights and bias form the set of trainable parameters that define how the network processes the input data. So now how to calculate these parameters? So as you can see here in our network, this we have input layers. It has only three input parameters, or let's see, input is for instance x1 y1 x1 x2 x3, and this is the hidden layers. I have here in this three hidden layers, and each layer has four nodes, let's see. And for the output layers has three, let's see, outputs. For instance, just like let's say you are trying to detect the animals, for instance, cat, dog, and maybe horse or any. This is only a sample. Now to calculate these parameters, we have to calculate this parameter from this to this layer, and from this layer to this, and from this to this, and from here to the output layers. So for each layer, we need to calculate how many parameters, and finally we will sum this up to find all these parameters. By the way, this for instance, this is input layer to this layer here, and this layer consider as an input to the next layer, and this consider as an input to this layer. So yeah, so how to calculate this parameter? So I have just simple formula here. It's n plus 1 times m. So n is the input unit. For instance, here I have three inputs. Plus 1 is 4, and multiply by m, where m is the number of output units. So this is output with respect to this, and input with respect to this. Now I have in details calculating the number of parameters in each layer. For instance, here I have 3 input plus 1 multiplied by 4. It will, for instance, it will be 16. Now this layer here, hidden layer to hidden layer 1 to hidden layer 2, it's 4 plus 1. I mean, with this formula here, 4 plus 1, 5 multiplied by 4, it's 20. And you can see here we have 20. And this one here, from the layer, this layer here to this is 4 plus 1 multiplied by 4 will be also 20. And here I have 4 plus 1, 5 multiplied by 3, it will be 15. Now, all of these, we need to sum all of these up to find number of parameters in our fully connected layer, or called dense layer. So you can see here 16 plus 20 plus 20 plus 15, it's 71 parameters for this simple network. So imagine if you have a big network, how many parameters you will have. You will have to prepare, or let's say trainable parameters, how many trainable parameters. And this is for the dense or fully connected layers. For the convolutional neural network, it's totally different. We will discuss it next video. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. In today's video, I will try to show you or explain how convolutional neural network is working. So the powerful model are specifically designed to process and understand images and making them, let's see, this is the CNN is the core of computer vision, and it's used for anomaly detection, autonomous driving, medical images, and many more applications. So this is, let's see, this is, architecture of the of the CNN, and this, of course, I will explain this in a very more details in the next coming videos. But this is only an introduction to CNN. What is the CNN, and how is it working, and when we need to use it. And before diving into a CNN, let me just let's us firstly understand what is an image. And an image is essentially is a grid of pixels. Let's say, for instance, two-dimensional matrix, just for simplicity. And each pixel represent a specific color. And as you can see, let me just zoom in. And if you see here, this is, for instance, this is the region, or this is the circle. It's, of course, not only one pixel, it's many pixels, because it's a small image. But if you can see pixel, it's like only one cell. And as you can see, for instance, for color images, we have red, green, blue, or RGB. And each pixel in each channel represent three numbers. I mean, each pixel, it represent three numbers. And it is the intensity of red, green, blue. And you can see, for instance, as you can see here, this is, for instance, this is the pixel value after, let's see, the normalization. So the color image, the intensity, or let's say the values of image, the normal one, it's from zero for each channel, from 0 to 225. But this is a sample of after normalization. So it's like the value of pixels will be between 0 and 1. This is only to show you how is it image represented. And you can see, for instance, here red, green, blue, and it has now three channels. And let's go back to the image, our image here. And you can see here, this is a color image, and I try to split each color, each channel in a separated image. And you can see this is the red image. If you extract only the red image, the first channel, it will be like this. It's a gray image. But if you would like to add some colors, it will be, of course, red. I mean, to make it as a color image, it will be red, for instance. And this is the green, and this is the blue. And now, and you can see, for instance, let me just forget to add this, to mention this. Here's, for instance, red, green, blue. If the three pixels, the three values in one pixel, let's say in the three channels, for instance, if you see, for example, if you select this pixel here, and this pixel is 0, and this one is 0 in the green color, and this one in the 0, this will be black. You can see it as a black color. And for instance, you can see this red, because it's 255, and the other one is 0. And blue, there's the blue, no, there's no blue. and it's just only let's see, this is the representative color, and this colors is from 0 to 255. For instance, this could be 100, 100, 100, or 120, 120, 100, 255. It depends. And there's no let's see, it's not, let's see, mandatory that the sum all of these values will be 200 to 55. No, as you can see here, for instance, 200 to 55, 200 to 55, and this is the this is the black one, and this is the white color. And let's see why we are not using the neural network, traditional neural network. In the previous video, I have explained how to calculate the parameters of the neural network. So if we would like to use an image for the traditional neural network, first we have to flat the images into one single dimension. For instance, as you can see, for instance, I have this image 224 and 224 multiplied by 3, let's see, 3 channels, width, height, and channel. And we need to flat all of these pixels in this one image, in this one image. And you can see here is 150 value for only for one image, if we assume only 224. Now we will, if we, let's see, flat these images, we will lose the spatial relationship between pixels. For instance, this pixel, it will lose the relationship. For instance, let's see, this is the image, and the second image, for instance, from here, it will be down here, and there's no relationship between these pixels. And no, now we will figure out that we need a huge number of parameters, and this will make us slow, and maybe we need a high computer just only to run a few images, a few layers. And let's see, assume, just to prove that we need a huge number of parameters. This is, I'm just flattening all my, the image that I have, this one here, in one list, let's see, in one dimension. And I have this, for instance, 150 pixels or value. Now I just assume that I have one hidden layer, and this hidden layer, it has eight, 1, 2, 3, 4, 5, no, six neuron, let's see. And to calculate these parameters, I already, as I mentioned in the last video in more details, the number of parameters in each layer, in this layer here, for instance, it will be n plus 1 multiplied times m. And n is the number of neuron here. So you can see here's 150 plus 1 multiplied by m, where m is 6 here. So for this layer here, we will have almost 1 million parameters. Let's see, 903 parameters, 1,000 parameters. That's why we can't use neural network for this region. For this, now we need, why we need to use CNN. For CNN, we will try to use a small filters. It's called filters or kernels, and it will move to the as a sliding window to the across the image, detecting local features like eyes, corners, textures. And this I will show you in a more details. This is only, let's see, an introduction to the neural network, CNN. And as a parameter, it's more efficient because we are the sharing parameters, the weights are already shared across all the image. And let me just show you this here. What are the main component of the CNN? It's a convolutional layer. So this detects the basic features like edges, vertical or horizontal edges, texture, and etc. Now, how is work? So filters 3 by 3 slides over the window. For instance, let me just move to this. So assuming this, I have this image here, this red here, and for that I have this filter here. And by the way, this filter will be updated over time when we have a back propagation. So in the beginning, this could be randomly initialized, these filters. The images will stay the same in each iteration. And let's see, for instance, I just because I have 3 by 3, I will just map it to this 3 by 3, and it will be product wise. For instance, 0 times 9 plus 2 times 4 plus 1 times 1 plus 4 times 1 plus 1 times 1, and etc. And this will output only one pixel, let's say this one here. And for the next time, we will try to multiply this pixel with the next region from the image. So this will move from this, for instance, and we will take this region here. For instance, like, no, we will take this from, for example, from here, from this region, and we will include also this. And for the next time, we will do this from here to this. And once we finish this, we will go down when it's 1 pixel. And so it will be from here and including this one here. And do it again from left to right and then down. This will be explained in the next video, don't worry. Uh, Let me just see. Yeah. And the output of this multiplication convolutional neural layers, it will be this one here, which is called feature map or output map or feature map. It's called the scientific. Now we will see this is the first component, convolution layer, and of course the kernel, of course. So we need also the kernel to learn these features, to extract this feature, for example, lines, curve, textures, and edges, and everything. And as I said in the beginning, filters will be updated over time with the back propagation. And as I mentioned in the beginning, we will, because we will see an introduced number of features. And as you can see here, I have 9 features here, for instance 9, and this 9 will be shared all for all the image. And I will use the C, for example, for the H ebook or H forward, I will use this filter for the whole image. So it means I'm sharing the weight for the whole image. So that's why we need to let's reduce number of weights. Now the activation function, after calculating the after computing the, let's say, the feature map, I just add a random example here. And the activation function, let's say I'm using ReLU, and ReLU it adding generally activation function adding non-linearity to the network, so that it can learn many, let's see, more complex patterns. And for the ReLU, it will activation function. It will reduce, let me replace the non-positive value with 0. And you can see here, for example, this is -1, -8, -3. It will be replaced by 0. And if we replace this by 0, we will try to reduce also the computation because this is almost 0. And for the pooling layers, is reduce the feature map. So as you can see, for instance, I have this feature map. This is also taken from this source, and also this one is from this link. And assuming that, let me just, so the polling layers, it's, let's see, I have different polling layers, polling mechanism. For instance, max polling layer or average polling layer, or maybe minimum polling layer polling. And let's say this in I'm taking the maximum. And let's say I have 2 by 2. Let's see the region. And from here I will take the maximum one, for example, max polling. And this I will just take the maximum value from here and put it here. So as you can see, I just reduced 4 pixels, and I just need only one to represent this region here. And for the other one, I will divide the image into grids with 2 by 2 and taking the maximum one. So as you can see, this feature map, it will be reduced to this. And what is the, let's say, the pipeline of the CNN? You have an image, you have a convolution layer, and also the filters. And after getting the output, let's say the feature map, you will do a ReLU plus, I mean, next polling, and also repeating these several layers for instance, convolution layer, ReLU pooling, and etc. Also, you can use dropout. You can use normalization layers. This will be explained in a very more details in the next video, next videos, and I think I think that's it. So if you don't understand, let's see some. This is only a basic, and hopefully you will get let's see let's see general idea about this topic. And for the next videos, I will try to explain you, or let's say show you how the convolutional layers is working exactly, with many examples and with real, let's see, small real examples, and how to calculate the number of parameters in CNN. Yeah, that's it. And thanks for watching. And if you like this video, please subscribe to my channel, like the video, and see you next time. Welcome back to my channel. So you already know what is filters and in a convolutional neural network, and we have talked about it and edge detection patterns and how the filter slide over the image. But let's see, we would like to go deeper in this topic. So as you can see here, the filter is might be 3 by 3, 5 by 5, 7 by 7, and etc. And the result of multiplying these filters with the image, it will give us a feature map. The feature map is the features that are extracted from the image. So as you can see, for instance, in this image here, I have this is the original image, and I have tried to detect the vertical and horizontal edges. I will show you in the code what does how this is looking, and how is working. And let's just start with how it's working, how it is this the heart of the convolution. It's like a tiny window that slide across the image. Do you doing a little of math? It's a multiplication. So at each step we multiply numbers from the filter with the image, add them up, and write the result in this, for instance, in here as a feature map. Then the slide filter will go the next spot and repeat again until finishing this image. It just multiply, add, move, and repeat, and that's the output is a new image with called, let's say, a feature map, which focusing on something specific like edges or buttons, as you can see, as you have seen here in this image. And why filters are matters. So different filters look for different things. So one might highlight vertical lines, another one's here is the vertical edges. Some look for the corners and textures. And the cool thing is that the same image can also have can look totally different depending on which filters you use. So that is how CNN start to understand what is inside the image. And as you can see, for instance, in this image here, this is the vertical edges, let's see, and horizontal. And this is, for instance, for the first layers. For the next layers, this is only for the first convolution layer. You can see there's nothing, it's just only edges, might be colors. And for the next layers, you can see there's somehow you can see some appearance or texture for the object. And as you go down to deeply to the network, you can see the recognized object, so you can understand what is the object. And one, let's see here something most people don't realize. We don't design a filter by hand, so the network will learn them by itself. So if you see filters, it means I haven't, let's say, initialized this filters, or let's say initialized by hand. So this will be randomly initialized, and during the training, it will be updated. So in the beginning, filter will I just random numbers, and you can see, for instance, this is here the random numbers here, and with the update it will be updated. These filters, only the filters will be updated, plus minus. And during the training, model tweets them again and again until they start finding useful things. And in the early layers, the filters the filters learn to detect simple things, lines, edges. In the middle layers, they will try to find shape like eyes, wheels, or texture. And deeper in a deeper layers, they start to recognize part of the objects like fish, animals, cars, and etc. So this is what you see. This is the filters are not learned. They are only randomly initialized, and they will be updated during the back propagation. And you can see here we don't need to use one layer or let's see filter. We have many filters and will be stacked together, and each layer passes its result to the next one. So the first layer finding edges, the second one find the shapes, and it will use the final the input the output of the first layer and consider as an input to the next layer. So the second layer find the shapes, and this shapes will be as an input to the next layer. So the third layer put all them together to find objects, and it's a building, let's see, something stuff we understand, or one layer at time. And here let's see as a recap. So filters are small buttons that scan the images. They highlight edges, lines, shapes. They are not let's see handmade. They are learned by the algorithm during the back propagation. Stacking filters together gives the model real vision, and that's how CNN go from pixel to understanding the image. And this is this happens just by showing the model enough example. That's the magic of the filters and convolution neural network. Let me show you the example of edge detection, and you can see here that this is the vertical edge kernel or filter. As you can see, this is the values, and here I have zeros. This is to see the transition between zeros and ones. And you can see this is the horizontal. It's like this is the zeros in the middle of the horizontal. And they have here one image, and they say give me the vertical edges when I have this image, and this is the kernel, and with padding 1. So padding 1, it means I need to have the same image size. And they have, I can show you the result, or it already showed in the beginning of this lecture, but let's do it again. Yeah, let's see. I will just run, and let's see the edges. And you can see this is the original image, this is the vertical, and this is the horizontal edges. So it is focusing on these vertical edges, and this focuses on these horizontal edges. And yeah, that's it for today. And if you like this video, please subscribe to my channel, like the video, and if you have any question, of course, drop it in the comment below. Thanks for watching, and see you next time. In CNN, how to calculate the output shape or the feature map size. So as you can see here, this is the formula. This is the W is the input size, width or height. The key is a kernel size, the filter dimension, padding extra border around the image, and the stride step the filter takes. And let's explain this. So let's say I have this, the image size is 5 by 5, then the filter is 3 by 3. The filter, this is the filter, and this is only the region this taken from the image. To multiply it, the convolution, we have already discussed this. And let's say 5 minus k, which is 3, plus 2 multiply 0, which the padding is 0, it's equal 3. So the output will be 3 by 3. And if we take this example here, 32 minus 3, which is the kernel size or the filter size, plus 2 multiply 1, which is a padding 1, divided by 1, it will be 32. So if you see here, the image size, the feature map is exactly the same size as the input image because we have a padding is equal 1. And if we have padding equals 0, we will reduce the image size, the output size into 30. Thanks for watching. Everyone, welcome back to my channel. In today's video, I will try to simplify the method how to calculate parameters in the CNN, and this lesson will be you will be able to calculate the number of parameters in any layer or in any network. So let's get started. So as you can see this formula here, this is the formula how to calculate. This is using to calculate the number of parameters. So if h is the filter height and if w is the filter width and cn is number of input channels. See, please be careful in this double line in under this one here, and number of channels in input image. Let's see, and n is the number of is the number of filters. Also the number of, let's say, output channels, and also this one here, it should be in indeed. Let me just change it to number of. Its number of parameters. It means one bias for each filter. Each filter has to have one bias. So let's get started to see the image. So assume this we have this image here. Let me just go this. I have image 5 by 5 and the filter has 3 by 3. So to calculate number of features, the features is only these values in the filters. So if we calculate it, if we just count it, 1, 2, 3, 2, it's 9 plus 1 for the bias. So it's 10 parameters. For this network, for this, let's see, image, I have 10 parameters. Or let's see, for this convolution layer, I have 10 parameters. And now, if I have this image here, let's see, 20 by 15. What do you think? Do you think I will have many parameters, or I got the same parameter? Let's see, 10 parameters. If you see 10 parameters, you are right. If you see rather than this, it's false. So this is the advantage of neural network. So what you have, the number of parameters, only these parameters, it's regardless of whatever image size is. So they are only focusing on number of channels. So if you see here, this is considered as a grayscale image. It's 2 by 2. I mean. Two-dimensional array, n by m, and number of parameters for this image and this filter here, it's only this filter's 9 plus the bias. But let's do it with this formula here. If you see, filter height is 3 and width is 4, I mean 3 by 3, and number of channel, as you can see, it's only one channel here. So it's not it's a grayscale image, not a color image. In a color image, you have 3 channels, but we will reach this in the coming section. And this one here, number of filters. So we have only one filter, and this is the bias, number of bias, because we have only one filter. So it's 3 times 3 plus 1 is 10 parameters. So if we see here, this image here, it's 5 by 5, the old one, but now I have 3 different filters. So by the way, you can have many filters, whatever you want. So number of filters, let's see, it's arbitrary number of filters. It depends on the algorithm indeed. But let's say this is the image, and I have 3 filters here. So because I have 3 filters, indeed, first the width and height of the filter is 3 times 3, and times 1 number of channels. So I have only one channel in this image. So it means 1 times 3 number of filters. It's 1, 2, 3 plus 3 for each bias for each filter. So it will be 30. And try to calculate it with this image, 20 by 50, of course it will be the same as the one. So let's have a look in the color images. So assume that I have color image, and my image is 32 by 32. It has to be, sorry, by 3. And because I have 32 by 32 by 3, the 3 is the number of channels. And in this case, I have 3 channels. So, so please don't confuse between this. And for this, I have each filter has to be, I mean, the dimension of the filters, or let's say this channel here, the last number here, 3, it has to be identical to this. So this has to be connected to, for instance, this one here, 3, it should be as this one here. So in the let's say in the if you go deeper into the network, so you will have this channel here will be 200, for instance. Okay, so this will be, for instance, times 200, and number of this channel of the filters, it will be 200. So oops, hopefully this should be clear. Now I'm assuming that I have image 3 channels, so 32 by 32 by 3, so red green color, and the filter size is 3 by 3, but I have number of filters is 64. So it means I have 64 filters. It means 64 3 by 3 by 3. So just as a recap, how this working, it's already discussed in the previous videos. But for the color image, this filter, for instance, this is the first layer here, will be convoluted with the first layer in this image, and the second one will be for the blue image, and the third one will be for the red image. And the summation of this will be, I mean, the result will be summation of all of these filters and put it in the output of the feature map. But let's apply how many parameters do we have here. So as I said in the beginning, or mentioned in the beginning, image size, it's not affecting on the number of parameters, only the number of channels. If the number of channels is great, is 1, it means I will have the same parameter, for instance. If I have 3, I will have 3 filters. If I have 200, I will have 200 layers of the filter, right? And let's see now, width, I mean height is 3, width is 3, and number of channels is 3. I mean the last channel, or let's see channel, is 3. It will be 3 times 3 times 3. Now multiplied by number of filters. So I said here we need 64 filters. It will have 64 filters plus 64 bias for each filter. So each filter will have 1 bias. And this is for the color image. And hopefully you can get this, and it will remove, let's see, or eliminate the ambiguity in this number of parameters. And in the previous video also, I showed you how to calculate the output, the feature map size. So please go and have a look. So if this video helps you, please subscribe into my channel, like this video, because this preparing this video, it takes much time. I mean, this tutorial. And if you have, of course, any question, drop it down in the comment below, and I will answer it, of course. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. If you have been following our CNN series or machine learning playlist, you already have mastered filters, feature map, CNN operations. Today we are diving into something that might be look simple, but it's a powerful. It's a pooling layers. So okay, so imagine you are looking at a photo, but from little far away. So you didn't see every pixel, but you will still recognize the image. So that's the intuition behind pooling layer. It helps see and see a big picture without getting lost in tiny details. So let me just show this example here. I'm seeing here a dog, right? And if I just zoom out and, for instance, minimize it to 50% and even 10%, I still can see the dog. So this help the neural network, let's see, to work efficiency without having, let's see, um, big load in this in the network. So why do we need the pooling layer? So CNN, as you see, it can create a massive of feature maps. Because it's extracting a complex and many features. So, but it's a good for learning, but it's a bad for memory and speed of the algorithm. So pooling it steps into reducing the size of the feature map, so that will lead to speed up the training and also make the network more robust to small shifts, like when a cat moves in a slightly left in the picture, let's see. And also it's try to reduce or prevent the overfitting. So how does it work? So it's like, let's see, it's break the image down. The most technique, it's max pooling layer. It's try the window is like 2 by 2, and as you can see in this example here, and it slide over the image, the feature map, and taking for a 2 by 2 the maximum value here. And for each window, it will keep only the maximum value. For instance, here 8, 6, 9, and 9. So why max? I mean, because there are several other types of polling layers, because it's keep the strongest signal, like highlighting the most confident detections in the area. And type of polling layers, you can see, for instance, average polling layer is taking this is the maximum one, and here's the average, and it takes the average of the value. Let's see, 2 by 2 is taking the average of this, and this will lead to smoothing the features. And the global polling is shrink the entire feature map to just one value, which is I'm not quite, I haven't used it indeed, but this is the what it's used in the previous researches. And these are, let's see, common more than CNN. Of course, you can also see the mini polling layer, which is not really used, but still this for instance, max and averaging and global is still using in a certain architectures. So is there any hyperparameters for this, for the convolution, for the polling layer? Of course, it's like convolution. Polling use window size, as you can see here, the window size and the stride. So sometimes you need maybe to move uh, for the next. Let's see, you can see here it's moving. The stride here is 2, because we use this and this. And most of the cases there is no overlapping between the polling layer. This is what I have seen in the previous. And you can see this cut the feature map size into half. So it says 1, 2, 3, 4. It's 4 by 4. It's the output will be 2 by 2. Let's see this one here. So where it fit in the CNN, where I can see this polling layer. So polling layers comes right after the convolution and the activation. So I'm just following the same structure. For instance, I have the convolution, then the activation layer, and now the polling layer. It's after right after the convolution and activation. It's a cleaning, let's say, cleaning up. So it's try to tidying the feature map before passing it to the deeper layers. And for the real application, for the real, let's say, example, so in a let let net is use polling layer. Let's see, for instance, let net polling layer. It's using, I think, average layer, average polling layer. This, I think, yeah, I think, yeah, I'm quite sure this is uh, pooling. Let's see pooling layer, which, oh, let's ask question. Yeah, it's using average pooling layer. And FGG and AlexNet using max pooling layer. Let's see which pooling layer in VGG. It's a max pooling layer. Yeah, it's a max pooling layer. And also a ResNet, it's using the global pooling before the classification. Okay, and let's see the with polling, yeah, this one here. So as I said in the beginning, it's reducing the the benefit of using polling layer is reduce number of the reducing the dimensions, and it helps also the translation, the invariance, and keep the network more efficient and fast. And some guys, they use the only the stride convolutional and to replace the polling layers. But yeah, for instance, it's almost the same because stride, if you increase the stride, it will also reduce the feature map. And yeah, pulling down simple feature, it's also down sampling of the feature map and keep only the most important one. And max pulling and average, it's almost, let's see, the most popular one. And this will try to reduce the size, speeding the training up, and also try to prevent the overfitting. If you have enjoyed this, please try to subscribe into my channel and like the video, and of course comment below if you wanted to give to dive into the global polling or attention instead of polling. So also, if you have any question, please write it down in the comment below. I will answer it. Thanks for watching. Welcome back to my channel. So as we have discussed in the previous videos, what are the main components of the CNN, and we figured out that activation function is one of the main, let's say, components. So imagine your brain is decided, let's say, to select whether to react or to stay quiet. That's what activation function do in a neural network. They decided whether a neuron should fire or not based on the input signal. And as you can see here, each output, let's see, this is for instance a hidden layer here. This is the hidden layer. I'm just trying to lock all of these. So let me, oops. So when I click, I will, okay. So each hidden layer, after this is, let's see, the input, and this is the hidden layer. And after calculating the summation of the of the linear regression, this equation of the linear regression, now we have the activation function, and the activation function is after applying the activation function to this value here and to the output. So if in case if we have a sigmoid function, let's say binary classification, we will use a sigmoid function. So our first guess is a sigmoid function. It takes any number of, it could be a negative or zero or huge number, and squeeze it into a range between 0 and 1. So why we need it to between 0 and 1? See, it's like when you have values between 0 and 1,000, it's hard to interpret it. And when you have it, if you squeeze it into between 0 and 1, you can it's easy to interpretate this. So it's like it will be as a confidence score or probability or maybe binary decision. So it turns the signals into how likely values, for instance, between 0 and 1. And let's have a look. This is in this feature map here. So the raw values, this is for instance the input image, this is the filter, and this is after convolution. This is a feature map. And after the feature map, we have the activation function. So as you can see here, the raw output from the convolutional layer, this is number can be range between 0 and 15, from 0 and the maximum one is 15. And it's like messy. It's not easy, let's say, to anticipate it, right? Now see, we apply sigmoid function. This I have applied a sigmoid function to every number in the future map, one by one. It's a pairwise, so it says the taking the 5 and replace it with x and calculate the activation function for this pixel, for this output, and do it for this and for the whole matrix. Let's see. And for instance, 5 will becomes 0.993 and etc. So if you can see here, the transformed function, think of it like a heat map of the confidence. A lighter means lower activation, and the height value, it's a strong signal. This is and every value is now normalized, making it easier for the next layer to work. So when you normalize normally in neural network, it's not we normalize the input images, like it's not let's say we didn't input as a numerical from 0 to 20 220 255. So it's like uh, normalize this between 0 and 1, so it will be easier for the calculation. So, and you can see here, this is a simple table that show several activation functions, and I will start with this. When you should use a sigmoid, use sigmoid when you wanted to express something in terms of how sure are we. So it's perfect for binary classification. So assume you have two binary binary classification, two classes, and you would like to see which one is to select. So the probability or using a sigmoid function is better. It's better to use it in this case. And yeah, and for the attention, it's also use attention, but it's carefully tried not to use this. Let's see, in a hidden layers. So avoid use in the hidden layers, and it's only used. It's better to use it in a classification for binary classification. Why we can't use it in a hidden layer? Because it's vanishing, it's gradient. So the value of this, the output of this might be close to 0, and if it's close to 0, it won't be let's say it will somehow freeze or stop the, not stop, but freezing the learning, because it's almost 0, right? And the leaky is, so we use in the hidden layers we use a relu function, which is just taking the max, so it's only taking the positive values. Any negative values will be ignored, it will be replaced by 0. And in this the advantage of this, so some, let's see, many neurons, let's say for instance many values here, this is a features map, it will be sometimes it will be let's see 0 inactive, and etc. And why we need indeed the activation function, that this could be an interview question, because it's adding non linearity to the network. So if we have no, let's see, if we ignore the activation function, the deep learning, the neural network will act exactly the same as the linear regression algorithm. And I will just have this. It's a short, let's see a short code how to apply this, because this sigmoid function is already implemented in, let's see, you can just use it in from Torch, PyTorch. It's by importing neural network, and you can see this is a sigmoid function. Yeah, I think that's enough. And for the next, I will try to implement all of these components in one project. If you like this video, please subscribe into my channel, like the video, and if you have a question, please drop it down in the comment below. I will answer it. Thanks for watching, and see you next time. And welcome back to my channel. In today's video, I will try to show you or explain you how what is the FGG16 and how it's working. So if you have been following my previous video, you're already familiar with the building blocks of, let's say, convolutional neural network. Field has polling layers, activation functions, and more. But today I will try to make them let's see, and real video. So you might heard about FGG16. It's one of the most, let's see, deep learning algorithm in the history. I would say it because it has a good performance. So why? Because it was groundbreaking when it comes out in 2014, and winning the ImageNet competition, and it's still widely used today for the tasks like image classification, object detection, and even for the feature extraction for transfer learning. So I also use for this for the feature extraction, and also use it for compute the similarity between two images. So you can use it for the images because extracting the features and just calculate the similarity. And you are not, let's say, you don't need in this video I will try to break it down step by step, both theoretical and implementation using Python and PyTorch. By end of this video you will not only know how the FGG16 works, but also able to build it your own version from scratch. And let me just ask you some question. Have you ever wondered why some models perform better than others? Because there are many, many models in the neural network. In the so this is why FGG, because it's really simple, but it's really the performance is really competitors, I would say. And because they say the principle behind this, the deeper network, the better the ability to learn complex patterns. And this is exactly what FGG16 is doing. So what we will learn in this lesson, theoretical understanding how this, for instance, numbers is presented, and why we have get, for instance, 112 times 112 times 112 8. Let's say why is this, and I also you how the image process through the convolution neural network, pooling and fully connected layers. So I will select two, or let's say two from the beginning layers and the last layers for the connected, because if I explain this, it's this and the rest are the similar to the previous one. So you don't need to repeat every steps in the whole diagram, let's say. And I will also show you how to implement this in a very easy way. It might be easy, yeah, in a PyTorch. And let me just show you this. This is the diagram. And if you see, the image size is 224 by 224 by 3. And why we have this? This is the implementation. This is the idea of the researchers. So if you have image like 500 by 500 by 3, so in the beginning you have to resize it to 224, 224, 224, 23, sorry. And this is if you need to use it for classification, for instance, if you would like to classify, just use it as it is, let's say, and use it for classification. You have to resize the image into 224 224 2 times 3. And of course you can use let's see, bigger images with different size, but for feature extraction. Or if you would like to use a different size, different input size, you have to retrain the network, so it will should work in with your data set. And as you can see here, it contains 16 layers, and 30 is convolutional. So you can see 1, 2, 3, 4, 5, 6, 7. This is the convolutional one, plus ReLU is this shape, and the red one is the max pooling, and this is the fully connected layers, and this is the soft max. This is for the classification. And why it's for the classification 1000? Because it's classified on the trained on the ImageNet dataset. So if you see, this is trained on this dataset, and it has 1000 let's see, classes. As you can see, this is the dataset or the images that it's trained on. See, it's 1000 class. It's fantastic indeed. And yeah, so as you can see, the input image is as I said, 224 by 224 by 3, and the pressed block, let's see, block 1, this one here, it has two convolutional layers plus polling, max polling. So as I explained, polling, it could be max, average, and mini, max, and etc., and even global. And now plus 2 conf layers plus 3 conf layers, and he max polling plus 3 layers, and etc. So as you can see, how many parameters he in this network? In this network, it's about 38 millions parameter. So someone will ask why it's too much. But if you compare it now with the fully connected layers, let's say a dense layer, you will have a billions of parameters, and it won't work like FGG. And the filter size is 3 by 3 in all all the network, and they use only a ReLU activation function in each layer. They have ReLU activation function, except this they have using the softmax. And they are also using drop out for the before the classification. So it's somehow to avoid the overfitting. And also you see max polling, it's 2 by 2 stride 2, and it's somehow just taking the half of the output. And all activation function, as I said, it's using ReLU function. Let's just recap all of this, how the conf layer is working. You can also see my previous video, but just as a recap, if you haven't followed my videos. So this is the convolutional network. You have this image, and you have this filter here, and this filter, it will be selected, let's say a region 3 by 3, and try to multiply by the filters, and you will get the output here. And for the stride, it's like would you like to move to have the overlapping between this moving sliding window? So if you see here, one, and the next one is moving here, so it means the stride is 1. So it was beginning from here, this rectangle here, and the second one is here, so it means it's only move 1, stride is 1. And if you have 2, it will move 2. And the padding, sometimes we have important features in the borders of the image, so that's why we need somehow padding. And for the activation function, after the calculation of the future map, we need to use the activation function. So that's only we need somehow the dominant features that should be kept. The other one should be really removed. And for instance, this is I'm using here sigmoid function, but in the BIBA itself they use ReLU. And the polling layer, it's like reducing the half of the image. So why we need to reduce the half of the image? I have already explained in the previous video. Please have a look. I will just add the link here. And it's like reducing the image size with keeping the quality of the image, and also this will lead to increase the speed of the image of the network. So let me just start with with the first input layer. So as you can see, the image size is 224 by 224 by 3, and I have three filters, and they have stride 1, padding 1, and all the parameters and all the layers and number. But here in this layer I have 64 filters. It means I have 3 by 3 by 3. Let me just me oh, I think I'm not quite sure if I can do it, but it's not needed to do it indeed because already explained in the previous video. So because I have I have image color image with 3 channels. So in this case I have to use 3 by 3 by 3 filters, and number of filters it will be 64. Now how to calculate the feature map? Why we have, for instance, this here. This is the feature map or after the first and second convolution neural network, because we have using padding 1, we will have the same image size. So as you can see here, the width, this indeed has to be calculated for width and height. So, but because here we have the same width and height, it's the same. But for some any cases, you will have different input. For instance, 300 by 200, 332 by 224 times 3, let's see. And for that, you need to calculate the width and height, the output width and the output height. But this will be done in the neural network, so don't worry about this. And this is how to calculate the output size. See, let's see, I have the image size is 224 minus 3, which is the kernel size, which is in this case 3, plus 2 multiplies the padding is 1, and divide by the stripe is 1 stride. And this we will have the same image size here. As you can see, 224, and of course the height will be 224. And the feature map of the first convolutional neural network, it will be 224 times 224 times 64, because we have 64 filters. And you can see here, this is the width of the filter, the height of the filter, the number of channels has to be identical to the image input image. So you see, I have here 3, that's why I have here 3. And number of filters, I have 64. So to calculate the parameters, number of parameters for this convolution, first let's say conv1. So you have the the filter width and height multiplies the number of channels times number of filters plus number of filters. It's 3 by 3 by 3 times 64 plus 64. This will have 1000, let's see, 800, almost 800, 1800 parameters only for this layer, for this conv1. For the second conv, we have, because we have the same parameter, the same config, let's see, 3 by 3 and times, and we will have the same number of features, let's see. And this is, let's see, this is the output from the conf1. It will be considered as an input to the conf2. And because we have a number of parameters 64, we will get 64. But here, there is a difference here. So as you can see, the filter size is 3 by 3. But how many channels in the output layers in the feature map, which, as I said, this will consider as an input to the second conf. So I have 64. That's why I have number of channels is 64. And times number of filters, it will be 64. And for this, you will have the same parameters here for the conv2. And now the second one, let's see, component is this red here. It is max pooling layer. And this max pooling rank, as I said, it will reduce the size of the image into the half. Why we into the half? Because we have used 2 by 2 and the stride is 2. So it means half of the image will be removed. By the way, after each conf1, after each conf layer, we will have the ReLU, and the ReLU will just keep the positive values. And let me just, where is this? Okay. Oh yeah. So the after max pooling, I will get this layer here. And as you can see, the feature map, the output of the conv2 is this one here. And to reduce this, I have this is divided by 2, this divided by 2, but I have to keep the channels. This channels, you don't need to touch it because it's only, assume this is 64 images, consider as 64 images. And for each image, you will reduce it to the half, but you still have 64 images, as you can see. And this is the feature map after let's say a pooling layer. This here, this here, in this point here, and at this point, no, sorry, in this after this point here, this is the first pooling layer, and I will say I will have uh, 112 times 112 times 128, as you can see, to 26 indeed. And this, as you can see, this one here, it's the next layer. It's the conf next layer. So as you can see, this is my feature map after the max pooling layer. After the pooling layer, I will have this. Now, see here, this is the magic here. So I have to change this. Sorry, this is should be 3. This is the third conf layer. Let's see. And now I have, this is the input, and I have 64 channels. But for this for this layer, I have 128 filters. So number of filters will be this one here. So after the convolution, you will get the output map. Let's say the output feature map. It will be 112 times 112 times number of filters, 128. So this is the output layer of the third convolution layer, and you will do it for the second, for the third one, for the second one here, and you will get the same image size. Let's see the feature map size, because it's not any more image. And after that, you will have max pooling layer, and this max pooling layer will reduce it to 56 times 56 times 128. There's a times here. Just you might confused. And this is our, let's say, the size of our network in this layer here, and this one here. Now I have, and you can repeat every layer as the same as we have done here. So you just to have to take care about how many filters, what is the feature map size, and etc. Now let me just see the this fully connected layers. Why it's 4096, and it somehow confused most of us. Let's see if you read it in the beginning. So as you can see here, this is the beginning, the conf layers, and after the max, after the max pooling, the max pooling layer, it will reduce it to the size here. Now assume this is, we need to flat this. What does it mean that? It's just to have it in one line. Let's see, in one list, and it's like this. We just move a little bit here, and if you see 7 times 7 times 512, it will be 25,088 value. Let's see. Imagine this is as a block, but if you just concatenate all of these values, it will be this filter, this vector here, and it's from 1 to 25,088 value. Now for that, we will have a new connected, let's say a new node with 4060 96 Yeah, so I have maybe to add this. It's my mistake. Sorry. Okay. So it's like this. And this is the latest one. Let's see. Yeah, just forgot to add this. And for this, we have to connect. Okay. So let me just, yeah, it should be like indeed this. And because this is the input, and this is, let's see, after flatting number of the after the pooling layer, this is, we have to flat this and connect this with 4096 features. And as you can see, each node from this, it has to be connected to all of these nodes. That's why it's called fully connected layers. And finally, you will have, sorry. So yeah, why it's like showing 1 times It's like this. We have the width and height and channel, and in this case we have only channel. I mean width one, channel height one, and the number of channels will be 4000. That's why it's showing here 1 times this one here, and it will be also the same as the class label after the class label. So you see here after this, we have three different layers, fully connected layers, and with the same size. And after that, we will apply a softmax, and getting the number of classes is 1000. Of course, you can change it to whatever you want, but this is, let's say, the main paper, the implementation. And let me now show you. Let me just save this and show you how to implement this. And as you can see here, let me just back to this, and you can see we have block one, which is contains it has two conf layers plus max layer, and each conf layer, it has a reload function, reactivation function. And let me just see it. I will try to implement not like this. I'll try to implement it, let's say, very simple, I mean, without taking care of a clean implementation. Of course, we need to implement a clean implementation, but I would like just to make it easy for you. So after importing the torch, we need to import the CNN. And now let me just create a class FGG, let's see, 16. No, maybe this is already in the, let me just say it like this, 2016. And this has to be inherited from the NN modules. And this, let us define init. Oh, it's cool. So we need the number. What we need number of, let's see, number of classes. We need to have how can we say num classes. Oh, let me get clear. Num of classes, and let's have the default value with 1000. And for this, we need to initialize also the super class. So in the super class, we need, of course, FGG16 self, and now calling the main function. Let's say the main class of the FGG. Now we need to have the convolutional layers, right? So let's start with this comment. conf layers. So we need to have self dot features, and we need to create now a model nn dot sequential. It's because, as you can see, it's a sequential of sequence of layers, right? And let's have a look. Let's have this and move this, and you can see we need number of nn. We need in the beginning we need a conf layer, and the conf layer, as you can see, this is input layers. You can see input number of channels. In the beginning, it's the image size is 3, and the output channel, how many filters do we have? We have 64. Now we have the kernel size. It should be kernel size. We can also just do it like this. In channel, just so to make it, let's see, clear. In channel, now we have okay. Output channel, it will be 64. Now kernel size will be 3, and you can see here the parameters. Padding, it will be 1. This, I think this is enough. This is for the first layer. Oh, we have this. Now, after, as I said, after the conf layer, we have after the each conf layer we have relu. We have relu. Relu has no parameters. Now I will also need the second layer, conf layer. I will just copy this and put it here. So we need to take care now. So number of the input channel is the output of this. The input layer of this, I mean the number of channels, and this it should be the output of the first layer. It will be 64, 64, and the output channels, I think it's 64, yeah, of course, 64, and the padding, and also the reload. Now let me just go back to the you can see it has 2 conf, then max polling layer. So we will add the polling max polling layer. Let's see, nn dot max polling 2d. The kernel size is 2, and the stride is 2. Let's see, this is for the first block, and of course we can also make it more efficient if we can create a function that can create, let's say, make a layers, and we put different input and output. But just as I said in the beginning, let's make it easy. Block 1, and for the block 2 we will have the same indeed. We have just, we need to make it 2, and now we have the input size. You can see the input size, it should be 64, and the output size is 128. You can see 128. You can see it here. And of course, kernel size and padding, it's almost the same in all the layers. And the input here, it will be 128, and here 128, and the size will be the same. Now we need also just to copy the block, C block 3, and the input size the input of number of channels will be 1 2 8, and the second one, the second let's see, the block 3 number of filters will be 256. So this is the output, 206, and this will be as an input and also as output, because we need to have the same as the image size, I mean the feature map size as the input size. And here we have the stride one, and here block 3, and let me just pause the video, and I will come back to you when I just finish this, because maybe it takes time to just to save time. Yo, so as you can see here, I have the first block. Sorry. So as you can see here, I have 4 blocks. Let me just show you the images. I have this is number of blocks. I have 4 blocks of conf, or 5 blocks. So, and you can see this is the fully connected after the flattening, the fully connected layers. So let me just see, 1 2 1 2 3 4 5. Let's see, 5. So this is the conf layers of the FGG, and this the last one is the fully connected layer, the fully connected layers. As you can see here, we have 3 different linears. Linears, it means fully connected layers. And as you can see here, this is our output from the last block 5. So the block 5 will be the output of this after the max pooling. It will be 512 times 7 times 7, and this is, well, as I explained, in this fully connected layers, this one here, this is the last, this one here. So after flatting, I will create 4069 layers, fully connected layers. Now we have the ReLU, and dropout, it's used for the training indeed, and the dropout I will explain it in more details in the next video. And the dropout is somehow drop. It means it's from the name. It's some neurons will be dropped or ignored. Will be let's see, reset to zeros, and this dropout is one method or effective loop from the preventing overfitting. And yeah, so you have the second layer, and this is the number of classes. After that, we'll have number of classes 12 1,000 class. Now this is only the features. This is the features, and this is the classifier, right? Now I need a function how to which called in the PyTorch is the forward function, how to calculate this, how to use this for the H image. Let's see, define forward function, and the input of forward function is, let's see, self, because it's belong to this class, and the input function, the input parameter is x, which is the image indeed, and I will see x is equal to self. Then I will go to the features, and the feature, it will be as I input the features. Now I will flat the output. So what does that mean? So we can see here, for instance, I have the image. Now these features, it will be called, And this feature, because it's a connect sequential layers, it will try to apply conf1, I mean block 1 till block 5 with this image here, with the input image x. Now the output, as you see here, it will be 7 times 7 times 500. Let me just add it here as a comment. 12 times 7 times 7. This is the output of the max. Let me just put it here. Now we need to flat this. So you can see x dot view should be this one. So you see x dot size 0, then -1. It means flattening the tensor. Flatten the tensor. So after the flattening the tensor, I will try to get this, I mean, put this as forward this as an input to the classifier, to this block here. So you see x is equal self dot classifier, and of course x, and return x. So returning this is the output, the class label of the indeed of this. And let me just, this is the implementation of the FGG, only the structure of the FGG. But now let's just initialize it. Let's see, using FGG 16. I will define the model parameters is equal to FGG. And you can see here number of the parameters we have, it's 1000, but because we have 1000, I will just keep it like this. And now try to print the model. It should give us what is the layers in this model. Let's just have a look. Okay. Sorry. Should be like this. So now because we have no image, so okay, it's already finished. I'm just waiting. So as you can see, after printing the model, you can see here it's, where's my mouse? FGG, and you can see sequential. It will print every layers here. You can see how many layers do we have, how many conf layers. I mean, you have to. It's 13, I think. It's mentioned here in the beginning. It was 13 layers. Yeah, 13 conf and plus 3, which is fully connected layers. And this is the FGG. And now how to use it and how to train our model, this we will see it in the next video. And maybe one point. Yeah, I just want to show you if I read an image and try to pass it to this. But by the way, was some mistakes here, and it was 200, but it has to be 500 indeed. And yeah, so for instance, I have read this image. I have it. It's a dog. It's an ad hoc image, as you can see here. But when you expect to have, let's say, a good output for this, because I'm not expected to have a good, because the model, it's the weights of the model, it's only initialized. So for this, we need to train the model. If you would like to use the FGG, you can also import it from the PyTorch. But this is how I did, reading the image, converted to the red, green, blue, I mean the three channels, and importing the transformer that will try to resize the image into 224 to 224 and convert it to a tensor, and this will also normalize the image into between 0 and 1, and this will be deleted. Now we will use this to transform the image, and use this, and the output will be here. And now we need to unsqueeze the image to add the batch size, because we have one image here, so it will be 133 200 240, and the image size. And let's see, just run this. I have already done that, but you can see the image size is this one, and if I see, it will try to output 1000 1000 value, because I have changed it here to 1000. And if we see, for instance, let's just change it to 5, and in case you have 5 classes, as I said in the beginning, you have to train this model to use it for the detection. It's just now a dummy example. So it should, now this should output only five values. You can see 1, 2, 3, 4, 5. It depends on number of values, because this, the output is mentioned here. The non-linearity will be number of classes, and number of classes I have changed it to 5. Okay, that's it for today. And if you like this video, please subscribe to my channel, like the video, and of course, if you have any question, write it down in the comment below. I will answer it, because this took much time for me to prepare this tutorial and try to figure out what are the let's say the changes, not the changes, the challenges in this CNN, and try to explain it with examples. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. In the last video, we have seen the FGG and theoretically, and also in a Python, how to build, how to let's see, write the architecture of VGG16. And as you have seen in this, in the, I mean, in the last video, I have shown you these steps. Now we would like, as I said in last video, this only the structure, and we would like to use this structure to train our model and see, let's see, building a model for instance, for image classification, and see how it's working. So let's just start and continue with this stuff. So for this, let's say I have added, this is our structure. Now I need, what I need a data and data loader. So let's say this is to load the data, and transformer. So transformer, this after loading the images, we need to transform the images. So all pixels, let's see, have to be normalized and considered as a sensors. And the next one is using the loss function, and for this we will use the cross entropy because we have, let's see, multi classes. So if you have only binary class, you can use entropy or softmax for the You can use cross entropy or yeah. And we need also optimizer. So this optimizer, it's working in a back pro propagation. So this after calculating the error, see how is this working, the training? It's reading, I mean extracting the features of all these images. Now try to predict with this classifier here. And finally, let's see, is it classified correctly or not? If not, we need to optimize the model, the network. So we're using optimizer during the back propagation. We will use Adam optimizer, adaptive momentum. And also we need a for loop. Just because it, I mean, I want to make it super easy for you to understand it. Load for loop for the number of ebooks. So how many let's see iterations we would like to go through these images, the whole images. This is the for loop, and the second loop is loading loop. This way I write it as a code, don't worry. Loop 2, reading the images in batch. So this batch size, it means you have, let's say, a big data set, and it's not easy to load all of these in in one time, let's say, in a memory. So that's why we need to use a batch. So every time we will read, let's see, 2 or 3 images or 10, depends on your GPU's capacity, right? And this is the main, let's say, the main important aspects. And let me just try now to load to import the transformer and data. Let's see, we start with the data loader. So from torch, I have seen the torch before. Yeah, from the torch dot utilities dot data import data loader. And the second one we need this is for data loader. Yeah, I should start with the data set, but yeah, it is fine. And also we need this is to read the data and also loading the data indeed. And I need, let's see, a transformer. So from torch vision import transformers. This will as I said, this will transform the image from raw images to the format that will be readable by the model. And also I need to add the optimizer. Let's see, from torch import optimizer, and we will define which optimizer we need. So let's define now the transformer. So I'm just having the data here. It's nothing. It's just only C1. Let's see, for instance, class 1, class 2, class 3, class 4. This, for instance, for the training. And for the testing, we will also have the C. So this is only a dummy example. That's nothing. So if you see here, it's the same images in each class. But just to show you how thing is working. So as you can see, for instance, I have the folder here, and I have 3 different folders. If I need, for instance, if I have 3 classes, and the dog folder, let's see, dogs folder will have many images. I mean, only the dogs, and the cat will have only the cat's images, also the pets, etc. So let's add the transformer because it's important. Transformer. So transform. I have seen I showed you the trans. This is enough. Transformers dot compose, and you have see this, right? And also this. So the first step, we need to resize the images. So transforms dot resize, and we have the image size. Let's see, like this, and also image size. This is considered as a parameter, but we should define it here. So let's see. Because if you would like to change it maybe later. So this is the image size, and we have also, this is the transformer. Yes, so we need it as a size, so we need as a size like this. Now we need to transforms to tensor. So we need to convert this to tensor, and we might also need to normalize the images. So normalizing the images to make it as the ImageNet. So transforms dot normalize, and we have mean, it's equal, let me just see what is image net trans normalize, yeah, trans normalize. Yeah, I think this one here. I'm quite sure this is what we are looking for. Okay, let's see what's going on. So this one here, this is a transformer. Once we read the image, we will try to resize it, convert it to a vector, and normalize it. Make it so, for instance, the normalize, after normalization, we will minus the mean divided by the standard deviation each channel, and we will have the values between maybe -1 and 1. And now we need to load the data set. Let's see, data set. For the data set, we have train data. It's equal data sets. We have imported over. Okay, here we have to import it as well. So data sets dot image folder. Yes, image folder. We need root equal. Let me just see this. Tree directory. Let's see like this. I have the train directory, I'm sorry, maybe the time is moving. I'm not quite sure, but let me just do some stuff, and I will try to stop and also now transform. It's equal to trans. This is for the training dataset, and you have to do it for the dataset or the dataset for the validation also. Valid data. It's equal the same, I will see, but this has to be different directory. But for me, for now, I will just keep it as it is. So, because and now I need the training. This is the training data. Now I need train loader. Train loader is equal data loader, and we need to have data set is equal to train data batch size. It's, let's see, optimal to define the batch size as well here. So let's see, each time we need to load 4 images, maybe because my GPU has it's just let's see, not that optimal. And what's this batch size? I will batch size, and there's also one option, as you can see here. This is the options that you would like to see. So I mean to use pin memory, false, drop, timeout, number of forecasts, but number of forecasts it's not working in a not working well in Windows. It's better to try it in let's see, in a Linux. And yeah, this one here, shuffle data. It's, let me make it true. So what is this does the shuffle? So every time we load the data, and maybe we and at each ebook we will have a different images in different ebook. So it's better to have it like this. But for the validation, let's see. I will just have copy this and valid. And as I said, this we need to change it to valid. Valid data. Why it's not defined? Okay, valid. And for the validation, we don't need to shuffle this, because we need to have the result for each time the same. I mean the same data set, the same image. Because if you shuffle the data, you will get different results. We need to control the algorithm and see how is this working. Now we have all the, let's see, creating this model. Let's just put it here. I think we can add it to device, right? To device, yeah. What is the device here? It's called it might be a CPU or GPU in your stuff, but you can see here. Check if you have, let's see, for instance, device is equal torch dot device torch dot device CUDA. If it's CUDA, if torch dot yes, torch dot CUDA. We need to check if it's available. Yeah, is available. So use Tosh if available. I mean CUDA if it's available. Else CPU. Now we need to remove this and see device. So by the way, I have shown you maybe in the all the videos, I mean in the same playlist, how to install the PyTorch, and you can see here, for instance, I have Torch version CB, I mean CUDA 11, and the source is from Torch, and the Torch is here. Now, even if you don't have a CUDA, I mean a GPU, you will have installed the CPU by default. So this installation in a TOML file with Biotree will save you much time. So let's be back here. I don't know how many classes do we need. Let's keep the default. How many? What was the default here? 5, maybe. Yeah, no, we need to have it for 4 classes. I mean, because I have 4 classes here, so should be like number of classes should be 4, just to be in a safe side. Now we need the loss and optimizer. Loss and optimizer. So loss is equal in entropy loss, and the optimizer, it's equal to opti. Now we need to define which optimizer. So I have also described this. What is the Adam? What is the stochasticated gradient descent? What is the ADA group, and many others. So please have a look in my. I will add the link. So you'll have add them model dot parameters, taking the updating the model parameters, and we have the learning rate. We also need to define the learning rate as a parameter. Let's see, parameters should be here. Learning rate. I don't know, maybe this, or just, and we have it here. Now we need a training. Let's say we also need a number of iterations. Epochs, number of epochs. See, 10 or 100, depends on your, as I said, in your capacity. So let's say for epoch and range epochs. So this will start from, because I have 10, it will start from 0 to 9. Now I have model. Now because I have to train the model, I have to add this train. Let's see, running. We need to see the loss. Running. Let's see, loss is equal 0 in the beginning, right? We need to have also this correct classified as well 0 and total is 0. So we need also now another for the images labels, and we will get this from train loader. So images, we need to put this in a device, images dot to let me just check this device. Yeah, sometimes we need to put it in if maybe you forgot just only to have the device. So what we need to get the model device itself and put it here. But we already have this device, the image device, and we also need the labels. Labels to the device, and how to call model images. So we will try now to predict the images, and we see the output somehow here. So now we need to calculate the loss. Loss is equal, I have put it here. Let's see, we need to add, because it's the same name, criteria. We will have the outs, then the labels. This will calculate the loss, the difference. Let's see, and we have the optimizer dot 0 grad. So you can see set all gradient optimize 0 to 0. So this is in the beginning, it will just put it as in the 0. Now we have loss dot back we have loss, yes, dot backward, I think backward. It's not showing any. This is the criteria. We have to find it here, of course. Now we have the out, the labels, optimizer, and now we need to calculate to update the network with this one here. But dot creatures dot backward. No, something wrong. But let me just do it loss. Just because this is calculating the loss, then we need to update backward. I will check this later. And after calculating, we need to optimize the optimize the network dot step. Let me just check this one. Indeed, I have checked this back and it's not giving any issue. Now let's see. Now we need to calculate, so sum up the running loss plus equal loss dot items. So we have now calculating the loss. So you could also add here if we need somehow another variable here. So we need just to print the ebook and also the loss function. Let's have a look here. By iteration is 0 to be iteration equal and plus equal 1. So we see now we see if iteration, the mode of iteration is if it's, let's see, 99, or let's say 10. Is equal 0. Then we need to print something. Print what ebook plus 1, because it is start from with 0, so we need just to add 1. Then we also out of, let's see, ebooks. Ebooks. And loss is running loss. Yeah, like this. Okay, because it takes time, I will just stop this and complete the stuff. And you can see here I have the number of ebooks, the images, and I will try. This is the by the way, the weights will be updated based on the batch size. So you can see here, I will try to load the images. For each batch size, the network will be updated. Now, after finishing, let's see, the training, the model will be saved somewhere else as you want. And now try to validate. Let's see, here's the testing data. So for the testing data, I have just loaded this, and of course we need, let's see, valid. No, of course we need another one test. We need the loader test, but for now let's use the training model loader, and we will have predicting the model. As you can see here, this is without updating any network, any weights. So with this line, you will save much time because it's only now it's prediction, or let's see, inference. So no need to update the networks. And this, it will try to classify these images and taking the highest label, the highest value, let's see. And here we will see if it's corrected or not, and we'll calculate the, let's see, the accuracy here. I think that's it for today. And if you understand the previous one and this one, of course you'll be able to let's see, to do it yourself. Thanks for watching and see you next time. Hi everyone, welcome back to my channel. Today's video we are trying to dive into a technique that changed, let's see, the neural network training, which is batch normalization. But don't worry, I'm here to simplify the concept so that you can understand it 100%. So whether you are a beginner or has experience, this video will break down a batch normalization in a way that easy to understand and easy to grasp. And guess what? I want you to join in. Feel free to ask questions, leave comments, and share your thoughts in this chat. So let me just let make this a fun and interactive learning experience together. So let's start. So what is the batch normalization? The batch normalization is a technique that normalizes the input of each layer in the neural network. So by doing this, it will try to reduces the internal covariance shift. So the change in the distribution of the network activation due to the continued update of the model parameters. This makes the training faster and more reliable. So before diving into the batch normalization, let me just make a short recap of the what is the normalization and what is the standard deviation. And the normalization is trying to scale to scaling the input into a 0 or 1, or maybe -1 and 1. So it's in a fixed interval. But the standardization, it's transforming the data, the input data that have mean 0 and unit and standard deviation 1. And this is, for instance, the formula here. I will just show you an example in a moment. And when to use this normalization, you use it to bound it your input like image pixel scaling. And the standardization it's used in the batch normalization, when your model assumes that the data normally distributed. And as you can see here, this is sensitive to the outliers, and this is not. And this is used for batch normalization. So once you see batch normalization, it means it's standardizing the data or transform your data into that have a mean equals 0 and standardized deviation is 1. So let's assume that we have this example here, this vector here, 10, 20, 30, 40, 50. Now we need, let's see, to minimize, to normalize it. So minima, we need to give the minimax. So the minimum is 10 and the maximum is 50. Let's see. And the result of this, using this formula here, so x minus the minimum of the vector divided by max of the x minus the minimum of the x. So as you can see here, 10 minus 10, so this is the minimum, divided by the 50 minus 10, and you will get this output of the normalization. As you can see here, it's between 0 and 1. So because we have mini-max scaling, so the standardization or z-score scaling, it's that we will calculate the mean of this, so the mean of this vector here, and also the standard deviation of this data of this vector here, and the result will be applying this x minus mu, which is the mean, divided by the standard deviation. And you can see this is our result. So this is before the standardization. This is our original data, and this is after the standardization. So now, if you calculate the mean of this, you will have 0. If you calculate also the standard deviation, it will be like this for this value here. But let's say it's almost 1, so it will be considered as 1. So let's just have a look in if we have data. Let's say you have a data set of house pricing, and this is few features here. So now, how to do the standardization? Standardization, it will take each feature and calculate the mean and standard deviation of this, and then apply this formula here to each value. So as you can see here, this is the size. I mean, I did it for the whole data, for the all columns. But let's say this is the original data, and this is after the no the standardization, or let's see, yeah, standardization. It's batch normalization, and batch normalization, as I said, it works only for features. So each features you have to calculate the mean and standard deviation, and you will also do it for this and for this. This called, let's see, I will just keep it simple to batch normalization. And what is the layer normalization? So I will explain it in a next video in a more details. But layer normalization, it will take each input as alone. So it will take, for instance, the calculating the mean and standard deviation of each sample. And let's go back to our example. So now let's talk about when to use the batch normalization. It's typically applied after linear or convolutional layers, but before the activation function. Let's see, like ReLU activation function. Because of these layers often produce outputs when with varying scales, which can slow down the training. Batch normalization steps it stepped in the normalizing these outputs and making the network convergence faster. It's especially used for big data and complex model. So whether it's try to make it, let's say, help the model to train more efficient. So assume that you train your model with big values, let's say. And is there any difference? Let's say, for instance, if you do this, use this in the training, and maybe use this one here. Which one is easier? For instance, if you multiply 50 by 50, it will be a big value, and if you multiply this one by point 4, it will be faster. Now, let's see. This is if you follow up from the beginning, you see this is the image, and this is the filter, our filter or kernels, and this is the features map, and from here, this features map we will try to apply. Let's see. This is the after convolution layer, and we will apply the batch normalization. We will try to normalize each channel. Let's see, and before the relo function. And I have a small example, or let's see, I'll see more effective, let's see, scenarios here. So assume that I have 10 batch, 1 2 3 4 5. This is 10. Let's see, 1 2 3 till 10. And in each batch I have 3 channels, just to make it really simple. And each let's see channel, let's see, this is the 1 2 3 channels, and in each channel I just assume that it's 32 by 32. Now how the batch normalization is working. So as I said here, I have 10 batches. Now I will try to calculate, I mean, do the batch normalization for each channel in this batch. So I have 1 2 3 till 10. So I can see here, I just take only the red. Let's see, the red channel, and I will see how many values, let's see, in this 10 images, or let's say 10 channels. Uh, Not 10 channels, but 10 red channels. Let's say make it like this. And you can see here number of channels is 10, and width and height is 32 by 32. So it means I have 10,240 values in all of these channels, not channels, and all of these red channels. Let's see. And I will try. Let's say this, for instance, this is a matrix, this is matrix, this is a matrix, and this is one matrix, 2D matrix. Let's see. And how many values we see here? We have seen 10,000 something. Now I will try to calculate the mean of this, or all of these, the values all over these slides, and also calculate the standard deviation, and then updating the values of each pixel with this formula here, as we have done it in, let's see, in this example here. So for instance, this is the the result. For instance, the mean, the value minus the mean divided by the standard deviation, and here is the same for each pixel. Let's see, assume this, we will take the firstly this one here. This is the first pixel, let's see, and I will do this pixel minus the mean divided by the standard deviation, and I will have the value. I will put it here, and I will go through the next pixel until finishing this. Now I will go here. I will see the x, this pixel minus the OD calculated mean divided by standard deviation. This is calculating the standard, let's see, standardization, the channel, the red channel. Now for the training, we have to keep our let's see, uh, there are two parameters indeed we need to keep. We need four parameters: mean and standard deviation, plus plus these are the scalable parameters we need to keep this. For instance, this the scale parameter for this channel, and the scale parameter for this channel. And for instance, this is multiplied by the output of this. Now this is for the red, or let's see, for the first channel in this tensor here, and we will do the same for the next channel and also for the third channel. So, and each channel has, let's see, has four parameters. For each patch, let's see, it will has four parameters: one, two, and three, four, and this will be updated over time, of course. And let me just show this. So let me just like this, and let's see what happened during the training and testing in batch normalization. So during the training, batch normalization compute the mean and variance for the each mini batch. So so you can see the mini batch, it means for instance, I have here 10 batches. And please take care. You need to have. No, we will discuss it later. Yeah, this is a tip. And as I said, for each mini batch, we'll calculate the mean and covariance, and updating the running average. So let's say, assume this, we have 10 batches, and we will have let's see, 100 ebooks. Let's see, and our running average, it will try to update the average of all of these batches. And during the testing, instead of computing the mean and covariance for the test data, the batch normalization, it will be still used in the testing as well, but we will use the running average that calculated during the training. So this ensures the consistency and avoid overfitting in the test data. So because assume that you will calculate the batch normalization for each batch. it will be maybe overfitting. But we will use the already calculated running average from the calculated from the training data set, and it will be also saved in the model. And let's recap. Let's see how to. This is the use cases and tips. So try to use batch normalization or BN after the convolution layer and before the activation, of course. And place the batch right after the linear or convolution layer, but before the activation function. And in the PyTorch, try to keep the track running status as true. This ensures that the running average of mean and covariance are updating during the training. And for small, avoid to use it with a small batch size. So assume that in this example I have 10 batches. I will see it's good to have it 10, but assume that you will use it with one. So this will for very small let's see batches, it will try to make the network not effectively, or let's see it will have the different distributions, and you need to update it, and you need to work it to do the training for a long time, and it might be not working. But that's why try to avoid this with a small batch size. And this work perfectly with the SGD, which is called stochastic gradient descent, and Adam enhancing this the performance. So, by understanding the batch normalization, you will not just speeding up your neural network. You also ensure that these are they are robust, reliable, and ready to tackle this. Let's see, when even when the most complex task. So try to normalize your data, to normalize your batches, and watch the model to know height. So also you try to visualize the model, the let's say the output, and maybe the loss function with normalization and without normalization. So thanks for watching, and please subscribe to my channel and like the video. And if you have any question, please drop it down in the comment below. Thanks for watching, and see you next time. Hi everyone, welcome back to my channel. So in the last video, we discussed batch normalization. So if you have ever felt that norm distribution, let's say batch normalization, it's not a good for small batches or sequential data, you are not alone. Today, let us keep deeply into the layer normalization, which is a technique powering models like BERT, ChatGPTs, and the other LLM models. So, layer normalization is like batch normalization. Let's see, the close, let's say, cousin. So instead of looking across the batch, it looks within a single sample, so across all its features. So that this means it doesn't care about the batch size. So it's perfect for transformer, RNN, and even for online learning setup. So when to use this layer normalization? So here's when to go with layer normalization. It's after linear or self-attention layer. And don't use it. It doesn't depend, let's say, on a batch size. It works with even a single sample. This is the good of layer normalization. So when training transformer and RNN, and also anytime you want to consist behave in the training and testing. So because we will see in the last section, we also calculate we did the normalization and calculate the mean and the standard deviation for training and also for testing. It's not like the batch normalization. And you can see here it's ideal for text sequence and a small batch size, even compatible with stochastic gradient descent and Adam. It's like the batch normalization. So why we need it? So it's just like batch normalization. It's help your network to train faster, converge smoother, and avoid, let's see, wild gradients. But layer normalization takes a step further. No need to track running statistics. So no surprise during the interferences. So you didn't need to keep all of this, the mean and covariance for the running for the all batches. So as you can see here, assume that we have, I'm just using the same example. I have 10 batches, and let's see, each one has 3 channels, and each channel is, let's see, the dimension of the each channel is 2D, is 32 by 32. And let's say I have here 1, 2, 3, and let's see, assume that I have 10, because I have, but here. So how is this working here? So in the batch normalization, we collect all each channel. Let's say, for instance, red channels, and calculating the mean and covariance for this, and also do the standardization. Now it's not like this. So here we need each sample. So for instance, this sample will be taken alone, this sample will be taken alone, and this and this. So it's not regarding any batch, it's only channel. And you can see here, for instance, for the h, for each sample, because we have from 0 to I mean from 1 to 10, from 0 to 9, and each sample, it has 3 times 32 times 32. This, for instance, for this, the input size, for instance, this one here. And as you can see, number of values in each sample is 33,072 value. And we will start with the first sample, because we have 10 samples. We will start with the first one. And for instance, we have 3 channels here, and we will try to, let's see, flat the image into one-dimensional vector, or let's say tensor, and compare the mean and the standard deviation as usual. And now normalizing the data and applying, for instance, for the scale and shift. So it's similar to the batch normalization. And now we will do it also for the second sample, because we have here 10 samples, and until finishing this, we have this is, let's say, for this, for example, n sample, which is in our case is 10. It's the number 10 sample. And what's happening in the training and yeah, hopefully this should be clear. So let me just recap this. So we will try to first flattening the image, because not the image, it could be, for instance, a feature map with several dimension, but I'm just trying to keep it easy for you, so that's why I'm just using image. Compute after flattening the image, or let's say the feature map, compute the mean and covariance. Normalization, then apply length, scale, y hat, and scale and shift, let's say. And this is simple and elegant, and exactly what like GPT do under the hood. This is what GPT doing. So for the training, what happening in the training and sorry, I did some mistake here. So this should be so this is layer, but you can see because of the copy and paste, sometimes we get issues. View mode. And remember how batch normalization changed the behavior between the training and inference. So it's trying in the batch normalization, we save the average running of the mean and covariance. But here it's not. So layer does not do this, or saving the, it's compute the statistics per sample in both during the training and also shifting. And testing or inference. So no shifting behavior, or no need to for running average. So this is only, let's see, a final tip. So when you should use let's see, reach the layer norm, it's good for small batches, for NLP task, and also for online learning. So it's consistent, optimized, friendly, and battle test in all the big models. So batch normalization, it changed the game, but the layer normalization brought it to the next level. If you are building anything from chatbot to translation models, so this is you go to this is you need to go for the layer normalization. So if you like this, please subscribe into my channel, like the video, and if you have any question, please drop it down in the comment below. Thanks for watching. Do you really need to train a neural network from scratch every time? So what if your dataset is too small to train deep learning model properly? Why spend days, maybe months training when someone already trained a powerful model on millions of images? Is the isn't there a smarter way, let's say, to reuse the existing knowledge like we do in our real life? What if your model couldn't remember how to recognize shapes, texture, or objects before even see your data? So if you have any question of the ask yourself questions about this, so welcome to transfer learning. So it's how modern AI system learn once and apply everywhere. It's like a musician who learns one instrument and then pick up other, let's see, faster. So let me now talk about the, let's see, the objective of this lesson here. So as you can see here, transfer learning is learning once, apply elsewhere. So we will see how the what is the transfer learning, what are the main components of the transfer learning, and when not to use the transfer learning, and what are the popular, let's see, framework. So as you can see in this image here, this is the ResNet ResNet 18 architecture, and this trained on an ImageNet with a huge number of images, millions of images. So could we use this, let's see, as it is as a trained model, and use it for our, let's see, data? The answer is yes, but we need to know how to use it. And as you can see here, this ResNet, it was trained on ImageNet, and it has 11, it's almost 12 millions parameters. And the number of layers, it has 18 layers and 17 convolutional, and one fully connected layer. And the input size is 224 by 224. So as you can see, this is it used the main features of the ResNet. It used residual connection and max pooling. And residual connection, I will try to make a video on this because I haven't done this before. And it was the winner in 2015. So as I said in the beginning, imagine this, for instance, the trained model, the pre-trained model, and it has image data, and this is the hidden layers, let's see, extracting the features, and this is the classes to classify the images, or to classify any type of data. So this is let's see, a connected fully connected layer, but just as example. So because ResNet, it's use a convolutional neural network, not like this. And just to see to show you the principle of the transfer learning. The transfer learning, as you can see, I will use the same architecture, but with different classes. As you can see here, I have, where's the classes? Okay, maybe it's removed, I don't know why. So I have two different classes. Let me just see why it's not there. Yeah, it's, as you can see here, let's just as example, I have used this pre-trained model as the number, the input size, let's see, has to be the same. The hidden layers must, I mean, even at least the first layers has to be exactly the same. And you can see, for instance, the last layer here is updated. So this, I have only three classes. So I can adapt the pre-trained model and use it for my new task. So this is how the transfer learning. This is answering question: can I use the pre-trained on my dataset? Yes, with transfer learning. So why using the transfer learning? Transfer learning is saving much time. So instead of training your model on a huge number of images, and you need also, I mean, from scratch, and also you need a lot of time, a lot of data, and also resources. And if you have small data set, you won't be able to use the neural network. You can use transfer learning. So sometimes you have only a small data set. So this is a perfect for your data set. And also better performance. Sometimes if you use a transfer learning, you will get a perfect result, or let's say satisfied result, even with training with few epochs, let's say 3, 10, 5, it depends on your data. And what are the components of the transfer learning? You have the pre-trained model, which is a model that trained on a millions of images, and it took for the training, it took several days, several weeks even. And the second one is this pre-trained model is used as a feature extraction, and the new model will be only updated the head of the classifier. As you see, as you see here, it's removed again. As you see, this is the same architecture but different classes. And this part here is called fine tuning. And as you see, the previous layers, let's say the first some layers have to be frozen. It means no update during the training. Only this part should be updated. And the popular frameworks could be TensorFlow, PyTorch, and Hugging Face for NLP. So for today, I will use PyTorch. And when you would like to use transfer learning, or when should you use transfer learning? When you have a small data set and you have no resources, and you have, let's say, no time to train the model from scratch, so you should use transfer learning. And try to avoid transfer learning when you have a big data set and completely different from the trained model. So let me just show you one example. ImageNet. It was trained on such images, on animals, on human, cars, many classes. And let's see if you see industrial, let's see defect detection. Let's see have to have a data set. So as you can see here, this is different features, different shapes, different appearance. So I'm trying just to tell you that it might be work, but try to if you have a different data set from this, you can see here it's a different data set, right? And the features of everything is different. And if you have a different data set, try to train it from the scratch, and try to only use the one that is somehow relevant to yours. And you can see it's your task is completely different from the pre-trained, and this one is a different task, this one here. And the data set, if you have a big data set, try to just use your own model. You might be using the ResNet. Where's the ResNet? You could use the ResNet network, but you need to update the whole weights. I mean, use it as it is, and for each layer, you don't need to freeze the layer, the weights. You need to update everything here. So now let me just show you how we can do this in a PyTorch. Okay, so let's start. So here, this is the Jupyter notebook, and you can see I have the transfer learning. I will try to import the libraries, transfer for pre-processing the images, and also loading the data with 10 classes, let's see, and loading the pre-trained model, which is ResNet in our case, ResNet 18. You can, of course, you have to choose whatever you want. There are many pre-trained model I will show you. And we need a function to calculate the parameters, and also freezing the layers of the trained model. So to save time, we need to freeze the layers, some layers, and we need to, oh, sorry, oops. We need to modify our classifier and then training the model. So let's start from this. So we need to import torch, import torch vision. This torch vision has the models and also the data sets, and of course also the transformers. Let's see, transformers, import transformers as transformers. You can use it, or maybe you can also use it as, choose whatever you want, the name. This is fine. And import torch dot nn as nn. This will be used to update the pre-trained model and updating our, let's see, new classifier. Now we might also need numpy as nb, and we also need importing from torch, from torch we need, yeah, before this. So after importing the torch, I mean the nn, we need to import the optimizer from torch dot optimizer import import name. Let's see, as optimizer. And now we might need the models from torch dot from torch vision import models. And you can see here, if we click on this, you can see this is the OD pre-trained models, and under each category you have many let's see, versions. So if you jump just to ResNet, you can see ResNet 18 with ResNet 15 ResNet, and it has many ResNet, and we will use, let's see, for this, for example, this one here. And you can just even use with MobileNet. You can use MobileNet, and you can use whatever you want from version here. So as I mean, you can use it with a transfer learning. And now we might need to the device to check if we have torch.device. Yes. So the device should be coda if torch dot coda dot is available. If it's available, else use a CPU. So if you see, now let's print the device. Let's a CPU because I have no GPU in this device. Okay, now we have the transform. We need to transform is equal to transforms dot compose. This is used for the pre-processing the images. So once we have the images, it will try, let's see, let me remove this. It will try to let's see, I need to transpose dot resize the image. Okay, and resizing the image, I need 224, 224, because the input of the ResNet 18 is 224, 224. Now we need also to convert it transforms dot to tensor. There's no parameter here, and also we need transforms dot normalize. We need to normalize the image, and we have the mean. Let's see, just let's see 0.5, 0.5, 0.5. It's fine. But for this, you need to see the ImageNet. Let's see transformation. Just to see why, because it's taking the mean and standard diffusion of the whole images in this dataset. So, and let's see, just copy this. And use it here. And this is the only the transformer. Of course, you need to change also this the mean, but it's just fine. You know how to do it. So let's see, run this. It has nothing to do. So now we need a data set. So train set is equal torch dot torch vision, indeed torch vision dot data sets. Which data set we would like to use? We would like to use this one here with 10 classes. And root is equal data, and see if the, let's see, trained is true, we need to use it for the training, and also download is equal also true. If it's not there in the directory, it should be transform is equal transform, it equal this one here. We need to transform these images. So we will download the images, I mean download the data set, and the transforms will be used as we have done it here. Okay, so I think the parameters are enough for that. Yeah, and I just copy this 3 lines, and it's taking the first 2000 images as the trained images, and it will be in the train loader, and each batch file has 32 images, and the shuffle is true. So it means every, let's see, every ebook we will have a different images, batch images. Let's see, now we need to generate to get our model. So we have imported models dot resnet. We need 18. Now this should be enough, and we could also print the model dot parameters. So let's try this first. Run. Okay, it will try to download the whole images, the dataset. This might take few minutes. I will pause the video. Okay, finished. Oh. So this is our model. I will see. You can see this is the ResNet parameter, ResNet 18, and you can see it has, let's see, four blocks, but called the layers, layer 1 and layer 2 and layer 4 till layer 4. and you can see that the fully connected layers at the end of the layers, the input is 512, and the output, let's see, the number of classes will be 1000. And for this we need just to update this part here, and the whole part from here should be the same, and also including the weights. Now let's write a function to calculate the parameters. Count parameters model def. Total parameters is equal sum of p dot model, not model. Let me just copy this because it's yeah, I have copied. I can't memorize everything indeed. So this is the parameter. Here you will load the parameter, and for this parameter you will try to sum up number of elements, and the trainable parameters will be true. Let's see, sum of the trainable parameters if the requires gradient is true, and you'll have total number of features, total number of parameters, and the trainable parameters. And if we see, let's see, just run this function, and let's try to print, let's see, final layer. You can see model dot fully connected. We also need to print number of parameters, or maybe also a number of classes. We see model dot fully connected layer dot out features. You can see here in this is the out layers, out features. And we might also need the parameters. Let's see, this calling this is equal count parameters. The input should be a model, and we need to print number of parameters. Let's see, total params, we also need to trainable parameters, So if you see, the final layer is 512, and number of feature, let's see, classes is 1000, and total number of parameters is this one here. It's 11 millions parameters. It's almost 12, not 12 millions parameters, almost. Now we need to freeze these layers. So let's say for we need to param, this is fine, I think, in model to parameters, param dot require requires gradient. It should be this. I don't know why it's not showing. Is equal false, and let's try model. Oh, I just forgot this parenthesis. And now if I print the number of parameters, let me just copy this and put it here. And you can see now the total parameters should be the same, but the trainable parameters will be 0 because I have add this freezing. So parameters requires gradient is equal false. Now let me just create another variable, model transfer learning is equal model. You just need to save it in another variable so I can save the model as it is once I have changed anything. So now number of features is equal model dot fully connected dot input layer, input features, and let's see, print. You can just print number of features. Num of features. Now we need to update our classifier. So we will see model transfer learning dot fully connected layers. Okay, then we will need this linear number of features, and the output should be, let's see, 10 classes. So now we have a different output classes. We will see how to print the number of classes and etc. So let me just run this, and you have seen transfer classes, number of classes. Let me just create another one. This is markdown. Let's see just a code, and let me copy this. What you expect to have a number of classes, and what you expect how many total number of features, and also the trainable parameters. So you can see number of classes is 10, and total number of features, total number of parameters will be less. One. If you see, it's this number of features. It almost minus 50,000 parameters. So we reduce the model with 50,000 parameters, and the number of trainable parameters will be 5,000. And in the one of our videos, how to calculate the number of parameters, I have explained how to calculate the number of parameters in the CNN. So if you have any question, please drop a comment. Drop a question in the comment below. I will try to answer. So now we can see this is the transfer the new model. Now we need to add the classifier. So not the classifier. We have already did the classifier here. Now we need to train this classifier on our data. And let's see. In the beginning, you need criteria. Let's find criteria. It's equal. You need to use cross entropy loss. You also need optimize is equal opti dot Adam. We need to update the model, the parameters of this model, the transfer learning. Fully connected, then parameters. We need only to update only this this part of the, then the learning rate, it's fine to see it like this. Mhm. Should be already imported here, this one. Optimizer, Adam. Okay, with this, we have seen this. Freeze optimizer got an empty parameter list. And the error is here. We have added the parameters and the learning rate. Sometimes you need to use the parameter name, but it's not helping. So let me check. Okay, this is only this parentheses, just solving the issue. As you can see here, I have the error. I just forgot to add this one here, so it should work now. So now we need to see for ebooks. Number of ebooks, let's see, in a range of 100. Let's see. And you need to calculate running loss is equals 0. And now we need to go through our dataset. For we need in images, then the label n train loader. We also need to put these images in a to in a device to device, and we also need to put also the model. Yeah, don't forget to put this. If you put the model, the images in a device and the models in another device, it won't be work. So please make sure that model transfer learning is equal model transfer learning dot to, then we need to put it device equal device. So because this is needed indeed, otherwise if the image is in a different CPU or GPU and the model in a different GPU, it won't work. So the model and images have to be in the same device. Okay, so optimizer. So we have defined the optimizer here. Adam transferred. Indeed, in the beginning to have it as 0 to reset, then output it will be model and images. And the images, you see, it will be in the train loader. It will be resized, converted to a tensor, and also use the normalization, or let's use standardization. And this is the right way, the right name, because you can see here, because the normalization, the the loader will use the transform, and the transform has this stuff. Okay, so we're almost done. Now we have to calculate the loss, and we need criteria label, compare the label with output, and this will calculate the loss. And now we need to have a loss dot backward to update the weights, and optimizer dot step, and let's calculate the running loss is equal loss dot item. And here for each ebook you need to print, for instance, ebook. Let's have use this one here, and ebook is ebook, and out of, you can see, because it's only 100, you can see here number of ebooks is equal 100, and change it here to ebooks. If you want to, let's see, to make it more efficient, out of ebooks. So this is the training model. So now this will use the ResNet model with after the freezing the layers, and train the model only with these few parameters, with this here, and only for our small data set. And I think that's it for today. And if you like the video, please subscribe into my channel, like the video, and if you have, of course, any question, drop it down in the comment below. I will answer it. And thanks for watching, and happy learning. Bye bye. Hi everyone, welcome back to my channel. In today's video we are diving into feature extraction. So imagine you have a pre-trained model like ResNet 18, A15 or 101, and or maybe if VGG 16, 18 or 19. And this pre-trained model is already trained on a large data set. And imagine you would like to use this as a feature extraction. So you mean, because the ResNet, it has several layers, and you would like to extract a specific, let's say, features from a specific even layers. For instance, ResNet 18, it has 4 layers. 4 blocks, because each block has several convolution neural network. So I will explain this in, a theoretical background behind this in the next video, maybe, or maybe the after one. Uh, then you have to use this pre-trained model to extract features from your images, uh, for your images, and use this, for instance, in a transfer learning, as we have done it in last time. And anomaly transfer learning is try to extract, for instance, features from the first few layers, and you will update the the rest of the layers. So this is called transfer learning. I have also uploaded a video on this. And also anomaly detection is trying to extract features from this image, from this images, then use these features to do anomaly detection. We will see it in a, I mean, a complete example. Let's see in a couple of videos. And also it could be used in image retrieval and self-supervised learning. So let me just show you how to use how to extract features from a specific layers in a neural network. So I will use, for instance, this 18, but you can use I will just show you now in a minute. So let me just close this one here, and this is our code. Let's see. I'm trying to use Jupyter Notebook, so it might be easy for you to follow. So now I would like to import the packages, and for the packages I would like to use import torch. Yeah, you can see here it's not defined, but because I have to select the kernel, and the kernel it's already identified because I'm using Beauty. So now let me just import the other one, torch torch.nn not one, this one, dot functional as if. Now I need also to import the models from torch vision, import models, and you can see here I have defined this dictionary. So if I'm using ResNet 18, the model, this will be retrieved. I mean, I will use this one here. If it's white ResNet 15, I will use this, and etc. This is only a dictionary, so it's easy to. I mean, it's normal dictionary. Now let's see. I would like to create a class for feature extraction. So what I will need indeed. So I will need the backbone name. Then I might need the layer. So which I wanted to extract features from. So it has, as I said, it has 4 layers, but it's not 4 layers, it's 4 blocks. And we will extract these features from every, let's see, every layer we would like to to extract. And I think this might be enough. So let's create a class feature extraction. Let's call it like this without. And let's see, I also need to import this one here. Import torch dot nn as nn torch. Yeah. Now I will inherit. I will inherit from this n dot module, should be capital, I think. Module, yeah. Because the class has to be starting with capital letters, as you can see, M, and I'm trying also to do it like the same. So we need to initialize the class, the init, the super class. Now, no, before this, sorry. Before this, I have to define def init. Oh, cool. So as I said, we need the backbone name. Let's see the layer index, because it's maybe in the indices, because it might be more than one layer. And also we need a device to put the result in this, I mean the model, and also the images and labels, if we have labels, but here we don't have. And let's see back, I will see backbone. Backbone, this is called backbone, it's a model, but it's a fancy name, but yeah, so there's no space here. Self dot backbone, and this will, I will get this from here, depends on the backbone name. So I will see backbones, which is this one here, and I will just put the name, and I might also need this weights is equal true, and progress. Oh, we don't need this progress, it's fine. By the way, you can also use this, like for instance backbone, it's let's make you just do it. I mean, if it's this one, it's not defined here, you can just see model and do, for instance, this weight equal true. Yeah, with this method, or I mean with this step, or this, it's the same, but I just try to define the backbones in a dictionary, because here, if so, I would like to see if backbone name is equal to resnet 18, then do this. If then I will do the next one, but imagine you have 100 backbones, so you'll have to add if statement here 100 times, but this will save let's see time. Now I will just add the device self dot device is equal device self dot layer, let's see, layer index. You just need to copy is sometimes it's dangerous, but it helps a lot. And let's see, layer index. Now what we need to do after this, we need to add a function, for instance with I will just give you this hint here for free, of course. So you can define extract, for instance, this method, and you can see here, for instance, self, and the batch size, I mean batch, the images we'd like to extract. Sorry, but for this, let me just add bass. So bass means you don't have any definition, let's see, or but try always to use forward function self on batch, because we already inherited the from this in module, this already defined in this one, and this forward function, it will called automatically, I mean not automatically, but let me just add here one symbol. If I see, if I already extract features, for instance, initialize this, right? Now if I see if, and here's the image, this will call directly the forward function. And if there's no forward function and only this it's only extract, so for this I will add dot extract and adding the image. but I prefer just to use a forward function because it's a fancy and also called without mentioning, let's see, the method itself. Okay, so let's back for this. Now, before this, we need to add with torch dot no gradient. So we don't need to calculate any gradient for this forward function because it's not training, it's just only extracting features. And I will see batch 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 is equal self dot backbone, and I will add no dot conf1 because it has conf1, and I will see batch. Okay, it's batch. And as you can see here, I will just this is the batch, this is the image or a set of images, and it will go through the backbone through the conf1 and return the result. Now I will go further with calling this. I will just, it's a call batch, and it's the next one is batch normalization 1, then relo batch 1, then max pool layer. So this is using a max pooling layer. So please, if you are not familiar with any of these, I have also uploaded a complete playlist for the main components of the new CNN, and it's explained with a real example, and I try to make it really simple. Now I need to extract the layers, the layer 1. It will be also a backbone, and let me just show you this. It's, you can see just layer 1, and the input should be the batch size, right? And see, in the next one the input should be layer 1, but the output should be layer 2, right? Again, the input should be layer 2 and the output should be layer 3. Again, the input should be layer 3 and the output should be layer 4 because we have 4 layers. Now, as I said in the beginning, let's see layers, all layers, it will be layer 1, layer 2, layer 3, layer 4. So because we have 4 layers, just an example. But now I have these 4 layers, but indeed I need to extract only what I have here in the layer index. So for that I will see if self dot layer index is not none. If it's not none, I mean if it has input, let's say 0, 1, 2, 3, then I will see layers equal compact layers compact for loop for in self dot layers index. So now if I see, if you see here, if I have only layer 0, let's say I would like to extract only layer 0, I will see here layer 0 is, and let's see, for instance, 0. Wait, I have something wrong, I think. Oh, no, really, else if everything is fine. So I will say this is the layers, and if it's F0 is in layer 1, then it will add it here. If not, we will see it will add only the in the layers itself. So now let's see, we need, let's see, to concatenate these features. But before this concatenating, I will try to show you the results. Let's see, return layers. Oh, because adding the layers now, it will. Okay, let me just show you some results. So let's see, I need to initialize the extractor, which is feature extraction. So this, I would like to use this class to extract some features. I just want to show you what is the output of these layers. Okay, before using concatenation, let me just device. We need to see what is the device. Device is equal torch to device coda f torch dot coda dot is available, else use CPU. I have no CPU GPU in my PC in this one. So extractor equal feature extraction. Now we need to define some some parameters. So backbone name is equal to resnet 18. Layer indices is a list 0, 1, 2, 3, because it's starting with 0, so I will just need to add now device bit 2, 3. Now device is equal device. So let me just run from the beginning and see if everything is fine. Okay, this class as well, and this is still not using, but I'll just run this one here. You can see it has no issue now. And I have also, I need to the transformer, so I just added here because I have already explained last time. So now I need to read images. Now from pillow import image, and now I will see image is equal image dot open, give it the path. I think I have a path here. Let's see, image dot gbig, and for this we need to convert to RGB, because ResNet it expect to has an image with 3 channels, so that's why we need to have this converted. This image might be, let's see, grayscale image only with 2 channels, so we need to convert it to RGB. Now batch is equal transform. Did I run this? transform image. Then we need to unsqueeze this, squeeze 0, then to device. I think this steps are clear. So this one here, I will call this function here transform, and it will resize this image into this size, convert it to a tensor, and normalize it, or standardize the image. And this unsqueeze here, it will give me, let's say, 3 times 2 2 2 2 4 2 2 2 2 4. But the algorithm is expecting a batch size, and it will just adding this one here. So this is the unsqueeze. And let's see here, I will just call this embeddings. Then I will call this extractor, which I already defined here. And now I will add only the batch. So as you see, I haven't added this forward. So because this one, it will be automatically called if I just add anything in the brackets. This one here, it will call directly the forward function. Now let's see what is the printing the side print, because this will be a list indeed. So let me just try. Cool. Okay, the image is not there. Let me just check. Okay, let's run. This is the transform, and we have, I read the image, and the, if you don't have any, okay, with this. So I think I forgot this one here, the brackets. Oh, see, a big mistake. Yeah, as I told you, the copy and paste might be okay, but see, I'm trying to extract now the, let's see if I don't change it, will it work? And this is the extractor. Oh, it's working. Shit. I mean, this is a big issue here. So I need the layer 2, layer 3, layer 4, and 1 2 3 4. Yeah. And with the extractor, I think I need to run this again, because it's using this class. And let me now printing the features. Print. Okay, yeah. Embedding size, I think it's list, so it won't be easy to print. But let's see, length. Yeah, it has for example for layers, but we can do like this: 0 dot shape dot shape. Okay, and this is the first shape. And if I say embeddings, layer 1, layer 2, and you can see here I have extracting the, let me just remove this, not needed. So I have the feature 0, 1, 2, and the 4, of course, the 3, because it's starting from 0, so it will be 3, and here should be 4. Now, so as you can see, with yeah, here I have defined the number of layers. So now if I see, I just need that first 2 layers, it will just start zoom, then like this, and of course I'm expecting here error because it's only the 2 layers, this and this, layer 1 and layer 2, layer 3 and 4, it's not included, so that's why I have error here. But where is the, where did I change it? Yeah, here, okay. Then this should work now. Okay, so now as you can see here, I have layer 1, layer 2, layer 3. But at a certain point, let's see, I need only one feature. Just concatenate all of these features and put it in a one big tensor, let's see. And that's why I have added here the concatenated layers. And for the concatenation, I will see here, let's say call it embedding. Embeddings is calling layers. Why it's not even, yeah, I need to, I have to add self because it's a member of this class. Okay, so now we need to return the embeddings and run. Also this should be activated, then this one and this, returning a global blah 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 self concatenated. Okay, it's not self, yeah, my mistake, but what did he find here? Maybe it has, this one should be defined before, but I'm not quite sure. Let's start with extract this one. Now we need this. Okay, now it's working. So as you can see here, but now this should be, let's see, removed because there's no now, it's only now one vector. Oops. So now it's only one vector of this. You just see it here. So you can see this is the first layer, right? And it has 65 50 56 times 56, and it has 64 here. And in the second one it has 100 and blah blah blah. And we would like to reshape or resize the next layers and make it similar to this one here. And as you can see here, if you sum up all of these values here, I mean 1 2 3 4, it will be 906. So this is the last features, or let's say the embedding extracted from the 4 layers. And this vector you can see it as put it, it could consider as an input to any algorithm, let's say. And I'll show you in a couple of, let's say, days how to use this for anomaly detection. And let's say, for instance, now it's 960, right? And if I just use just two layers, the first and second layers, and for that I will of course have only 64 plus 128. It will be 192. And that's it, how to extract features from any layers, and from let's say any network. Just this is related, this code is related to ResNet series. And let me just use ResNet 2, I mean 18, and see what is the size of this. Okay, it's need to be downloaded in the beginning. Done. And I need number of layers. This is not need to be running. And see now, many features are included only from these two layers. So that's why we need, if you have, let's see, if you need to extract more, let's see, patterns or more complex features, you can use wired ResNet. I mean, yeah, wired ResNet. But I have also some experiments, and I have done intensively test all of these. So there's no, let's say, a big difference in terms of accuracy. Of course, there's accuracy, but not that too much. Okay, this is how to do feature extraction with ResNet networks. And if you like this video, please subscribe to my channel, like the video, and of course, if you have a question, please drop it down in the comment below. By the way, before this, you can also try to add another backbones, for instance, mobile net or VGG 16, 19 or 18, or and try to adapt. Of course, this code has to be adapted based to run on the other, let's say, the other backbones, because this is only for the ResNet versions. Okay, thanks for watching, and see you next time. Welcome to the world of deep learning, where every pixel counts and every computation matters. So today we are diving into the power of one one times one convolution. It's a small, but it's back punish. Let's see how it's working. So one times one convolution might sound simple. It's apply a tiny one by one times one filter across each pixel location. But here's what is happening. It combined information across all channels or depth. So think of it as a many fully connected layers that operate on each special location independently. So it's like having, let's say, for instance, this example here. I'm just trying to make it animated so you can understand this. For instance, this is the input image here, and because the image it's only one channel, so I have only one filter of one. This is, let's see, one by one filter. So now you can see this times this will multiply each value in the filter and just put it here. And because I have only one channel, so I just only have the filter, it will be only one. So if I have let's see, three channels here, the filter will be 1 times 3. It means three values, one values for each channel. And how it is working, it's just sliding one by one this filter here across the image, and the output of the image will be, this is, for instance, the filter size is one by one, right? And this the output will be the image width times height times 1. So it means I will just get the same image with the same because I have only one channel. So, and what is the advantage of using one convolution neural, one times one, let's say conv? So it's let's say dimensionality reduction. So let me just show you here this example here. So assume that I have this image here, and this is 16 by 13 by 12. So because I have 12, the channel is 12, so I have 12 filters, but each one by one. So what are you expecting to have the size of the feature map? So if you see 16 by 13 by 1, this is right. So the final result of this will be 16 by 13 by 1. So it means all of this dimension, for instance, here is just summed up into one value after applying the filters. And for instance, this one here, the value of this pixel in the whole volume, it will be this one here, the value of one pixel. And the second pixel, it will be for from here till the end of this volume, it will be this one, this value here. So it's just simplifying the. Let me just see if I have the code is here. Sorry. Okay, so if you see here, I have 3 channels. Okay, I will just stop the video. So let's say I have these 3 channels, and as you can see, for each channel I will have one filter. So the filter will be one times one. So since this one and this and this. And now I will try to multiply. Let me just try to stop. It's so fast because I just increase the time. So this indeed done by Mani in Python. Yeah, perfect. So I got it. So as you can see, I will multiply 4 by 1 plus 7 by 1 plus 2 by minus 2. And here, this one, for instance, 1, 2, 3, it's only the channel number. So it's not, let's see, let's see, mathematical or so. It's just layer 1, layer 2, layer 3. And the output will be 7. And this will be here, added here. And etc. This is only, I can just show you the code. If you are, let's see, need this code, I can give you this code. But let me just back to the presentation. And yeah, so what is the difference between 1 and 1, 1 times 1 and 3 times 3? It's already obvious. So it's just focus on one pixel, and the 3 by 3, it's just specialists try to detect the patterns or special patterns in the region. And the computational cost, of course, this one is cheaper and this one more expensive because you need to multiply for the whole 9, let's say 9 values, and here we need only to multiply one value. And the perspective field is 1, and the perspective field here is, let's say, 3 by 3. And primary depth, primarily used to depth transformation and special, and it's also used in, you can see one by one convolution in Google Net network, and also ResNet is used in ResNet heavily, and I think in MobileNet. So this is the powerful of one by one convolution. As you can see here, it's just try to reduce this dimension here to this one here. That's it for today, and if you like this video, please subscribe into my channel, like the video, and if you have a question, please drop it down in the comment below. Thanks for watching, and see you next time.